Yeah.
What to you is the most beautiful, speaking of hyenas, what to you is the most beautiful nature-inspired algorithm in your work that you've come across? Something maybe earlier on in your work or maybe today?
I think that evolutionary computation is the most amazing method. So what fascinates me most is that with computers is that you can get more out than you put in. I mean, you can write a piece of code and your machine does what you told it. I mean, this happened to me in my freshman year. It did something very simple and I was just amazed. I was blown away that it would get the number and it would compute the result and I didn't have to do it myself. Very simple. But if you push that a little further, you can have machines that learn and they might learn patterns. And already, say, deep learning neural networks, they can learn to recognize objects, sounds, patterns that humans have trouble with. And sometimes they do it better than humans. And that's so fascinating. And now if you take that one more step, you get something like evolutionary algorithms that discover things, they create things, they come up with solutions that you did not think of. And that just blows me away. It's so great that we can build systems, algorithms that can be, in some sense, smarter than we are, that they can discover solutions that we might miss. A lot of times it is because we have, as humans, we have certain biases. We expect the solutions to be a certain way. And you don't put those biases into the algorithm, so they are more free to explore. And evolution is just absolutely fantastic explorer. And that's what really is fascinating.
Yeah, I think I get made fun of a bit because I currently don't have any kids. But you mentioned programs. I mean, do you have kids?
Yeah.
So maybe you could speak to this. But there's a magic to the creative process. Like with Spot, the Boston Dynamics Spot, but really any robot that I ever worked on, it just feels like the similar kind of joy I imagine I would have as a father. Not the same perhaps level, but like the same kind of wonderment, like that exactly this, which is like, you know what you had to do initially to get this thing going. Let's speak on the computer science side, like what the program looks like, but something about it doing more than what the program was written on paper is like, that somehow connects to the magic of this entire universe. Like that's like, I feel like I found God every time I like it's like because you've really created something that's living.
Yeah,
even if it's a simple
it has a
program.
life of its own, has intelligence of its own. It's beyond what you actually thought. And that is, I think it's exactly spot on. That's exactly what it's about. You created something and has a ability to live its life and do good things, and you just gave it a starting point. So in that sense, I think that may be part of the joy, actually.
But you mentioned creativity in this context, especially in the context of evolutionary computation. So, we don't often think of algorithms as creative. So how do you think about creativity?
Yeah, algorithms absolutely can be creative. They can come up with solutions that you don't think about. I mean, creativity can be defined. A couple of requirements has to be new, it has to be useful, and it has to be surprising. And those certainly are true with, say, evolutionary computation, discovering solutions. So maybe an example, for instance, we did this collaboration with MIT Media Lab, Caleb Harvest Lab, where they had a hydroponic food computer, they called it, environment that was completely computer controlled, nutrients, water, light, temperature, everything is controlled. Now, what do you do if you can control everything? Farmers know a lot about how to make plants grow in their own patch of land. But if you can control everything, it's too much. And it turns out that we don't actually know very much about it. So we built a system, evolution optimization system, together with a surrogate model of how plants grow, and let this system explore recipes on its own. And initially, we were focusing on light, how strong, what wavelengths, how long the light was on. And we put some boundaries, which we thought were reasonable. For instance, that there was at least 6 hours of darkness, like night, because that's what we have in the world. And very quickly, the system evolution pushed all the recipes to that limit. We were trying to grow basil, and we had initially have some 200, 300 recipes, exploration as well as known recipes. But now we are going beyond that. And everything was like pushed that limit. So we look at it and say, well, we can easily just change it. Let's have it your way. And it turns out the system discovered that basil does not need to sleep. 24 hours, lights on, and it will thrive. It will be bigger, it will be tastier. And this was a big surprise, not just to us, but also the biologists in the team that anticipated that there's some constraints that are in the world for a reason. It turns out that evolution did not have the same bias. And therefore, it discovered something that was creative, it was surprising, it was useful, and it was new.
That's fascinating to think about, like the things we think that are fundamental to living systems on Earth today, whether they're actually fundamental or they somehow fit the constraints of the system, and all we have to do is just remove the constraints. Do you ever think about, so what's the story in Python behind PyTudes? Your GitHub repository with puzzles and exercises in Python is pretty fun.
Yeah, just it seemed like fun. I like doing puzzles, and I like being an educator. I did a class with Udacity 212, I think it was. That was basically problem solving using Python and looking at different problems.
Does PyTudes feed that class in terms of the exercises? I was wondering what the...
Yeah, so the class came first.
Yeah.
Some of the stuff that's in PyTudes was write-ups of what was in the class, and then some of it was just continuing to work on new problems.
So what's the organizing madness of PyTudes? Is it just a collection of cool exercises?
Just whatever I thought was fun.
Okay, awesome. To some degree, the entirety of the system, as far as I understand, is written in various variants of Lisp. So my favorite programming language is still Lisp. I don't program in it much anymore because, the world has, in majority of its system, has moved on. Like everybody respects Lisp, but many of the systems are not written in Lisp anymore. But Psych, as far as I understand, maybe you can correct me, there's a bunch of Lisp in it.
Yeah, so it's based on Lisp code that we produced. Most of the programming is still going on in a dialect of Lisp, and then for efficiency reasons, that gets automatically translated into things like Java or C. Nowadays, it's almost all translated into Java because Java has gotten good enough that that's really all we need to do.
So it's translated into Java, and then Java is compiled down to bytecode.
Yes.
Okay, so that's it's a process that probably has to do with the fact that when Psych was originally written and you build up a powerful system, like there is some technical debt you have to deal with, as is the case with most powerful systems that span years. Have you ever considered this would help me understand, because from my perspective, so much of the value of everything you've done with Psych and PsyCorp is the knowledge. Have you ever considered just like throwing away the code base and starting from scratch? Not really throwing away, but sort of moving it to throwing away that technical debt, starting with a more updated programming language. Is that throwing away a lot of value or no? Like, what's your sense? How much of the value is in the silly software engineering aspect, and how much of the value is in the knowledge?
So, development of programs in Lisp proceeds, I think, somewhere between 1,000 and 50,000 times faster than development in any of what you're calling modern or improved computer languages.
Well, there's other functional languages like Clojure and all that. There's, but I mean, I'm with you. I like Lisp. I just wonder how many great programmers there are. There's still like
yes. So it is true when a new inference programmer comes on board, they need to learn some of Lisp, and in fact, we have a subset of Lisp which we call cleverly sub-L, which is really all they need to learn. And so the programming actually goes on in sub-L, not in full Lisp. And so it does not take programmers very long at all to learn sub-L. And that's something which can then be translated efficiently into Java. And for some of our programmers who are doing, say, user interface work, then they never have to even learn sub-L. They just have to learn APIs into the basic psych engine.
So you're not necessarily feeling the burden of like it's extremely efficient. There's that's not a problem to solve. Okay.
Right. The other thing is, remember that we're talking about hiring programmers to do inference who are programmers interested in effectively automatic theorem proving.
Right.
And so those are people already predisposed to representing things in logic and so on. And Lisp really was the programming language based on logic that John McCarthy and others who developed it basically took the formalisms that Alonzo Church and other philosophers, other logicians had come up with, and basically said, can we basically make a programming language which is effectively logic? And so since we're talking about reasoning about expressions written in this logical, epistemological language, and we're doing operations which are effectively like theorem proving type operations and so on, there's a natural impedance match between Lisp and the knowledge the way it's represented. So
I guess you could say it's a perfectly logical language to use.
Oh, yes. And
Okay, I'm sorry.
I'll even let you get away with that. Fun.
Okay, thank you. I appreciate
I
it.
like that. So I'll probably use that in the future without
credit.
Without credit. But no, I think the point is that the language you program in isn't really that important. It's more that you have to be able to think in terms of, for instance, creating new helpful HL modules and how they'll work with each other, and looking at things that are taking a long time and coming up with new specialized data structures that will make this efficient. So let me just give you one very simple example, which is when you have a transitive relation like larger than, this is larger than that, which is larger than that, which is larger than that. So the first thing must be larger than the last thing. Whenever you have a transitive relation, if you're not careful, if I ask whether this thing over here is larger than the thing over here, I'll have to do some kind of graph walk or theorem proving that might involve like 5 or 10 or 20 or 30 steps. Mm-hmm. But if you redundantly store the transitive closure, the Kleene star of that transitive relation, now you have this big table, but you can always guarantee that in one single step, you can just look up whether this is larger than that. And so there are lots of cases where storage is cheap today. And so by having this extra redundant data structure, we can answer this commonly occurring type of question very, very efficiently. And let me give you one other analog of that, which is something we call rule macro predicates, which is we'll see this complicated rule and we'll notice that things very much like it syntactically come up again and again and again. So we'll create a whole brand new relation or predicate or function that captures that and takes maybe not 2 arguments, takes maybe 3, 4, or 5 arguments, and so on. And now we have effectively converted some complicated if-then rule that might have to have inference done on it into some ground atomic formula, which is just the name of a relation and a few arguments and so on. Mm-hmm. And so converting commonly occurring types or schemas of rules into brand new predicates, brand new functions, turns out to enormously speed up the inference process. So now we've covered about 4 of the 150 good ideas I said.
So that idea in particular is like a nice compression that turns out to be really useful. You kept bringing up sort of coding stuff up. I wanted to ask 2 things. First of all, like what programming language do you like? And also what, because you're, as a computational quantum astrochemist, no,
that's correct.
Yeah, that's right. You're kind of, you could say you're you're actually understanding some exceptionally complicated things. With one of the things you're using is the tools of computation, of programming. Is there a device you can give to people? Because I know quite a few that have not practiced that tool and have fallen in love with a particular science, whatever it's biology and chemistry and physics and so on. And if they were interested in learning to program and learning to use computation as a tool in their particular science, is there advice you can give on programming, and also just maybe a comment on your own journey and the use of programming in your own life?
Well, I'm a terrible programmer. A lot of scientists, their programming is bad because we never learned formal programming. We learned science, physics, chemistry. And then we were told, oh, you have to get these equations modeled and run through a simulation. And you're like, oh, okay, so I'm going to learn how to code to do this. And you learn just as much as you need to run these simulations and no more. So they're rarely optimized. They're really clunky. 6 months later, you can't read your own code. Yeah. My variable names are extremely embarrassing. I still have error messages for different compilation errors that say things like, at least your dad loves you, Clara. It doesn't help me at all.
There's like humor.
Yeah.
Yes.
Just like you suck at coding, but there's other things in your life. So I'm a bad programmer. And so, if that will give hope to anyone else who's a bad programmer, I can still do pretty impressive science.
Yes.
But I think I started learning MATLAB and Java when I was in college. Mm-hmm. It did me no good at all. It has not been particularly useful. I learned some Fortran. That was very useful, even though it's really not a fun language because so much of legacy code is in Fortran. And so if you want to use other people's code who have now retired, Fortran will be nice. And then I used IDL to visualize. So that simulation and body simulation, that was all Fortran and IDL. But thankfully, since I've left college, I've just learned Python like a normal person, and that has been much nicer. So most of my code now is in Python.
I should also make a few quick comments. Well, so one is you say you're sort of bad at programming. I've worked with a lot of excellent scientists that are quote unquote bad at programming. They're not. It gets the job done. In fact, there's a downside to sort of especially getting a software engineering education. If I were to give advice, especially if you're doing a computer science degree and you're doing software engineering, is not to get lost in the like optimization of the correct. There's an obsession, you can see it in like Stack Overflow, of the correct way to do things, and I think you can too easily get lost in constantly trying to optimize and do things the correct way when you actually never get done. The same thing happens. You have like communities of people obsessed with productivity, and they keep researching productivity hacks, and then they spend like 90% plus of their time figuring out how to do things productively, and then never actually do anything. So there's a certain sense, if you focus on the task that needs to be done, that's what programming is for. So not over optimizing, not thinking about variable names in the following sense. Sometimes you think, okay, I'm going to write code that's going to last for decades. In reality, your code, if it's well written or poorly written, will be very likely obsolete very quickly. The point is to get the job done really well. So there's a trade-off there that you have to make sure to strike. I should also comment as a public service announcement or a request, if there's any world-class Fortran or COBOL programmers out there, I'm looking for them. I want to talk to you. Because I think
that will not be me. I'm a terrible Fortran programmer.
But it's fascinating because so much of the world in the past and still runs on these programming languages, and there's like no experts on it. So
they're all retiring.
Yeah.
I disagree slightly in that I think because I can get the job done, I'm a programmer. Yeah. But because no one else can look at my code and know how I got my job done, I'm a bad programmer. That's how I'm defining it.
Yes. Including yourself.
Including myself 6 months later. Yeah. I'm working with a new student right now, and she sent me some messages on Slack being like, what is this file that you've got with some functions I run? And I was like, this was from 2018. It wasn't that long ago. And I can no longer remember what that code does. I'm going to spend now 2 days reading through my own code and trying to improve it. And I do think that's frustrating. And so I think my advice to any young people who want to get into astronomy or astrobiology or quantum chemistry is that I certainly find it much easier to teach the science concepts to a programmer than the programming to a scientist. And so I would much faster hire someone who knows programming but barely knows where space is than teach programming to an astronomer.
Oh, that's fascinating. Yeah. Okay. This is true. I mean, yeah, there's some basics. I'm focusing too much on the silver lining because the people that write like MATLAB code, single letter variable names, those kinds of things.
And it's accessibility, right? I want my code to be open source, and it is. It's on GitHub. Anyone can download it. But is it really open source if it's written so cryptically, so poorly that no one can really use it to its full functionality? Have I really published my work? And that weighs on me. I feel guilty for my own inadequacies as a programmer. But you can only do so much. So I've already learned quantum chemistry and astrophysics. So,
I mean, there's all kinds of ways to contribute to the world. One of them is publication, but publishing code is a fascinating way to contribute to the world, even if it's very small, very basic element. Great code. I guess I was also kind of criticizing the software engineering process versus which is a good thing to do, is code that's readable, almost like without documentation. Exactly. It's readable. It's understandable. The variable names, the structure, all those kinds of things. And
that's the dream.
You did a bunch of programming competitions. What was your interest, your love for programming? What did you learn through that experience? Especially now that much of your work has taken a long journey through mathematics.
I think I always was amazed by how computers could do things fast. If I wanted to make an abstract analysis of why it is that I saw some power in the computer. Because if the computer can do things so many times faster than humans, where the hard part is telling the computer what to do and how to do it, if you can master that asking the computer what to do, then you could conceivably achieve more things. And those contests I was in, those were the opposite in some sense of making a complete product, like a game is a product. Those contests were effectively write a function to do something extremely efficiently. And if you are able to do that, then you can unlock more of the power of the computer.
But also doing it quickly. There's a time element from the human perspective to be able to program quickly. There's something nice. So there's almost like an athletics component to where you're almost like an athlete seeking optimal performance as a human being trying to write these programs. And at the same time, it's kind of art because the best way to write a program quickly is to write a simple program, is to have a damn good solution. So it's not necessarily you have to type fast. You have to think through a really clean, beautiful solution. I mean, what do you think is the use of those programming competitions? Do you think they're ultimately something you would recommend for students, for people interested in programming or people interested in building stuff?
Yes, I think so, because especially with the work that I've been doing nowadays, even trying to control COVID, something that was very helpful from day one was understanding that the kinds of computations we would want to do, we could conceivably do on like a 4-core cloud machine on Amazon Web Services out to a population which might have hundreds of thousands or millions of people. Mm-hmm. The reason why that was important to have that back of the envelope calculation with efficient algorithms is because if we couldn't do that, then we would bankrupt ourselves before we could get to a big enough scale. If you think about how you grow anything from small to big, if in order to grow it from small to big, you also already need 10,000 cloud servers, you'll never get to big.
And also, the nice thing about programming competitions is that you actually build a thing that works. So you finish it. There's a completion thing, and you realize, I think there's a magic to it, where you realize that it's not so hard to build something that works, to have a system that successfully takes in inputs and produces outputs and solves a difficult problem. And that directly transfers to building a startup, essentially, that can help some aspect of this world, as long as it's mostly based on software engineering. Things get really tricky when you have to manufacture stuff. That's why people like Elon Musk are so impressive, that it's not just software. Tesla Autopilot is just not just software. It's like you have to actually like have factories that build cars, and there's like a million components involved in the machinery required to assemble those cars and so on. But in software, one person can change the world, which is incredible.
Standardize this.
What do you think about the giant ecosystem of frameworks in JavaScript? It feels like, because I mean, this is a side effect of how many people use JavaScript.
Yes.
A lot of entrepreneurial spirit, like create their own JavaScript frameworks.
Yep.
And they're actually awesome in our own different ways. And this is an interesting question about almost like philosophically about biological system and evolution, all that kind of stuff. Do you see that as good, or should some of them die out quicker?
I think that maybe they should. Now, jQuery was a very clever thing. John Resnick made this library that was sort of query and do and blended sort of CSS selector syntax with JavaScript sort of object graph or DOM querying, and made it very easy for people to do things almost like they were learning jQuery as its own language, domain-specific language. And that, I think, reflected in part the difficulty of using the document object model, these APIs that were originally designed in the 90s for Java as well as JavaScript. They were very object-oriented or even procedural. They were very kind of verbose. And it took like a constructor call and 3 different, hokey pokey dances to do something, whereas in jQuery, it's just one line.
Yep.
Right. So that fed back finally into the standards. It didn't mean we standardized jQuery. It wasn't quite that concise, but you find now with the modern standards that we were working on in the HTML5 sort of effort, that things became simpler. The fetch API and the query selector API, document.query selector. A lot of things can be done now in raw JavaScript that you would make more concise and terse in jQuery, but it's not bad. It's pretty good. Whereas in the old DOM of 15 years ago, it was just too verbose.
So maybe the frameworks were born kind of because JavaScript lacked some of the features of jQuery. And so like now that JavaScript is swallowing what jQuery was, then the frameworks only the ones that truly add value will stick around, and the other ones will die out.
And that highlights this division between the core language, JavaScript, which can show up in other places like Node.js on the server side, and the browser-specific APIs or the document object model APIs, which are even managed by the W3C, the standards body that was often XML La La Land when we were doing real JavaScript standards in ECMA. And you have this division of labor, division of responsibility, and division of style and sort of aesthetics, and also speed. So the document object model really stagnated after Microsoft kind of de-invested in the web. And Microsoft did something in their haste, in the spirit of Netscape, doing things quickly and getting on first, called DHTML. And some of their innovations that were like an alternative document object model didn't really get standardized until HTML5, when we pragmatists at Opera at the time, Ian Hickson, who went to Google, Apple, and Mozilla said, let's XML is not going to replace HTML. HTML4 is too old. Let's standardize HTML5 based on all this good stuff, including that DHTML variant.
It's a special moment in the history of all of computing. It's we'll talk about it later, but it's arguable. It's possible that the entirety of the world will run on JavaScript at some point. Yeah. So like it's like those days. It would be interesting if you could just describe actually zooming in on how the cake was baked from the several days that you were working on it. What was in your mind? How much coffee were you drinking? Yeah. Were you nervous? Why you're freaking out?
I'll try to remember it. I mean, you're right. There are these pregnant moments you see in hindsight. Maybe they're overrated, but like Hegel sees Napoleon on horseback at Jena and says, "There's the world spirit on horse." And I knew that there was a chance to do it. Mark knew, and he was my executive sponsor, and he was the one sort of brainstorming how the JavaScript should be right there in the page. That was important for him to say that, because I thought so too, but a lot of people were like, oh, you can't write programming language in the middle of the markup. Mm-hmm. And indeed, there are problems. If you did it naively, you'd see the code laid out as like random gibberish. So I had to figure out how to hide that. That was a challenge.
Is that a breakthrough idea? I mean, so you and Mark thinking about this idea that you just inject code in the middle of the markup
of the web page. Yeah, it was considered kind of heretical. There was an SGML guru, I forget his name, but he corresponded with me. And at first he was angry. He's like, you should have used a marked section. Why didn't you use a marked section? And I said, well, HTML marked sections are not part of HTML, by the way, and they're not supported in the browser. Yeah. And so I did some hack that was equivalent, and over time you could do the proper HTML thing. But eventually he came around, and it was, again, sort of evolutionary necessity. It was almost like introgression, like the idea, which Lynn Margulies, I think, helped get across, that we have to consider mutualism in biology, that maybe, mitochondria were ancient prokaryotes that got into the cell and became beneficial. Yeah. Somehow, the same sort of thinking applies. You have to embed JavaScript in HTML. It's going to be a good virus. It won't hurt you.
The code becomes data in the sense it just gets carried along. But is there the side of the, so you were focusing on the Netscape at that time? Doesn't the browser have to interpret correctly this a mix of HTML and whatever code?
I had to hide it from old browsers, including Netscape 1.1, which was predominant then. So I used an HTML comment, but inside the container that comment lived in, the script tag, which is a new element, I could make different semantics in Netscape 2, where those HTML comment delimiters, instead of being multi-line brackets, became one line, or essentially one line.
So you wrote, JavaScript was written, the programming language was written as a comment.
A comment for old browsers, and a set of brackets that were ignored with real code for new. And it was this two-way comment hiding hack, as I called it, that was absolutely necessary for us to get off the ground. We couldn't have bootstrapped JavaScript without it. We didn't have scripts that were loaded from a separate file. The only scripts in Netscape 2 were inline in the document.
What were the challenges here? Typing, what were the choices you were thinking about?
Garbage collection.
Garbage collection.
I didn't have time to write a garbage collector, so I didn't at first. So the thing was using essentially arenas, or what GNU calls obj pools, and just would run out of memory eventually. And I added reference counting in a hurry after the 10 days in which I hacked. So after I was in the server team doing HTTP 1.1 and thinking about the language, I finally got transferred to the client team in early May. And that's when I got the go sign from Mark, and it was like, we can't wait, because people inside Netscape are doubting. Even people inside Sun are definitely doubting. Bill Joy was the champion, but he was like alone in that, in seeing there was a role for JavaScript as as I call it, the sidekick language, robbing the boy hostage. Frank Miller put it in The Dark Knight Returns. That there was this silly little language that would be the glue language, and it could become important over time. And you were better off having that complementarity, that pairing of languages, just like Microsoft Stack did with Visual C++ and Visual Basic.
So what was the big moment of I'm done?
So I had to do a demo. I forget the dates. I think for a history of programming languages paper that Alan Wersbrock did with my help, he did a lot of the writing. I think it was the 10 days from like Thursday evening through to the following weeks, the whole of that week, and then into the Monday.
Did you get sleep?
Not enough. And I was really going fast because I'd already used a lot of C compiler and front-end compiler knowledge that I'd gained from undergraduate school. When I started getting into computing as a renegade physics major, people were formalizing more efficient bottom-up grammars, parsers for bottom-up languages. Really, LALR1 was the big thing. And I studied all this and learned how to parse them. And in the end, if you're doing C languages, you often do what Dennis Ritchie did anyway, which is a recursive descent parser. You can hand code it. And I did that for JavaScript in a blazing hurry. Mostly got it right. I didn't, have precedence inversion problems or other bugs, but I copied a lot from Java and C. And I tried to keep things simple, like the equality operator in those 10 days sprint between two objects of different dynamic type said, no, they're not equal. Their types are different. Mm-hmm. And then after that, I had internal early adopters, and they were using JavaScript to like match a number against a database field that had been stringized. And they said, oh, can't we just have implicit conversion? And like an idiot, I agreed. I gave them what they wanted. I was trying to please them and get adoption. And that, broke what equivalence relation nature there was to the double equal. There's some edge cases with not a number that break that up too, but it really broke it. Having implicit conversions in that operator is something that people still roast me over.
So let's talk about two things. One, it sounds like the comparison operator, the equality operator, is the thing that you regret. So maybe
making it sloppy. Yeah.
Making it sloppy. So what is the biggest thing you regret in those 10 days, and what is the biggest thing you're proud of?
So that making it sloppy came after the 10 days, and my lesson there, which I've tweeted, is when people come to you saying, "Can you please make it sloppy or add this cute feature?" the answer should be no. And I should have known that because I think Niklaus Wirth, one of my heroes, said the essence of design is leaving things out. But during the 10 days, I also, like I said, I was in such a hurry, I left out garbage collection. It came back to haunt me, but I got reference counting in time that people weren't running out of memory right away on long-lived JavaScript.
Wait, what happens when you don't have garbage collection and you have objects?
Well, you just run out of memory. And,
I love it.
At first, you write a short script and the page doesn't last long or it doesn't do a lot, and it's okay.
Oh, I see. Yeah.
But if you're writing a game or something and you're doing event-based allocation, you run out of memory. And this was noticed in the summer of 1995, and people were like, "What's going on?" I better go back and do reference counting. And then the problem with reference counting is you're writing the language in the runtime in C, an unsafe language. And if you're reference counting and you overflow the counter, you mismanage it so it goes high, it gets stuck high, you leak memory again and you run out. If you underflow it, you free memory that's still in use. Mm-hmm. And even then, we knew what all the security hackers came to know, that you therefore have potentially a remote code execution vulnerability. Because this was before things like non-executable heap memory and stack defenses against taking over memory. So if you can, from the remote side, write some HTML and JavaScript that just happens to exploit a bug in memory safety, like it causes JavaScript to underflow a reference counter, and the script still has its hands on that object and it's trying to call a method on it, and there's some kind of lookup function table in the object, but you've managed to stuff the heap with strings that forge their own lookalike for the function table, you can call some other code. And this was a problem right away. So security, JavaScript upped the ante. Java had this problem too, but in its own VM, and it just was, a separate headache for Sun to worry about. We had this problem in Netscape right away. So Netscape 2 came out after my 10 days and after these, follow-on work to embed JavaScript better in the browser and to add garbage collection through reference counting. Really, I call it reference counting, and get it shipped. We had a bunch of dot releases where we fixed security bugs like maniacs.
But what is the thing when you sit back on a porch and just look out into the sunset, what are you most proud of from those 10 days?
I think the first class functions shines. I think especially since Java didn't have it and it was somewhat unusual.
So Scheme made it in somehow at the end of the day.
In spirit. Yeah. I mean, people complain because Scheme has minimalism. It has, 6 or 7 special forms. It has hygienic macros. It has call CC. It has sort of a beautiful, complete set of forms to make the Lambda calculus pleasant to use in practice. And JavaScript is, kind of multi-paradigm or shambolic.
Yeah. And today we have an incredibly fast language that, like you said, still... without hate, you can't have love. So I think there's both love and hate for this dance, this rich, complex dance of JavaScript throughout its history.
There's a dialectic for sure.
Today, JavaScript is the most popular language in the world. Why? By many measures. Why do you think that is? Is there some fundamental ideas that you've already spoke to a little bit, but sort of broader, that you think is the most popular language in the world?
So I think I did, by doing first class functions and taking the good parts of the C operator hierarchy and just keeping things simple enough. Maybe it could have been simpler, but I had to make it look like Java and interoperate with Java. That there was inherent goodness, Aristotelian quality there. And people perceive that even through all the quirks and warts. And then over time, working on it with the standards body, working on it not only as a core language, but in the context of HTML5, making the browser better, listening to developers, thinking about, this is something that Nick Thompson wrote nicely about on Hacker News. I was very flattered. He said, Java was this thing where the experts were writing the code and it was compiled and you had to declare all your types. And Sun didn't really give a damn about, the average programmer who wanted to build real web apps, dynamic things. And I was in there, meanwhile, doing, a bunch of people's jobs, making JavaScript survive those early years when it was kind of touch and go, right? JavaScript was considered a Mickey Mouse language. It was for annoyances like the scrolling text at the bottom of the browser and the status bar. But I kept listening to developers, working with them and trying to make it run in that single-threaded event loop in a useful way. And I think that forged something that people have come to love. Now, you don't always love, the best thing, right? I talked about Shakespeare sonnet about I Mistress Eyes Are Nothing Like the Sun, or the scene from Joss Whedon's film Serenity at the end, where the actual piece in the score by David Newman is called Love, where Captain Mal is teaching River Tam about how to pilot a ship, and she's a super genius, super soldier. She knows how to do it already. And he's basically talking about how you have to love the ship, because if you don't, it's going to kill you. And then a piece falls off the ship. It's kind of like JavaScript. You have to love it. You have to love it because now people say, we're stuck with it because it got this priority of place.
But there's love underpinning that, and actually the listening to developers. That's kind of beautiful. There's most successful products in this world, with all the messes, with all the flaws, perhaps the flaws themselves are actual features, but that's a whole nother, that's a discussion about love. But underneath it, there's something that just connects with people.
And it has to keep connecting. If JavaScript kind of went off in this, people sometimes complain about ES6. Oh, you put classes in JavaScript. I hate classes. You've ruined it. But it's not true. It's a dynamic language. Smalltalk had classes. Python has classes. There are lots of Lisp variants that had classy systems. Common Lisp. So, people who don't reject it based on some sort of fashion judgment do use it and do interact with the standards body. The standards body is competing browser vendors mainly, but also now big companies that use JavaScript heavily, the PayPals and the other such companies, Salesforce. And they have to cater to web developers. They have to hire developers who know JavaScript. They have to keep their engines up to the latest standard. And this creates all this sort of social structure around JavaScript that is unusual. I mean, you get C++ buffs that follow the inner workings of, C++, what is it now? 21 something. I don't know. I've lost track. But it's a more rarefied group. It's more like the old language, gray hairs. Whereas JavaScript is a younger and more, vibrant and large crowd.
There's a community feel to it. There's echoes. Perhaps I don't want to draw too many similarities. Maybe you can comment on it. There's C++ is like Wall Street, and JavaScript is like Wall Street bets from the recent events. It's like there's a chaotic community of all, and there's some power from that distributed crowd of people that ultimately
it's more demotic. It's more of the people. It lets people in without requiring these credentials. I remember in the late 90s into the noughties, people were all getting Java credentials. And I knew people, and friends knew people who became Java programmers, and you knew they really should have been like nature guides or pilots. They hated programming, but they thought, I got to make money. I'm going to become a Java programmer.
Do you have some, because it's such a monumental moment in our current history, as a quick aside, do you have thoughts about this huge distributed crowdsourced financial happenings with Wall Street bets? That's like nobody could have, you could have predicted, but the scale and the impact of this kind of emergent behavior from independent parties that could happen.
Like I said, my own experience with the dismal science, as with physics, led me to reject a lot of bad models. And, economics was always compromised by politics, political economy. You could also argue that it used to be a branch of moral philosophy, so it was concerned with the good, and it became divorced and became sort of in this quasi-Newtonian way, just about everything's just running by itself. Don't worry about it. This monopoly's crushing your Netscape company, but that's just nature.
And economics couldn't, or doesn't really have good models for the Wall Street bets subreddit.
They know how to squeeze a short, right? So, the amazing thing is you have Robinhood app, which was, again, supposedly for the demos, for the people, and eliminated the fee through various kinds of, straddles or some kind of spread operation that helped them eliminate the fee or eat the fee. And in fact, as a broker in these days, because it takes 2 days to settle, there's counterparty risk, as they found out. And so the Wall Street Bets people, the memes are like the Terminator robot with the $600 stimmy check, and the hedge funds, the anime little girl hiding under the desk. There's a problem, which I talked about in a recent podcast, which I'm conscious of from the history of the web, and that is, you could say it's monopoly, which antitrust wasn't enforced after US v. Microsoft for a long time. And a lot of this was due to the money interests buying control of politicians. And, in Plato's 5 regimes, that's oligarchy. That's where we are. And now we're seeing a fight against the oligarchs. I don't know if it'll work, but you're definitely seeing it. And it's also kind of hackerish, right? It's got a hacker ethos. Hey, Robinhood, no fees. Oh, interesting. Hey, I can buy a fraction of a share in this thing, or I can keep buying with my stimulus check. So I mentioned Hegel seeing Napoleon on the horse, right? Hegel also talked about the cunning of reason, that you have this sort of, God sees history in full. And if you believe in God, or, we don't know the future, but there's always this sort of fly in the ointment, this unintended consequence that confounds the best plans of the powers that be. And we're living through it. I'm glad it's not, street warfare or mechanized warfare, because it has been in the past. It's more like soft power.
Yes.
And people are fighting back.
Do you think it's possible? So the JavaScript used to be for the front end of the web. It's now increasingly so being used for back end, like running stuff that's like behind the scenes. And it's also starting to be used quite a bit for things like TensorFlow.js. So starting to actually use like these heavy duty applications that are using neural networks, machine learning, and so on in the browser. Is it possible in 10, 20, 30 years that basically most of the world runs on JavaScript?
This is a dystopia and a nightmare to some people. When we did Asm.js and WebAssembly, I would joke and meme people with scenes like Neo waking up in his pod in the Matrix, and he's all skinny and weak and hairless. And, you realize in the future that you're living in some simulation that it's all running on JavaScript, and you just scream forever. It's possible. Gary Bernhardt does these funny talks. He did Watt.js, and then he did this The Life and Death of JavaScript, I think it's called, where he took some clever ideas that actually have a thread of credibility to them. But I mentioned software fault isolation. In the old days, when we were using computers, we said we're going to use the Unix, monolithic monitor, and it's the privileged program. This is before you even had hardware rings of protection. Some of the early '60s operating systems used hardware protection zones, but Unix is privileged, and the program that runs user code in a process is hosted. It's the guest in the host, and you get to suspend it, you get to kill it. If it crashes, it doesn't take down the whole OS. It's a wonderful idea. But the call into the kernel is expensive, the system call, so-called. And this has even been optimized now for things like getting the time of day, so it doesn't actually enter the kernel. And meanwhile, hardware architectures and virtualization techniques have gone in a different direction, even to the point where you can do software fault isolation very cheaply without entering the operating system kernel. And so you get unikernels and exokernels and very lightweight VMs. And so Gary took this idea and said, JavaScript will take over computing because the system call boundary is too expensive. So everything ends up in JavaScript with these lighter weight isolation enforcement mechanisms. It's not totally beyond belief.
Yeah.
It'd be WebAssembly too.
Was the standardization process beautiful or painful that those early days, you as the designer of the language?
It was painful because it was rushed. Now, Guy Steele was contributed by Sun. So even more than Sean, you had this giant brain, Guy Steele, helping, bringing some of that scheme magic. And he even brought Richard Gabriel for fun. And Richard wrote the fourth clause of the ECMA standard, which was kind of an intro to what JavaScript's all about. So we had some really good people. And we didn't fight too much. There was some tension where I was fixing bugs and I was late to a meeting, and Sean Katzenberger of Microsoft was actually mad. Like, where is he? We need him. And when I got there, I saw that only he saw this sort of off by one bug somewhere in the spec. And then I saw it too. And I said, there's a fence post bug there. And then we kind of locked eyes and we realized we were on the same page, and he wasn't mad anymore.
What were the features that are being like struggled over and debated and thought about? And
it was mainly writing down what worked and what we thought should work in the edge cases that didn't interoperate or that seemed wrong. But we were already laying the groundwork for the future editions that I was already implementing. I was still trying to lead the standard by using the dominant market power to write the code that actually shipped. So the de facto standard would lead the de jure standard, and I was putting in the missing function forms that I didn't have time for in the 10 days.
So this is the engineering mindset versus the theoretician. So you didn't want to create the perfect language, but one that was the popular and shipped and all that kind of stuff.
And you could say I was standing on the shoulders of giants, so there was a staged process where I had to hold back things that were well designed by others in other languages and I could imitate, but I couldn't do them all in the 10 days. So they came in 1996 and 97, and they came into the third edition of the standard, which was finalized in 1999. But at that point, Netscape had been sold to AOL which was a decent exit considering, and had previously been mercilessly crushed. Netscape was selling the browser along with server software that it had acquired after its IPO, and Microsoft was just underpricing it. So there was no way to compete with that. Microsoft was also, making Internet Explorer the default browser in Windows, which is called tying in antitrust law. And they were doing even more brutal things. There's a famous investor. He did very well on Google, so he's a billionaire, Ram Shriram, and he was sales guy or head of sales at Netscape. And he got off the phone looking ashen-faced after Compaq called and said, Microsoft just told us they're going to pull our Windows license if we ship Netscape as the default browser.
Wow. So there's some bullying going on.
It was totally material in the antitrust case. But JavaScript escaped into the standard setting where there was fairly good cooperation. Microsoft had a really good guy on it, and Guy Steele was there for a time, and there was some good work. But after the antitrust case and Netscape kind of dissolving into AOL and not really going anywhere quickly, Mozilla took years to really bring up. The standard froze. And by 2003, even though they've been sort of noodling around with advanced versions, JavaScript 2, I'd given the keys to the kingdom to another MIT grad, Waldemar Horwath. Very big brain, still at Google, I think. He won the Putnam in 86. So he's, very mathematical.
Legit.
He designed this successor language, JavaScript 2, but it only showed up in mutated form in Microsoft's ASP.NET server side, and it didn't last there. And it showed up in Flash, and that's what became ActionScript 3. With changes.
ActionScript, interesting. And then Flash, of course, declined. And so, how did we arrive at ES6, where it's like there's so many, where everyone there's this history of JavaScript that it was just like cool when you're like having beers to talk crap about JavaScript. Everyone loves to hate, like people who are married say, marriage sucks, is they just want to let off some steam, even though everyone uses the language.
Yeah.
But ES6, it's become this like, reputable, like it fixed major pain points, I think.
It added things to the language and added something that was already in ES5 strict mode, but made it implicit in class bodies and module bodies. It was a big jump, but it accumulated some of the ES4 designs that we'd done with Adobe for what we hoped would be the fourth edition of ECMAScript that were supposed to fold in some of these old JavaScript 2 ideas that had come into ActionScript 3. So you look at the family tree and you see these forks, and the main ones are the ones that go into Adobe Flash, acquired from Macromedia, and the one that went into the server side of Microsoft's stack, which kind of died. And then trying to bring them back into the standard and not quite succeeding. ES4 was mothballed, but all the good parts that everyone liked made it into ES6. And so that was a success. And I said earlier I had the wrong year. I think it's 2015, so it's off by...
For ES6?
Yeah, it was finalized in 2015. It took a little longer than we hoped, but... because ES5 was 2009, and that was a smaller increment from ES3. We skipped 4 again. We mothballed it. And we had a split in the committee where some people said, ES4 is too big. We're going to work on incremental improvements. No new syntax in particular, they promised. Not quite true, but they added a bunch of interesting APIs. Alan Weir-Sprock, my co-author of that Hobble paper, and he was at Microsoft at the time. I ended up hiring him at Mozilla. He wanted to get to Mozilla and keep doing the sort of editor job of the JavaScript standard, ECMAScript. And when we got ES6 done, it was a little late, 2015, and we switched to year numbers. So people still call it ES6. I call it ES6.
Yeah.
But if you remember, off by 9 plus 2000.
When did you first fall in love with programming?
I didn't program a lot when I was in high school, but I had a friend who had a Commodore PET. And after we saw Star Wars, he said, hey, let's make a basic program that does the Death Star trench run. And it was just, simple 2D graphics. And I didn't know what I was doing, so I just helped him out on the math and stuff like that. I was a math and science kid. I was really into the HP calculators of the early mid-'70s. These were the RPN. They were really strongly built. And as Arik Goldfinger said of gold, divinely heavy. There's probably some gold in them too, gold metallization. But they were awesome calculators, and they had all the scientific functions, so I was really into that. So I aimed toward physics. I was a little late for the 20th century golden age, and I read a lot of science fiction. So I was like, yeah, it's on to hyperdrives and warp drives, and physics was not going to get there quickly. And I started hacking on computers while I was studying physics as an undergraduate at Santa Clara University. And I dodged the Fortran bullet because I was in the science department instead of the engineering department, where they still did Fortran and card decks. I think they had an autocollator. But we were using Pascal, and I got one of the first portable C compilers ports to the DEC mini computers we were using. And I fell in love with programming just based on, procedural abstraction, Pascal, just what now would be considered old school, like structured programming from the 70s. Niklaus Wirth, the creator of Pascal, was a good writer and a good pedagogue, right? He always at ETH would do these courses where it's like build your own computer, build your own compiler, build your own operating system.
From scratch.
Yeah, kind of. And I know some people who are grad students under him and said he would torture the students with things like this custom email system that had 25 word limit and things like that.
I unfortunately dodged both the Pascal and the Fortran bullets. Could you maybe linger on the Pascal? Like, what kind of programming language was it? What is it reminiscent of today? Because it sounds like it may have had an impact on your own trajectory.
Yeah, it was in the Algol family, and Algol was, the big successful language design and compiler project in the 60s. It had a successor called Algol 68, which was ambitious but not as successful. But Pascal was kind of a wordy procedures and functions language. It distinguished between functions which return a value and procedures which don't, which just compute. And you could say that whole Algol family went into Ada. Pascal had a second life thanks to Borland with Turbo Pascal, which was hugely successful. I think in large part due to Anders Hellsberg, who then went to Microsoft and did C# and .NET with his team there, and has done really well doing type JavaScript. So yeah, there's a lineage here, but I was also interested in C and Unix by the time I was an undergrad, because people were bringing Unix up on all sorts of hardware. I had some friends who were doing their own wire wrap computers, 6820 maybe, and I was wire wrapping for my engineering course, 6809 or something simpler, building a computer on a board. And I wanted to build a more ambitious one and port Unix to it, but I picked the wrong processor. I picked the National Semiconductor NS16032, which was this amazing, CISC, complex instruction set computer, and not the reduced instruction set computers that were just being contemplated into the mid 80s.
And RISC ultimately won out.
RISC won in some ways. It dissolved into, you have both. Now you have these superscalar architectures where, like, Intel has kept probably too much backward compatibility at the instruction level, but that's just there's a front end that parses that into these, these wide internal instructions. So, the very long instruction word research that was also interesting at the time kind of became the microarchitecture inside the backward compatible Intel. But I picked a National Semi chip, and it never got made successfully. It was full of bugs, and I never could have brought it up. But I went on out of physics after 3 years into math computer science. And like I said, I did it because I saw I was being sort of childlike and naive about physics, and I thought, meanwhile, the Valley is go-go for computers. The Apple II, right? The PC, the Intel 8080 86, 8088 based PC, the IBM, gave Microsoft the future for in a somewhat fishy deal.
So speaking of things that didn't follow a perfect theory and model, JavaScript. So there's two things. One, it had an impact on the world at a huge scale, obviously. And it's also still is one of probably the most popular programming language in the world. So can we go back to the origin story? Can you tell the story of how JavaScript was created?
Yeah, I was at Silicon Graphics after graduate school for 7 years. And it got to be big and successful and divisionalized and political. And I thought kind of boring. And a friend who'd been there went to one of the last of the super companies, the super startups in the early 90s. There were several. I suppose General Magic was a little after that or around the same time. But MicroUnity was that company that I went to. And it was because my friend Jeff Weinstein had gone there from Silicon Graphics. He recruited me. And MicroUnity was doing everything. So this was like the ultimate sort of pretend grad school. It was doing a new fab, new semiconductor process. It was doing new analog and digital circuits on the same very large but not wafer scale chip. Originally, it was 5 centimeters on a side. It was really hot too, so it needed a water cooler. It was a Cray killer, and then they shrunk it and they tried to do a home sort of media processor that was essentially a barrel processor, but you could think of trying to do all the things that we now see in modern architectures with short vector instructions and sort of wide instructions or multiple issue, and doing a lot of the stuff in software, because the second iteration, the set-top box, was really for avoiding the cost to the cable company of rolling the trucks out to replace your garbage General Atlantic set-top box with a slightly newer, less garbagey one. So if you could have software upgradable set-top boxes, the cable companies thought they could save a lot of money and add features.
Is this assembly? Or which level of the software?
It was like we were writing we were using GCC, we were writing C++ and C. Somebody I worked with there, really very smart guy, hired from a sort of Wall Street hotshot programming consultancy, did his own hardware design as well as software. And we were working on how to make not only short vector units, but general bit shufflers and permuters. So you could do things like, crypto algorithms efficiently, and you could do demodulation of the cable, complex quadrature amplitude modulated signal. So you were basically taking A to D converters, dumping things in buffers, and then doing the rest in software. All the framing and the Reed-Solomon and Viterbi and all that error correction. So that was really great learning experience, but it was not going to work. It was doing too many risky things at once, right? As Jim Clark said to me when I hopped to Netscape after 3 years at MicroUnity, he said, "Oh yeah, you do 10 things each, 1 in 10 odds. It's going to be 1 in 10 billion, right?" The multiplication principle. So, Netscape was already a rocket, and I'd passed the chance to go there in 1994. I knew the founders because I worked at SGI, Clark's company.
Could you pause for a second? In Netscape, when was the launch of this rocket?
94.
94 was the launch of Netscape?
And I went there in early 95 in April.
Okay. But so you said you missed the launch.
Well, I missed the first floor employment opportunity, but the IPO was August 1995. So I was there for that.
How obvious was it that Netscape was like world changing? What was the layout? Was Netscape one of the first big browsers?
Yes. So when I was at MicroUnity still in 93, we saw a browser called Mosaic. And up till then, we'd used email and we'd used Usenet, the NNTP protocol. We'd used newsreaders. We used FTP. We used all these old internet protocols, all relying on the DNS and TCP/IP and UDP for that matter. When I was at Silicon Graphics, we brought up the whole stack, right? We had to, discover how to find the Ethernet addresses on your network and then find IP addresses for them, ARP protocol, all that stuff. And it was great because nobody knew in the 80s what was going to win. All the proprietary stacks like IBM, SNA, and DECnet, and all these other protocols were saying we're going to do it, or it's going to be heterogeneous future. And instead, it was Berkeley Unix and the TCP/IP stack that dated back to the ARPANET that won. And I think we knew it. We all knew it at SGI, but the salespeople didn't, and so they kept trying to get multiple network stacks interoperating. But in the end, it won, and so that was the internet, and it was email and texty, and it was Usenet, very texty. And then Tim Berners-Lee did his thing, but I don't think I was paying attention. And I think the date when he first did it, or when he wrote the famous email, has been pushed back to 89. But I noticed Mosaic in 93 because one of the things that Mark Andreessen and Eric Bina did at NCSA was they innovated on the early HTML standard. They, in particular, Mark sent this email saying, "Hey, everybody, we think you should be able to put an image in a page." And when he sent that, Eric Bina had already written the code. And I talked to Tim Berners-Lee more recently, just a few years ago, and he was like, "Oh, we had another way of doing it." And it didn't work out because Mark shipped his in Mosaic. And this convinced me of several things. One, the internet meant there was a huge first mover advantage, and being fast, getting on first mattered a lot. And so, Richard Gabriel of Scheme and Poetry fame has written about this, the famous essay.
What's poetry?
He's a poet.
Richard's actual poetry.
Yeah,
I thought you talking about some kind of something.
No. I mean, he's the founder of Lucid, which is where Jamie Zawinski worked before Netscape. And Lucid was doing, compilers, and Lucid Emacs, which was a fork of Emacs. Famously, Jamie fighting against Richard Stallman, Stallmax. And so Richard Gabriel, very, very brainy computer guy, but also a poet. But he wrote a nice essay that gets abused all the time. In fact, Jamie's put a kind of warning in front of his version of it on his site, jwc.org, called Worse is Better. And this is about survival advantage of software in the networked world, in my opinion. It's about Unix. It started out being framed as Unix and Lisp, good news, bad news, because all the Lisp people, the MIT people were like, this is the crown jewel, right? Scheme, this Fabergé egg, or Common Lisp, this giant cathedral. Of course we're going to win. This is civilization. And those, those farmers in New Jersey, to borrow from The Sopranos, those hicks down at Bell Labs, they're just, there's nothing sound there. It's all hacking. Yeah. Well, guess what won?
Wow. So you're saying this is a fundamental principle of the internet is moving fast wins.
You could say in almost any network system, like in biological evolution, you see successful alleles sweep populations, and they don't always have, they aren't free of flaws. They heterozygous advantage, right? You can get both parents give you the gene variant, and you get sickle cell anemia, right? But if one of them does, you're more resistant to malaria. And so this isn't a beautiful process, except at large scale. And then you realize that because it moves fast and can adapt, it can win. And people still struggle with this. I used to struggle with this because JavaScript was done in such a hurry, and the force of web compatibility meant early mistakes couldn't be fixed. And even the standards process injected new mistakes, as it will. But often standards bodies go back and make incompatible changes. You can't do that with the web. It's more like biology. You preserve what still works. You don't want to break ATP metabolism or whatever. So you have to kind of resign yourself to the reality of worse is better being enshrined in actual design points you might not like. And that happened with JavaScript. And I'm way over it, but it also, I think, was a huge advantage. That's why JavaScript has kind of swept a lot of programming domains. People will say, "Oh, it's not because of merit." Well, you're right, but we also improved it over time in the standards body. I spent 20 years doing that. And you don't get that choice. It's like, I'm not saying that was the best language. I'm just saying that was the right time to do it. And I like to say the alternative was not to do it. I could have told Netscape, "I can't do this. It's too rushed." And it would have been Visual Basic script, and it would have been bad.
So that's a good way to present the alternative. But so it was a Netscape, and you have written it in how many days, and why was it only that many days, and what was the goal and the underlying principles in your mind at the time?
So the whole I'm sort of describing worse is better in a frenetic way because it fit the model of Netscape. When it was known that Jim Clark and Mark Andreessen were founding Netscape, and they did the first release in 1994. That browser took over from Mosaic. In fact, that's why Mozilla is called that. It's the Mosaic killer. It's like the giant monster that kills Mosaic.
That's awesome.
And they knew they could, it wasn't that, again, it's not like you're doing advanced scientific research that is changing the world. You're more like taking down the last iteration on the browser Mark did, which had images and, other affordances before he stopped working on it. And you're making Netscape the new thing that has images, plugins, which was the way to do video back in the day. It had something that's kind of died now for tiled windows called frames and frame sets.
Mm-hmm.
It had
yeah.
HTML tables. That was new. Eric Bina did tables in Netscape 1.1. So when I got there, they were heading toward IPO. Clark wanted to IPO early. I think his instinct was right. And that kicked off the whole dot-com era, right? There was a recession in the US in 91. You can see old Law and Order reruns where they talk about the recession, how hard it's hitting New Yorkers. And after that, Greenspan really goosed things at the Federal Reserve, and technology had been sort of fermenting in a way that came together with the internet. And Netscape made it, possible to do pets.com, to do eBay, to get people to recognize a URL on a billboard and then type it in when they get home. And that was huge. That was so fast moving a rocket that Mark and the engineering team there thought we need to make this a programmable browser, not just a document viewer, not just a video.
So it was all HTML with images and tables, and also, like you said, frames. And
Early
so
plugins.
There's no dynamic element at all.
Yeah, the most dynamism you get was from a plugin, which there were a few of them then. Flash didn't exist at that point. It was, I think...
Java applets yet, or no?
Well, that's the thing. We did the deal with Sun. In fact, I was recruited to go do Scheme in the browser. Remember Guy Steele and Gerald Sussman's beautiful Lisp variant. I was going to do it in the browser because my friends from SGI thought, hey, we like Scheme, you like Scheme. And I'm like, I hardly ever use Scheme. It's not really used in industry except in sort of silos. But I like it. Okay, I'll come do Scheme in the browser. I have a slide from my 2017 talk where I have Bruce Willis crawling through the duct in Die Hard. He's like, come out to the coast, have a lot of fun. Come on, do Scheme in the browser. But when I got there was no Scheme in the browser because they'd started a deal with Sun Microsystems. And my best contact there was Bill Joy, who I admired as a Berkeley Unix founder and Sun founder. And Bill got the idea of making the browser programmable too. And so the main idea was to put the Java VM, which at that point was not really easy to embed, into Netscape, including the Netscape version on Windows that was still most popular, which was the 16-bit Windows 3.1, which was going away. Microsoft was coming out with Windows 95, and everyone was afraid they were going to do, Internet Explorer, I guess, 2 at that point, 3 the next year. They already bought or invested in somehow Spyglass, this other company that shot out from NCSA at University of Illinois. And in fact, Microsoft had tried to buy Netscape in late 94 before I got there. And I heard about this later. I heard they offered way too little money. And so, Jim Barksdale and Jim Clark said, get out of here, pound sand. But then they realized, oh, this is going to hurt us because now they're going to copy us. It didn't happen right away. I'm not sure when Gates' Internet tidal wave memo was written. That's the famous memo he wrote when Bill Gates realized that Microsoft was going down this old copy AOL path or copy CompuServe path, a project called Blackbird, presumably after the SR-71, I don't know. But they were going to make a dial-up service with a custom content language stack and custom rendering. It wasn't the web. They could have content partners. They have a lot of money. But it still wasn't to scale the web. It wasn't going to be compelling. And Gates realized this, and he turned the company on a dime, and they couldn't buy Netscape. Again, I'm not sure of the timing, so they decided to copy it. And once we realized that, everybody inside Netscape felt even more urgency and more of a frenetic mood. And so my chance to do Scheme disappeared when the Java deal started brewing. But there was still a chance to do a companion language to Java because Java is a compiled language. It's evolved and improved quite a lot since then too, but it was for sort of serious advanced programmers that cost a certain salary or hourly rate. And people observed, Bill Joy observed, and Mark Andreessen and I observed that in a mature stack like Microsoft, you really benefit from having a scripting language like Visual Basic, which became Visual Basic Script in IE3, but didn't take over and kill JavaScript, that you need 2 languages. One is for the component writers who are higher price and more expert, and the other is for scripters, certified public accountants, designers, graphic designers with some programming inclination, anybody, amateurs, doesn't matter. There's a much more demotic approach there for programming the components together, gluing them together. Some people say duct tape language, which I don't really like. But we saw, Bill Joy and Mark Andreessen and I, we saw the need for a companion language. And the gleam in our eye was to call it JavaScript, though I didn't like it. That was marketing's plan. Mark called it Mocha, which I liked. And Netscape marketing, I think, didn't like that. So they said, oh, there's some trademark in some software somewhere that uses Mocha, so we can't use that. And they tried LiveScript in August, and that didn't last. And then finally, we got the trademark license in December 1995. But the work I did to prove that it could be done was important because I came in April, and even then Netscape was growing so fast that they couldn't find an open hiring requisition in the client team for me. So they hired me into the server team. And I worked for a month on the server team on what became HTTP 1.1. So I had done protocol work at Silicon Graphics with Greg Chesson, former Bell Labs grad student intern who knew all the Unix founders. And Greg was very interested in taking protocols to the next level with VLSI because he thought that CPUs wouldn't scale up. He was mistaken in that, unfortunately. Moore's law more than kept up, and you have gigabit Ethernet running with conventional processors. But I worked on protocols at SGI as well as Unix kernel hacking and NFS and things like that. So I came into Netscape to work on the server side for a month. But I was thinking the whole time, what should this language be like? Should it be easy to use? Might its syntax even be more like natural language, like Hyper Talk, which is Bill Atkinson's language in HyperCard, if you have ever used HyperCard on an early Mac. And I thought, well, I'd like to do that, but my management is saying, make it look like Java, which looks like C from a distance.
What does that mean? Is it braces? We're talking about visually? Does it mean like what management? Do they understand what
they don't? Marketing didn't know, but management did. Like Rick Shell, the VP of engineering, knew. And we had a plan even that was, if you have this companion language, you're going to glue things together between Java and JavaScript. So you're going to have commerce in memory in the heap with data types. So you're going to want some of the data types in Java to reflect in the JavaScript. You're going to want the primitive types that Java unfortunately separated from objects. So at least some of them double, let's call it in Java's terms, from the C term for double precision, floating point, or strings or Booleans, and objects. And so right away, there was this constraint that looking like Java meant kind of the C curly brace syntax, but also some of the data types and objects.
Like objects and so on, all that kind of stuff.
Dotted call,
comparison operator, all
garbage
that
collection, all that stuff.
Collection,
Even the bitwise operators and the shift operators, including the unsigned right shift, which Java had because it didn't have unsigned integer types. It said if you want to do unsigned operations, use an operator. And that turned out to be important much later. I'll tell that story if I have time. But JavaScript inherited a set of operators, the expression grammar, the statement grammar up to a point from Java. But I wanted a functional language. I wanted scheme, a little bit of scheme, even though it wasn't as clean as scheme.
So you had a love, sorry to interrupt, you had a love for scheme and Lisp, that functional language landscape.
Yes, I wanted first-class functions because I saw the need for callbacks in the browser where it's a single-threaded program.
Wow.
All the early browsers were single-threaded, and it's the right model for users. Most users weren't ready for mutual exclusion and threading. So in a single-threaded world, you cannot block the user interface. So you have to use a callback and run later. And without getting too fancy and trying to capture the continuation like call CC does in Scheme, I thought, I'll just make it easy to have fun args, first-class functions you pass downward and they can be called back. And Java didn't have that at the time. It took forever to get proper first-class functions, lambdas now into Java 7 or 8, I think.
It did have concurrency, right? From the very beginning. But you were thinking that the JavaScript in the browser would not have the luxury of being concurrent.
That's right. And the reason was Java was going to run into plugins, so it could fork threads and go to town. But the main action in the browser was in a single-threaded program, a single Unix process on Unix or Windows. And it was where you had to service the event loop and then go, do things, respond to the network, lay out some HTML, render it, turn, widths into heights by filling containers, boxes, what became the CSS box model, and run scripts to, make the thing livelier, respond to user input. And all that event-driven programming was in part like HyperCard because HyperCard had this on event name syntax. Mm-hmm. And so that's why you have in JavaScript on-click run together as the name of the event handler. And there's some funny ones, on mouse over and on mouse out. People still complain about those. But, there are many more events now over the years standardized. But it was a mix of event-driven single-threaded programming because it had to run in the main thread of the browser where the action is. And Java never got there, which meant Java could not interact easily or quickly or in a nested way with the document, with the objects reflected from the HTML document, with the tables and forms and so on. And that is one of the reasons I think JavaScript survived and Java kind of died. Java was in this plugin prison. It essentially was confined to a rectangle, the applet rectangle. And while we even built next year, Nick Thompson friend from SGI who was an intern grad student at CMU at the time, built the first version of Live Connect to glue Java and JavaScript together to deliver on that vision where you do have commerce between the data types in the heap.
Did it work?
It worked, but Java was in charge. JavaScript was in charge, and Java was just these components, these helper objects.
You might as well do everything in JavaScript.
And what happened over time? It's like an evolutionary filter. It just kind of, who needs the plugin? And in fact, Sun mismanaged Java as a plugin. They thought, oh, Netscape was giving us the distribution vehicle, and we don't care about the browser. It's just about getting Java out there. And that was a big miscalculation. They then tried, because Microsoft was killing Netscape after a few years, they tried getting into Microsoft. And you may remember there was a Sun Microsoft deal, which famously blew up. And Microsoft kicked Java out of Windows. And that's when they really pulled the trigger. I think they'd already evaluated it and liked it on Anders Hellsberg's .NET and C#, and decided we're going to just not have Java. We don't want any of that Sun stuff. We don't want the patent risk. We don't want... I'm not sure what the fights were about. There was some patent angle to it, I think. And up till then, Microsoft had been using Java components, like in Outlook Web Access, which had a lot of JavaScript to be a webmail-like, Hotmail-like user interface. They had to call the mail server through HTTP, and they used a Java object to do this. And when they gave the boot to Sun, they suddenly the left hand gave the boot and the right hand said, we better do something else in Outlook Web Access. What are we going to do? And they said, let's just add an ActiveX component, which is their own native way of embedding things in languages. And we'll make it, it'll be what became XML HTTP request, which is now a web standard for calling asynchronously. And it's been replaced by the fetch API in HTML5 or HTML living document. But this whole lineage goes back to Java being successfully the loser and getting kicked out. And after Microsoft kicked it out, it was a plugin, and you would find it required for like smart card banking in the Nordic countries, where that was mandated by law, but really didn't get used much. Or, there were pilots who used it for flight information. But Flash, which Netscape could have bought, but fortunately didn't.
Fortunately didn't.
Yeah, we would have screwed it up. I mean,
what year are we talking about with Flash?
I think after the IPO, so it was probably late '95. And
Flash was around. Was it Adobe? No, it wasn't.
No, it was called Future Splash, and it was these brothers, Jonathan Gay, I think his name was. And he came knocking, and the marketing guy at Netscape, who was screening the technology partners or wannabe acquisitions, was brutal, and just everybody wanted to get in on the Netscape, stock gravy train, and he sent them packing, and they ended up selling to Macromedia, and Macromedia was where Flash was created. And the good thing about Macromedia was it was a tool company, so it invested in the best ideas, I think, which are still somewhat lost to us of Flash. The timeline. Animation has sort of been a mutable function over time.
They had the tooling around that too, like that Dreamweaver. There's a Flash
Director. There were a bunch of them.
Yeah, I mean, yeah, that was a
Flash Builder was one of the last ones. These tools were used by real artists and special effects people and designers. All the restaurant websites around 2005 were done in Flash, which was, we were trying to do HTML5 at the same time. That was the Firefox era. We were trying to make the web capable enough you didn't need Flash. But if you recall, you go to a restaurant, it's like, this is kind of like a game or something. It's like a Flash. All the font looks small. And
so you didn't like Flash from the beginning. You're like, this doesn't feel right.
Not really. I actually admire Flash's technology, and I'm pretty pragmatic about these things. And I realized that, it doesn't matter if you're dealt a bad hand, like JavaScript was a rush job, or if you have Flash as a plugin and you can invest in the tools and make it pretty good. You should make it better for your users and grow it as best you can. And what happened with the browser due to Microsoft's monopoly abuse, for which they were convicted, and even after that, until I think Firefox and then Chrome, was people kept saying, "Oh, the web can't do X, it can't do Y. Yeah. We'll have to have a plugin. We'll have to have a new approach. We'll clean the slate and have a new web." And everyone who said that failed. And the reason they failed is because there's too much value in the web, this huge network. And the worse is better principle means that you can not only start bad, which they all sneer at, but get on first and get wide distribution, get sort of an evolutionary advantage in the priority of place, but you can also improve it over time.
Yes.
And so if you're going to improve Flash, and for some reason Flash is now out of favor, Steve Jobs said you can't have Flash on the iPhone. That was probably the death knell. Put your energy into JavaScript. And that happened, right? So we did things at Mozilla with Adobe to improve, which bought Macromedia, to improve Flash and to improve the version of JavaScript that was in Flash. We tried to standardize that.
Oh, that's right.
I'm getting ahead of myself.
You
That
can
was
program
ES4.
Flash.
Yeah,
That's right.
AS3.
Right. Can we just rewind to the magical, so how is, if you can do sort of a big sweeping progress of JavaScript, how has JavaScript changed over the years in your view from those early 10 days with a quick addition of garbage collection and fixes around security? How has this evolution that now it's taken over the world?
It's been a bumpy ride because the standards body got shut down after Microsoft, I think, took over the web and then felt punished by the US v. Microsoft antitrust case.
Can you speak to the standard body?
That was a fun ride too, because Netscape had taken the lead with the web and HTML innovations like frames and frame sets, tables. And the W3C was sort of off even then, sort of in SGML land, heading toward XML la land. I'm going to be a little harsh on it.
What's HTML? I'm sorry.
SGML was the precursor markup language to HTML, or it was sort of the more extensible standard generalized markup language. It was a
XML like
pointy brackets, but it had all sorts of elaborate syntax for doing different semantics. And this is why I think TBL and others who wanted to do the semantic web then took XML forward. But they had this, or some of them anyway, had this strange idea they could replace the web with XML, or that they would upgrade the web to be XML. And it couldn't be done. Worse is better had concrete meaning. The web was very forgiving of HTML, including sort of minor syntax errors that could be error corrected. Like error correction isn't generally done in programming languages because
that's another amazing thing about HTML is like it's more like biology than programming.
Yeah, exactly. and so XML was in its standard form super strict and could never have admitted, the kind of users who were committing these errors. And the funniest part was Microsoft said, "Hey, we're doing XML," but the way they put it in Internet Explorer under the default media type put it through the HTML error corrector.
Oh, wow.
So they kind of bastardized it to make it popular and usable and accessible. And so XML as a pure, thing was never going to take over. And the W3C was kind of not fully functional because Netscape wasn't cooperating with them. We thought about where to take JavaScript, and we realized, our standards guru, Carl Cargill, realized there was a European standards body that had already given Microsoft fits by standardizing parts of the Windows 3.1 API, which European governments insisted on. They said, Microsoft, we can't use your operating system without some standards. And Microsoft said, here's our docs. And the government said, no, we need a European standard. So this body called the European Computer Manufacturers Association, ECMA, which eventually became global and became a proper noun instead of an acronym.
Right. It's just one capital E now with a lowercase CMA.
Right. And as one of the early Microsoft guys I met when we first convened a working group to talk about JavaScript said, it sounds like a skin disease.
But it gave, maybe you'll speak to that, but it gave the name to JavaScript of ECMAScript.
That was the standard name because Java was a trademark of Sun's. They were so aggressive, they were sending cease and desist letters to people whose Middle European heritage meant their surname was Javanko, and they called their website javanko.com, and Sun would send them a letter saying, you're using JAVA at the start of your domain name, you must cease and desist.
I love marketing more than anything else in this world. So ECMAScript, and now is popularly named as ES plus version.
I would say people use JS more than anything. People still say JavaScript. JavaScript is in all the books.
So, when you're referring to, it's usually JavaScript, and when you want to refer to a version of JavaScript, you'll say ES6, ES5.
Yes, or now they've gone to years, which is kind of confusing because it's an offset of 2009. ES6 is ES 2016.
It doesn't match the years perfectly. So what were the choices made, and how did JavaScript evolve here?
So we took this new standards body, which had, we thought, sort of a proven record of standing up to Microsoft. But Microsoft sent a lot of people. They sent some people who were pretty good, and then when they realized that I was there and Netscape was not going to, just bend over and do whatever they wanted, they sent somebody really good. And he was a smart guy. He did a lot of the work on the first draft of the spec. Sean Katzenberger, he's left Microsoft. He even did what I sort of did. He told his bosses, stop bugging me to do other things. I'm focused on this, because it took a lot of focused work to create the first draft of the spec. And I was spinning almost all the plates. I had like part-time help in certain areas. And on the front end integrations, I had the front end guys. But I couldn't take as much time as Sean was to write the draft spec, but I had to participate because I was essentially helping write down what the language did. And in areas where we didn't like what it did and Microsoft didn't agree, we sometimes got away with slight changes. And that's the story of standards. You have different implementations, and depending on their market power, they interoperate where you have agreement, and where they don't, the dominant one usually sets the de facto standard. And then you should probably reflect that into the de jure standard. And this happened with JavaScript. Over time, as Netscape went down and Microsoft went up, we did the first edition of the standard, codified in 1997 in France. We had a trip to Nice, which was very memorable.
For any interesting reason, or just because it's Nice?
And ECMA's European, and IBM and others were, there. Mike Cowlishaw, an IBM fellow, was a Britisher. And the guy who ran ECMA at the time, Jan van den Belt, was quite a raconteur and a very fun guy. And he had us out for, the great, Fruit de Mer, the Bouillabaisse time. And we at Mozilla realized this, and we saw JavaScript was something that you could compile to. Adobe had somebody in the Adobe Labs doing this too. He had a project called Alchemy. We had somebody who's now at Google, Alon Zakai, who did his own LLVM-based compiler that would take C or C++ and it would emit JavaScript. And you would think, this is crazy. You're going from this sort of machine types, low-level, controlled memory allocation language to this garbage collected, dynamically typed, higher level language. But Alone sort of just phenomenologically carved nature of the joint and found the forms that were fast in JavaScript. And then with Dave Herman, who I'd recruited from Northeastern University, who was a type theorist, and Luke Wagner, who's still at Mozilla, who was the compiler guy and the JIT guy, they figured out how to codify what Alone had done into a typed subset of JavaScript called ASM.js. And this is a strange thing to think about because it doesn't have new syntax. The types are casts that occur in dominator positions in the control flow graph. So it's like a hack on JavaScript, and it's a subset, and it uses those bitwise operators that I talked about copying from Java to basically cast numeric types, which are double precision floating point, into integers. And so inside JavaScript, in the kernel semantics, are integers. And if you use these operators, if a compiler emits them in the right places, you can then treat them as typed values, typed memory locations, and you can type check your program. You can not only type check it, you can compile it, and this is all in sort of linear time, and you can compile it to have deterministic performance. It doesn't touch the garbage collector. It calls a bunch of functions that come from the C functions or C++ code that you're compiling, and you can make the epic Unreal Engine go in 30 frames a second.
Yeah.
And when we did this in 2013 in the fall, Tim Sweeney, I met, didn't think it could be done quickly, thought it would take years. And the team went to Raleigh to Epic, and in 4 days they had Unreal Engine ported by pressing a compile button. Right? They had to, but they had to have WebGL, which came from OpenGL ES, which came to OpenGL, which came from Silicon Graphics GL. They had to have Web Audio, so they could map OpenAL, which was another audio library standard, to Web Audio, which was kind of a Chrome idiosyncratic thing. But they could make it work. And they had to have ASM.js for fast C++ to JavaScript. And if you didn't have that fast compiler step, the JavaScript you'd write by hand trying to do an Unreal game would be too big and too slow. It would touch the garbage collector. It would not keep up with 30 frames a second on the hardware, 2013 hardware. So we demoed that at this must have been fall 2012 now that I think about it, because we demoed it at GDC, Game Developer Conference 2013, and people were stunned. It's like Unreal Engine, Unreal Tournament running in my browser window, no plugin, no Flash, no Java, no.
So were those the early days of, because JavaScript now is able to run basically on par with a lot of the like C++.
Yeah. And even before then, you had the fast JavaScript VMs in 2008 when Chrome came out. Just before it came out, Mozilla, my friend Andreas Gall and I and others hacked out Trace Monkey, our trace-based JIT, the Squirrel Fish Extreme team at Apple did their JIT, and we were all competing on these crazy performance benchmarks. It was a little bit too much tuning to the benchmark, but JavaScript started getting fast and developers started noticing it, but it was still kind of its own high-level language with garbage collection. The ASM.js step helped us go further because until we really proved the concept, people were still saying, well, JavaScript's okay. It's getting faster thanks to V8. Everybody gave Google credit, especially Google. But we need something to kill Flash. Let's use the portable native client code that Google had acquired, native client, which is a separate lineage for taking basically C code, compiling it into a software fault isolated container of some sort using some kind of virtualization technique. And maybe it can even be in process and still be memory safe. That would be awesome. But they ended up using process isolation too. And that kind of weakened it. And in the end, it was like portable native client. Okay, meet the new boss, same as the old boss. This is the Google Flash, right?
Yeah.
But when we did ASM.js and we showed Unreal Engine working, I think it was only a matter of time before Google threw in the towel. And in fact, everybody agreed in spring of 2015, we're going to take what was proven by ASM.js and make a new syntax, a binary syntax that's efficient, that loads into the same JavaScript VM that JavaScript loads into. So there'll be two source languages, one VM, very important, one garbage collector, one memory manager, one set of compiler stages, and that's called WebAssembly, and that's the successor to ASM.js. And it's important that it have binary syntax because at the end of the day, especially on mobile, if you're downloading JavaScript, even if you're using LZ compression on the wire, that's cool, but you've got to blow it out into memory and then parse the silly 8-character function keyword that I picked when I should have used something shorter. I picked it because of awk, the Unix tool. So anyway,
I'm not following. I want to, but I'm not following the awk thread.
Yeah,
but,
don't worry about it.
Is it surprising to you that how damn fast JavaScript is these days? I mean, like, because you've been through the whole journey. Yeah. I know every step of the way, but is it like? I mean, it feels incredible.
It does, but I knew. So the funny thing is, computer science is this big karmic wheel, right? Wheel of Fortuna, and in the 97, I was loaned by Netscape to do due diligence for Sun in their acquisition of Anamorphic, which was David Unger and friends, people. Craig, I'm forgetting his name. He went to Microsoft. These Stanford language buffs who had taken Smalltalk and then David created Self as a simpler sort of Smalltalk language and made really fast just-in-time compiling VMs for them. And they, well ahead of Java Hotspot or JavaScript V8 or any of these modern VMs, figured out how to make dynamic code fast because Smalltalk is a dynamic language, right? It has classes, it has I think more lockdown declarative syntax than JavaScript, but it's fundamentally dynamic. You don't declare the types. But you could infer the types as the program runs and you start to form these ideas about what types are actually flowing through key operations, and you form little so-called polymorphic inline caches that are optimized machine code. The cache is the machine code that assumes it does a quick check to make sure the type is right. And if it's not right, it bails to the interpreter. And if it is right, you go pretty fast. And that short test is a predicted branch. So things are pretty quick. All that amazing stuff I knew about in the 90s. And I didn't have time to do it. And Anamorphic got bought by Sun and they did Hotspot. And you needed that even in Java because at scale, Java has some dynamic aspects due to invoke interface. You can have basically collections of Java code where you don't know at the time each module or package is compiled exactly what's being called, what subclass or what implementation of an interface is being called. Mm-hmm. And so you want to optimize using this sort of dynamic polymorphic caching there too. And they did that. And Hotspot's amazing beast. I've met like 13 people who all claim they created it. I think one of them maybe deserve credit more than others. But I didn't get to do that in JavaScript. And when we knew that Google was going to do their own browser, which we knew at Mozilla around 2006, I also met the team that did V8. And it turns out it was Lars Bach, who was one of the young engineers from Anamorphic, who got acquired by Sun. And so Lars is like one of the world's expert on these kinds of virtual machines. And he picked my brains about JavaScript. I could tell he didn't like it at the time, but he had to do it. And
oh, really? Interesting.
Yeah, in 2006 lunch at Google's campus. And then I had another friend who was DevRel at Chrome, and he said, yeah, we don't know what they're doing. This is getting 2007 to fall, getting toward 2008. We're trying to get Chrome out, and we don't know what's going on with the V8 team. They're off in Aarhus, Denmark, rewriting their engine 4 times, which is good. That's the right way to do this kind of development. They were learning JavaScript, including all its quirks, which they came to hate with the fire of 1,000 suns, which is one of the reasons that Lars and company did Dart, their own language. But they also made the language fast. And meanwhile, we knew this was happening, so we got our act together with TraceMonkey, our tracing JIT at Mozilla, and Apple, I think, was also aware, and so they were doing their own JIT. So the era of JITted fast JavaScript in 2008 had this prehistory going back to Smalltalk and Self and Anamorphic. And the lineage is interesting because you had Lars at Anamorphic, and then he ends up at Google.
Field. Can you put your finger on how to design a language such that it fits in your head? Certain things like the colon or the certain notation aspects of Python that just kind of work. Is it something you have to kind of write out on paper, look and say it's just right? Is it a taste thing, or is there a systematic process? What's your sense?
I think it's more of a taste thing, but one thing that should be said is that you have to pick your audience, right? So the better defined the user audience is, or the users are, the easier it is to build something that fits in their minds, because their needs will be more compact and coherent. It is possible to find a projection, right? A compact projection for their needs. The more diverse the user base, the harder that is.
Yeah.
And so as Python has grown in popularity, that's also naturally created more complexity as people try to design any given thing. There will be multiple valid opinions about a particular design approach. And so I do think that's the downside of popularity. It's almost an intrinsic aspect of the complexity of the problem.
Well, at the very beginning, aren't you an audience of one? Aren't all the greatest projects in history were just solving a problem that you yourself had?
Well, so Clay Shirky, in his book on crowdsourcing, or in his kind of thoughts on crowdsourcing, he identifies the first step of crowdsourcing is me first collaboration. You first have to make something that works well for yourself.
Yeah.
It's very telling that when you look at all of the impactful big projects, well, they're fundamental projects now in the SciPy and PyData ecosystem, they all started with the people in the domain trying to scratch their own itch. And the whole idea of scratching your own itch is something that the open source or the free software world has known for a long time. But in the scientific computing areas, these are assistant professors or electrical engineering grad students. They didn't have really a lot of programming skill necessarily, but Python was just good enough for them to put something together that fit in their domain, right? So it's almost like it's a necessity is the mother of invention aspect. And also it was a really harsh filter for utility and compactness and expressiveness. Like, if it was too hard to use, then they wouldn't have built it because there was just too much trouble, right? It was a side project for them.
And also necessity creates a kind of deadline. It seems like a lot of these projects are quickly thrown together in the first step. And that, even though it's flawed, that just seems to work well for software projects.
Well, it does work well for software projects in general. And in this particular space, one of my colleagues, Stan Siebert, identified this, that all the projects in the SciPy ecosystem, if we just rattle them off, there's NumPy, there's SciPy, built by different collaborations of people, although Travis is the heart of both of them. But NumPy coming from Numeric and NumArray, these are different people. And then you've got Pandas, you've got Jupyter or IPython, there's Matplotlib, there's just so many others I'm, not going to do justice if I try to name them all, but all of them are actually different people. And as they rolled out their projects, the fact that they had limited resources meant that they were humble about scope. A great famous hacker, Jamie Zawiski, once said that every geek's dream is to build the ultimate middleware, right? And the thing is, with these scientists turned programmers, they had no such dream. They were just trying to write something that was a little bit better for what they needed, the MATLAB. And they were going to leverage what everyone else had built. So naturally, almost in kind of this annealing process or whatever, we built a very modular cover of the basic needs of a scientific computing library.
If you look at the whole human story, how much of a leap is it? We've developed all kinds of languages, all kinds of methodologies for communication, and just kind of like grew this collective intelligence. Civilization grew, it expanded. We wrote a bunch of books, and now we tweet. how big of a leap is programming if programming is yet another language? Is it just a nice little trick that's temporary in our human history, or is it like a big leap in the almost us becoming another organism at a higher level of abstraction, something else?
I think the act of programming or using grammatical constructions of some underlying primitives, that is something that humans do learn, but every human learns this. Anyone who can speak learns how to do this. What makes programming different has been that up to this point, when we try to give instructions to computing systems, all of our computers, well, actually, this is not quite true, but I'll first say it and then I'll tell you why it's not true. But for the most part, we can think of computers as being these iterated systems.
Yeah.
So when we program, we're giving very precise instructions to iterated systems that then run at incomprehensible speed and run those instructions. In my experience, some people are just better equipped to model systematic iterated systems. Iterated systems in their head.
Mm-hmm.
Some people are really good at that and other people are not. And so when you have, like, for instance, sometimes people have tried to build systems that make programming easier by making it visual, drag and drop. And the issue is you can have a drag and drop thing, but once you start having to iterate the system with conditional logic, handling case statements and branch statements and all these other things, the visual drag and drop part doesn't save you anything. You still have to reason about this giant iterated system with all these different conditions around it. That's the hard part, right? So handling iterated logic, that's the hard part. The languages we use then emerge to give us ability and capability over these things. Now, the one exception to this rule, of course, is the most popular programming system in the world, which is Excel, which is a data flow and a data-driven, immediate mode, data transformation-oriented programming system. And this actually not an accident that system is the most popular programming system because it's so accessible to a much broader group of people. I do think as we build future computing systems, you're actually already seeing this a little bit. It's much more about composition of modular blocks. They themselves actually maintain all their internal state, and the interfaces between them are well-defined data schemas. And so to stitch these things together using like IFTTT or Zapier or any of these kind of, I would say compositional scripting kinds of things. HyperCard was also a little bit in this vein. That's much more accessible to most people. It's really that implicit state that's so hard for people to track.
Yeah, okay, so that's modular stuff, but there's also an aspect where you're standing on the shoulders of giants. So you're building like higher and higher levels of abstraction. That you do that a little bit with language. So with language, you develop sort of ideas, philosophies from Plato and so on, and then you kind of leverage those philosophies as you try to have deeper and deeper conversations. But with programming, it seems like you can build much more complicated systems. Like without knowing how everything works, you can build on top of the work of others. And it seems like you're developing more and more sophisticated expressions, ability to express ideas in a computational space.
I think it's worth pondering the difference here between complexity and complication.
Sure.
Okay, right.
Back to Excel.
Well, not quite back to Excel, but the idea is, when we have a human conversation, all languages for humans emerged to support human relational communications, which is that the person we're communicating with is a person, and they would communicate back to us. And so we sort of hit a resonance point, right, when we actually agree on some concepts. So there's a messiness to it and there's a fluidity to it. With computing systems, when we express something to the computer and it's wrong, we just try again. So we can basically live many virtual worlds of having failed at expressing ourselves to the computer until the one time we expressed ourselves right. Then we kind of put it in production and then discover that it's still wrong, a few days down the road. So I think the sophistication of the things that we build with computing, one has to really pay attention to the difference between when an end user is expressing something onto a system that exists versus when they're extending the system to increase the system's capability for someone else to then interface with. And we happen to use the same language for both of those things in most cases, but it doesn't have to be that. And Excel is actually a great example of this, of kind of a counterpoint to that.
Okay, so what about the idea of, you said messiness.
Mm-hmm.
Wouldn't you put the software 2.0 idea this idea of machine learning into the further and further steps into the world of messiness. The same kind of beautiful messiness of human communication. Isn't that what machine learning is? Is building on levels of abstraction that don't have messiness in them, that at the operating system level, then there's Python, the programming languages that have more and more power. But then finally, there's neural networks that will ultimately work with data. And so the programming is almost in the space of data, and the data is allowed to be messy. Isn't that a kind of program? So the idea of software 2.0 is a lot of the programming happens in the space of data. So back to Excel. All roads lead back to Excel. In the space of data, and also the hyperparameters of the neural networks. And all of those allow the same kind of messiness that human communication allows.
It does, but my background is in physics. I took like 2 CS courses in college. So I don't have, now I did cram a bunch of CS in prep when I applied for grad school, but still, I don't have a formal background in computer science. But what I have observed in studying programming languages and programming systems and things like that is that there seems to be this triangle. It's one of these beautiful little iron triangles that you find in life sometimes. And it's the connection between the code correctness and kind of expressiveness of code, the semantics of the data, and then the kind of correctness or parameters of the underlying hardware compute system. So there's the algorithms that you want to apply. There's what the bits that are stored on whatever media actually represent. So the semantics of the data, within the representation. And then there's what the computer can actually do. And every programming system, every information system ultimately finds some spot in the middle of this little triangle. Sometimes some systems collapse them into just one edge.
Are we including humans as a system in this?
No. I'm just thinking about computing systems here. Okay. And the reason I bring this up is because I believe there's no free lunch around this stuff. So if we build machine learning systems to sort of write the correct code that is at a certain level of performance, so it'll sort of select, right? With the hyperparameters, we can tune kind of how we want the performance boundary in SLA to look like for transforming some set of inputs into certain kinds of outputs. That training process itself is intrinsically sensitive to the kinds of inputs we put into it. It's quite sensitive to the boundary conditions we put around the performance. So I think even as we move to using automated systems to build this transformation, as opposed to humans explicitly from a top-down perspective, figuring out, well, this schema and this database and these columns get selected for this algorithm, and here we put a Fibonacci heap for some other thing. Human design or computer design, ultimately the boundaries that we hit with these information systems is when the representation of the data hits the real world is where there's a lot of slop and a lot of interpretation. And that's where actually I think a lot of the work will go in the future, is actually understanding kind of how to better, in the view of these live data systems, how to better encode the semantics of the world for those things. It'll be less about the details of how we write a particular SQL query.
Okay, but given the semantics of the real world and the messiness of that, what does the word correctness mean when you're talking about code?
There's a lot of dimensions to correctness. Historically, and this is one of the reasons I say that we're coming to the end of the era of software, because for the last 40 years or so, software correctness was really defined about functional correctness. I write a function, it's got some inputs, does it produce the right outputs? If so, then I can turn it on, hook it up to the live database, and it goes. And more now we have, in fact, I think the bright line in the sand between machine learning systems or modern data-driven systems versus classical software systems is that the values of the input actually have to be considered with the function together to say this whole thing is correct or not. And usually there's a performance SLA as well. Like, did it actually finish making
What's SLA?
Sorry, service level agreement. So it has to return within some time. You have a 10 millisecond time budget to return a prediction of this level of accuracy, right? So these are things that were not traditionally in most business computing systems for the last 20 years at all. People didn't think about it. But now we have value dependence on functional correctness. So that question of correctness is becoming a bigger and bigger question.
What does that map to the end of software?
We've thought about software as just this thing that you can do in isolation with some test trial inputs and in a very, very sort of sandboxed environment. And we can quantify how does it scale, how does it, perform, how many nodes do we need to allocate if we want to scale this many inputs. when we start turning this stuff into prediction systems, real cybernetic systems, you're going to find scenarios where you get inputs that you're going to want to spend a little more time thinking about. You're going to find inputs that are it's not clear what you should do, right? So then the software has a varying amount of runtime and correctness with regard to input. And that is a different kind of system altogether. Now it's a full-on cybernetic system. It's a next generation information system that is not like traditional software systems.
Can you maybe describe what is a cybernetic system? Do you include humans in that picture? So is a human in the loop kind of complex mess of the whole kind of interactivity of software with the real world, or is it something more concrete?
Well, when I say cybernetic, I really do mean that the software itself is closing the observe, orient, decide, act loop by itself. So humans being out of the loop is in fact what, for me, makes it a cybernetic system. And
so humans are out of that loop.
When humans are out of the loop, when the machine is actually sort of deciding on its own what it should do next to get more information, that makes it a cybernetic system. So we're just at the dawn of this, right? I think everyone talking about ML/AI, it's great, but really the thing we should be talking about is when we really enter the cybernetic era. And all of the questions of ethics and governance and all correctness and all these things, they really are the most important questions.
Okay. Can we just linger on this? What does it mean for the human to be out of the loop in a cybernetic system? Because isn't the cybernetic system that's ultimately accomplishing some kind of purpose that at the bottom, the turtle's all the way down, at the bottom turtle is a human.
Well, the human may have set some criteria, but the human wasn't precise. So for instance, I just read the other day that earlier this year, or maybe it was last year at some point, the Libyan army, I think, sent out some automated killer drones with explosives. And there was no human in the loop at that point. They basically put them in a geofenced area, said, find any moving target, like a truck or vehicle that looks like this, and boom. That's not a human in the loop, right?
So increasingly, the less human there is in the loop, the more concerned you are about these kinds of systems, because there's unintended consequences. Like less, the original designer and engineer of the system is able to predict. Even one with good intent is able to predict the consequences of such a system. That's
right. There are some software systems, right, that run without humans in the loop that are quite complex, and that's like the electronic markets. And we get flash crashes all the time. We get, in the heyday of high frequency trading, there's a lot of market microstructure, people doing all sorts of weird stuff that the market designers had never really thought about, contemplated, or intended. So when we run these full-on systems with these automated trading bots, now they become automated, killer drones, and then all sorts of other stuff. We are. That's what I mean by we're at the dawn of the cybernetic era and the end of the era of just pure software.
Are you more concerned if you're thinking about cybernetic systems, or even like self-replicating systems? So systems that aren't just doing a particular task, but are able to sort of multiply and scale in some dimension in the digital or even the physical world. Are you more concerned about like the lobster being boiled, so a gradual, with us not noticing, collapse of civilization, or a big explosion? It's like, oops, kind of a big thing where everyone notices, but it's too late.
I think that it will be a different experience for different people. I do share a common point of view with some of the climate, people who are concerned about climate change and just the big existential risks that we have. But unlike a lot of people who share my level of concern, I think the collapse will not be quite so dramatic as some of them think. And what I mean is that I think that for certain tiers of, let's say, economic class or certain locations in the world, people will experience dramatic collapse scenarios. But for a lot of people, especially in the developed world, the realities of collapse will be managed. There will be narrative management around it so that they essentially insulate, the middle class will be used to insulate the upper class from the pitchforks and the flaming torches and everything.
It's interesting because so my specific question wasn't as general. My question was more about cybernetic systems, so software.
Okay.
It's interesting, but it would nevertheless perhaps be about class. So the effect of algorithms might affect certain classes more than others.
Absolutely.
I was more thinking about whether it's social media algorithms or actual robots. Is there going to be a gradual effect on us where we wake up one day and don't recognize the humans we are? or is it something truly dramatic where there's, like a meltdown of a nuclear reactor kind of thing, Chernobyl, like catastrophic events that are almost bugs in a program that scaled itself too quickly?
Yeah, I'm not as concerned about the visible stuff. And the reason is because the big visible explosions, I mean, this is something I said about social media, is that, at least with nuclear weapons, when a nuke goes off, you can see it and you're like, well, that's really, wow, that's kind of bad, right? I mean, Oppenheimer was reciting the Bhagavad Gita, right? When he saw one of those things go off. So we can see nukes are really bad.
He's not reciting anything about Twitter.
Well, but then when you have social media, when you have all these different things that conspire to create a layer of virtual experience for people that alienates them from reality and from each other, that's very pernicious. It's impossible to see, right? And it kind of slowly gets in there. So,
can you speak about this problem that you stumbled into of package management, Python package management? What is that? A lot of people speak very highly of Conda, which is part of Anaconda, which is a package manager. There's a ton of packages. So first, what are package managers? And second, what was there before? What is pip? And why is Conda more awesome?
The package problem is this, which is that in order to do numerical computing efficiently with Python, there are a lot of low-level libraries that need to be compiled with a C compiler or a C++ compiler or Fortran compiler. They need to not just be compiled, but they need to be compiled with all of the right settings. And oftentimes those settings are tuned for specific chip architectures. And when you add GPUs to the mix, when you look at different operating systems, you may be on the same chip, but if you're running Mac versus Linux versus Windows on the same x86 chip, you compile and link differently. All of this complexity is beyond the capability of most data scientists to reason about. And it's also beyond what most of the package developers want to deal with too.
Yes.
Because if you're a package developer, you're like, I code on Linux. This works for me. I'm good. It is not my problem to figure out how to build this on an ancient version of Windows, right? That's just simply not my problem. So what we end up with is we have a creator economy, or create a very creative crowdsourced environment where people want to use this stuff, but they can't. And so we ended up creating a new set of technologies like a build recipe system, a build system, and an installer system that is able to, to put it simply, it's able to build these packages correctly on each of these different kinds of platforms and operating systems and make it so when people want to install something, they can. It's just one command. They don't have to set up a big compiler system and do all these things. So when it works well, it works great. Now, the difficulty is we have literally thousands of people writing code in the ecosystem, building all sorts of stuff. And each person writing code, they may take a dependency on something else. And so you have all this web, incredibly complex web of dependencies. So installing the correct package for any given set of packages you want, getting that right subgraph is an incredibly hard problem. And again, most data scientists don't want to think about this. They're like, I want to install NumPy and Pandas. I want this version of some like geospatial library. I want this other thing. Like, why is this hard? These exist, right?
Yes.
And it is hard because you're installing this on a version of Windows, right? And half of these libraries are not built for Windows. Or the latest version isn't available, but the old version was. And if you go to the old version of this library, that means you need to go to a different version of that library. And so the Python ecosystem, by virtue of being crowdsourced, we were able to fill 100,000 different niches. But then we also suffer this problem that because it's crowdsourced and no one, it's like a tragedy of the commons, right? No one really wants to support their thousands of other dependencies. So we end up sort of having to do a lot of this. And of course, the Conda Forge community also steps up as an open source community that, maintains some of these recipes. That's what Conda does. Now, pip is a tool that came along after Conda to some extent. It came along as an easier way for the Python developers writing Python code that didn't have as much compiled, stuff. Mm-hmm. They could then install different packages. And what ended up happening in the Python ecosystem was that a lot of the core Python and web Python developers, they never ran into any of this compilation stuff at all. So even we have, on video, we have Guido van Rossum saying, the scientific community's packaging problems are just too exotic and different. I mean, you're talking about Fortran compilers, right? Like you guys just need to build your own solution, perhaps, right? So the core Python community went and built its own sort of packaging technologies, not really contemplating the complexity of this stuff over here. And so now we have the challenge where you can pip install some things. And some libraries, if you just want to get started with them, you can pip install TensorFlow, and that works great. The instant you want to also install some other packages that use different versions of NumPy or some like graphics library or some OpenCV thing or some other thing, you now run into dependency hell. Yeah. Because you cannot, OpenCV can have a different version of libjpeg over here than PyTorch over here. Like they all have to use if you want to use GPU acceleration, they have to all use the same underlying drivers and same GPU CUDA things. So it gets to be very gnarly, and it's a level of technology that both the makers and the users don't really want to think too much about.
And that's where you step in and try to solve this.
We try to solve it.
Subgraph problem. So how much is that? I mean, you said that you don't want to think, they don't want to think about it, but how much is it a little bit on the developer and providing them tools to be a little bit more clear of that subgraph of dependency that's necessary?
It is getting to a point where we do have to think about, look, can we pull some of the most popular packages together and get them to work on a coordinated release timeline, get them to build against the same test matrix, et cetera, right? And there is a little bit of dynamic around this, but again, it is a volunteer community.
Yeah.
People working on these different projects have their own timelines and their own things they're trying to meet. So we end up trying to pull these things together. And then it's this incredibly, and I would recommend just as a business tip, don't ever go into business where when your hard work works, you're invisible. And when it breaks because of someone else's problem, you get flack for it. Because that's in our situation, right? When something doesn't Conda install properly, usually it's some upstream issue, but it looks like Conda's broken, or it looks like, Anaconda screwed something up. When things do work though, it's like, oh yeah, cool, I just worked. Assuming naturally, of course, that's very easy to make that work, right? So we end up in this kind of problematic scenario, but it's okay because I think we're still, our heart's in the right place. We're trying to move this forward as a community sort of affair. I think most of the people in the community also appreciate the work we've done over the years to try to move these things forward in a collaborative fashion. So
one of the subgraphs of dependencies that became super complicated is the move from Python 2 to Python 3. So there's all these ways to mess with these kinds of ecosystems of packages and so on. So I just want to ask you about that particular one. What do you think about the move from Python 2 to 3? Why did it take so long? What were, from your perspective, just seeing the packages all struggle and the community all struggle through this process? What lessons do you take away from it? Why did it take so long?
Looking back, some people perhaps underestimated how much adoption Python 2 had. I think some people also underestimated they overestimated how much value some of the new features in Python 3 really provided. Like the things they really loved about Python 3 just didn't matter to some of these people on Python 2.
Yeah.
Because this change was happening as Python, SciPy was starting to take off really like past like a hockey stick of adoption in the early data science era in the early 2010s. A lot of people were learning and onboarding in whatever just worked. And the teachers were like, well, yeah, these libraries I need are not supported on Python 3 yet. I'm going to teach you Python 2. It took a lot of advocacy to get people to move over to Python 3. So I think it wasn't any particular single thing, but it was one of those death by, a dozen cuts, which just really made it hard to move off of Python 2. And also Python 3 itself, as they were kind of breaking things and changing things around and reorganizing the standard library, there's a lot of stuff that was happening there that it kept giving people an excuse to say, I'll put off till the next version. 2 is working fine enough for me right now. So I think that's essentially what happened there. And I will say this, though, the strength of the Python data science movement, I think, is what kept Python alive in that transition. Because a lot of languages have died and left their user bases behind. If there wasn't the use of Python for data, there's a good chunk of Python users that during that transition would have just left for Go and Rust and stayed. In fact, some people did. They moved to Go and Rust and they just never looked back. The fact that we were able to grow by millions of users, the Python data community, that is what kept the momentum for Python going. And now the usage of Python for data is over 50% of the overall Python user base. So I'm happy to debate that on stage somewhere at PyCon with someone if they really want to take issue with that statement. But from where I sit, I think that's true.
the statement there, the idea is that the switch from Python 2 to Python 3 would have probably destroyed Python if it didn't also coincide with Python, for whatever reason, just overtaking the data science community, anything that processes data.
Yeah.
So like the timing was perfect.
Yep.
That this maybe imperfect decision was coupled with great timing on the value of data in our world.
I would say the troubled execution of a good decision. It was a decision that was necessary. It's possible if we had more resources, we could have done it in a way that was a little bit smoother. But ultimately, the arguments for Python 3, I bought them at the time and I buy them now, right? Having great text handling is like a non-negotiable table stakes thing you need to have in a language. So that's great. But the execution, Python is it's volunteer driven. It's like now the most popular language on the planet, but it's all literally volunteers. So the lack of resources meant that they had to do things in a very hamstrung way. And I think to carry the Python momentum in the language through that time, the data movement was a critical part of that.
So some of it is carrot and stick. I actually have to shamefully admit that it took me a very long time to switch from Python 2 and Python 3 because I'm a machine learning person. It was just, for the longest time, you could just do fine with Python 2.
Right.
But I think the moment where I switched everybody I worked with and switched myself for small projects and big is when NumPy announced that they're going to end support, like in 2020 or something like that.
Right.
So like when I realized, this is going to end.
Right.
So that's the stick.
That's
not
the stick.
A carrot. That's not. So for the longest time it was carrots. It was like all of these packages were saying, okay, we have Python 3 support now. Come join us. We have Python 2 and Python 3. But when NumPy, one of the packages I sort of love and depend on, said like, nope, it's over. That's when I decided to switch. I wonder if you think it was possible much earlier for somebody like NumPy or some major package to step into the cold.
Well, it's a chicken and egg
this
problem too, right? You don't want to cut off a lot of users unless you see the user momentum going too. So the decisions for the scientific community for each of the different projects, there's not a monolith. Some projects are like, we'll only be releasing new features on Python 3.
Yeah.
And that was more of a sticky carrot, or a firm carrot, if you will, a firm carrot. A stick-shaped carrot.
Yeah.
But then for others, NumPy in particular, because it's at the base of the dependency stack for so many things, that was the final stick. That was a stick-shaped stick. People were saying, look, if I have to keep maintaining my releases for Python 2, that's that much less energy that I can put into making things better for the Python 3 folks, or in my new version, which is, of course, going to be Python 3. So people were also getting kind of pulled by this tension. So the overall community sort of had a lot of input into when the NumPy core folks decided that they would end of life on Python 2.
So these numbers are a little bit loose, but there are about 10 million Python programmers in the world. You could argue that number, but let's say 10 million. There's actually, where I was looking, said 27 million total programmers, developers in the world. You mentioned in a talk that changes need to be made for there to be 100 million Python programmers. So first of all, do you see a future where there's 100 million Python programmers? And second, what kind of changes need to be made?
So Anaconda, Miniconda get downloaded about 1 million times a week. So I think the idea that there's only 10 million Python programmers in the world is a little bit undercounting. There are a lot of people who escape traditional counting that are using Python and data in their jobs. I do believe that the future world the world I would like to see is one where people are data literate. So they are able to use tools that let them express their questions and ideas fluidly. And the data variety and data complexity will not go down. It will only keep increasing. So I think some level of code or code-like things will continue to be relevant. And so my hope is that we can build systems that allow people to more seamlessly integrate Python kinds of expressivity with data systems and operationalization methods that are much more seamless. And what I mean by that is, right now you can't punch Python code into an Excel cell. I mean, there's some tools you can do to kind of do this. We'd even built a thing for doing this back in the day. But I feel like the total addressable market for Python users, if we do the things right, is on the order of the Excel users, which is, a few hundred million. So I think Python has to get better at being embedded, being a smaller thing that pulls in just the right parts of the ecosystem to run numerics and do data exploration, meeting people where they're already at with their data and their data tools. And then I think also it has to be easier to take some of those things they've written and flow those back into deployed systems or little apps or visualizations. I think if we don't do those things, then we will always be kept in a silo as sort of an expert user's tool and not a tool for the masses.
I work with a bunch of folks in the Adobe Creative Suite, and I'm kind of forcing them or inspiring them to learn Python to do a bunch of stuff that helps them. And it's interesting because they probably wouldn't call themselves Python programmers, but they're all using Python. I would love it if the tools like Photoshop and Premiere and all those kinds of tools that are targeted towards creative people, I guess that's where Excel is targeted towards a certain kind of audience that works with data, financial people, all that kind of stuff. If there would be easy ways to use Python for quick scripting tasks.
Yeah.
And there's an exciting application of artificial intelligence in this space that I'm hopeful about, looking at OpenAI Codex with generating programs.
Yeah.
So almost helping people bridge the gap from kind of visual interface to generating programs to something formal, and then they can modify it and so on, but kind of without having to read the manual, without having to do a Google search on Stack Overflow, which is essentially what a neural network does when it's doing code generation, is actually generating code and allowing a human to communicate with multiple programs, and then maybe even programs to communicate with each other via Python.
Right.
So that to me is a really exciting possibility, because I think there's a friction to kind of like, how do I learn how to use Python in my life? There's oftentimes you kind of start a class, you start learning about types. Yes, I don't know, functions. Like this is, Python is the first language with which you start to learn to program. But I feel like that's going to take a long time for you to understand why it's useful. You almost want to start with a script.
Well, you do. In fact, I think starting with the theory behind programming languages and types and all that. I mean, types are there to make the compiler writers' jobs easier. Types are not, I mean, heck, do you have an ontology of types for just the objects on this table? No. So types are there because compiler writers are human and they're limited in what they can do. But I think that the beauty of scripting, like there's a Python book that's called Automate the Boring Stuff, which is exactly the right mentality. I grew up with computers in a time when I could, when Steve Jobs was still pitching these things as bicycles for the mind. They were supposed to not be just media consumption devices, but they were actually, you could write some code. You could write BASIC, you could write some stuff to do some things. And that feeling of a computer as a thing that we can use to extend ourselves has all but evaporated for a lot of people. So you see a little bit in parts in the generation of youth around Minecraft or Roblox, right? And I think Python, CircuitPython, these things could be a renaissance of that, of people actually shaping and using their computers as an extension of their minds and their curiosity, their creativity. So, you talk about scripting the Adobe suite with Python in the 3D graphics world. Python is a scripting language that some of these 3D graphics suites use. And I think that's great. We should better support those kinds of things. But ultimately, the idea that I should be able to have power over my computing environment. If I want these things to happen repeatedly all the time, I should be able to say that somehow to the computer, right? Now, whether the operating systems get there faster by having some, Siri backed with OpenAI, with whatever. So you can just say, Siri, make this do this and this and every other Friday, right? We probably will get there somewhere. And Apple's always had these ideas. There's the Apple script in the menu that no one ever uses. But you can do these kinds of things. But when you start doing that kind of scripting, the challenge isn't learning the type system or even the syntax of the language. The challenge is all of the dictionaries on all the objects of all their properties and attributes and parameters. Like, who's got time to learn all that stuff, right? So that's when then programming by prototype or by example becomes the right way to get the user to express their desire. So there's a lot of these different ways that we can approach programming. But I do think as you were talking about the Adobe scripting thing, I was thinking about, when we do use something like NumPy, when we use things in the Python data and scientific, let's say, expression system, there's a reason we use that, which is that it gives us mathematical precision. It gives us actually quite a lot of precision over precisely what we mean about this data set, that data set. And it's the fact that we can have that precision that lets Python be powerful over as a duct tape for data. You give me a TSV or a CSV, and if you give me some massively expensive vendor tool for data transformation, I don't know I'm going to be able to solve your problem. But if you give me a Python prompt, you can throw whatever data you want at me. I will be able to mash it into shape. So that ability to take it as sort of this machete out into the data jungle is really powerful. And I think that's why at some level, we're not going to get away from some of these expressions and APIs and libraries in Python for data transformation.
You've been at the center of the Python community for many years. If you could change one thing about the community to help it grow, to help it improve, to help it flourish and prosper, what would it be? I mean, not, it doesn't have to be one thing, but what kind of comes to mind? What are the challenges?
Humility is one of the values that we have at Anaconda, at the company, but it's also one of the values in the community that it's been breached a little bit in the last few years, but in general, people are quite decent and reasonable and nice. And that humility prevents them from seeing the greatness that they could have. I don't know how many people in the core Python community really understand that they stand perched at the edge of an opportunity to transform how people use computers.
Yes.
And actually, PyCon, I think it's the last physical PyCon I went to, Russell Keith McGee gave a great keynote about, very much along the lines of the challenges I have, which is, Python, for a language that can't put an interface up on like the most popular computing devices, it's done really well as a language, hasn't it? You can't write a web front end with Python, really. I mean, everyone uses JavaScript. You certainly can't write native apps. Mm-hmm. So for a language that you can't actually write apps in any of the front and runtime environments, Python's done exceedingly well.
Yeah.
And so that wasn't to pat ourselves on the back. That was to challenge ourselves as a community to say, we, through our current volunteer dynamic, have gotten to this point. What comes next, and how do we seize, we've caught the tiger by the tail. How do we make sure we keep up with it as it goes forward?
So that's one of the questions I have about sort of open source communities is, at its best, there's a kind of humility. Mm-hmm. Is that humility prevent you to have a vision for creating something like very new and powerful?
And you've brought us back to consciousness again. The collaboration is a swarm emergent dynamic. Mm-hmm. Humility lets these people work together without anyone trouncing anyone else. How do they, in consciousness, there's the question of the binding problem. How does our attention, how does that emerge from, billions of neurons?
Yes.
So how can you have a swarm of people emerge a consensus that has a singular vision to say, we will do this, and most importantly, we're not going to do these things. Mm-hmm. Emerging a coherent, pointed, focused leadership dynamic from a collaboration, being able to do that and then dissolve it so people can still do the swarm thing. That's a problem. That's a question.
So do you have to have a charismatic leader? For some reason, Linus Torvald comes to mind, but there's people who criticize.
He rules with an iron fist, man.
But there's still charisma.
There's charisma, right?
There's a charisma to that iron fist. There's every leader is different, I would say, in their success. So he doesn't. I don't even know if you can say he doesn't have humility. There's such a meritocracy of ideas that like this is a good idea and this is a bad idea.
There's a step function to it. Once you clear a threshold, he's open. Once you clear the bozo threshold, he's open to your ideas, I think.
Yes.
Right.
But see, the interesting thing is obviously that will not stand in an open source community if that threshold that is defined by that one particular person is not actually that good.
Mm-hmm.
So you actually have to be really excellent at what you do.
Mm-hmm.
So he's very good at what he does. And so there's some aspect of leadership where you can get thrown out. People can just leave. That's how it works with open source.
Yeah.
They'll fork. But at the same time, you want to sometimes be a leader, like with a strong opinion, because people, there's some kind of balance here for this like hive mind to get behind.
Leadership is a big topic. And I didn't, I'm not one of these guys that went to MBA school and said, I'm going to be an entrepreneur and I'm going to be a leader and I'm going to read all these Harvard Business Review articles on leadership and all this other stuff. Like I was a physicist turned into a software nerd who then really like nerded out on Python. And now I am entrepreneurial, right? I saw a business opportunity around the use of Python for data. But for me, what has been interesting over this journey with the last 10 years is how much I started really enjoying the understanding and thinking deeper about organizational dynamics and leadership. Mm-hmm. And leadership does come down to a few core things. Number one, a leader has to create belief, or at least has to dispel disbelief. Leadership also, you have to have vision, loyalty, and experience.
So can you say belief in a singular vision? Like what does belief mean?
Yeah, belief means a few things. Belief means here's what we need to do, and this is a valid thing to do, and we can do it. That you have to be able to drive that belief. And every step of leadership along the way has to help you amplify that belief to more people. Mm-hmm. I think at a fundamental level, that's what it is. You have to have a vision. You have to be able to show people that, or you have to convince people to believe in the vision and to get behind you. And that's where the loyalty part comes in and the experience part comes in.
There's all different flavors of leadership. So if we talk about Linus, we could talk about Elon Musk and Steve Jobs. Mm-hmm. There's Sundar Pichai. There's people that kind of put themselves at the center and are strongly opinionated. Mm-hmm. And some people are more like consensus builders.
Right.
What works well for open source? What works well in the space of programmers? So you've been a programmer, you've led many programmers and are now sort of at the center of this ecosystem. What works well in the programming world, would you say?
It really depends on the people, what style leadership is best. And it depends on the programming community. I think for the Python community, servant leadership is one of the values. Like at the end of the day, the leader has to also be the high priest of values, mm-hmm. right? So any collection of people has values that they're living. And if you want to maintain certain values and those values help you as an organization become more powerful, then the leader has to live those values unequivocally and has to hold the values. So in our case, in this collaborative community around Python, I think that the humility is one of those values. Servant leadership, you actually have to kind of do the stuff. You have to walk the walk, not just talk the talk. I don't feel like the Python community really demands that much from a vision standpoint.
And they should.
And I think they should.
This is the interesting thing is like so many people use Python. From where comes the vision? Like you have a Elon Musk type character who makes bold statements about the vision for particular companies he's involved with. Mm-hmm. And it's like, I think a lot of people that work at those companies kind of can only last if they believe that vision. And some of it is super bold. So my question is, and by the way, those companies often use Python. How do you establish a vision? Like get to 100 million users, right? Mm-hmm. Get to where, the Python is at the center of the machine learning and data science, machine learning, deep learning, artificial intelligence revolution, mm-hmm. right? Like, in many ways, perhaps the Python community is not thinking of it that way, but it's leading the way on this. Mm-hmm. Like the tooling is like essential.
Right. Well, for a while, PyCon, people in the scientific Python and the PyData community, they would submit talks. This is early 2010s, mid 2010s. They would submit talks for PyCon, and the talks would all be rejected because there was the separate sort of PyData conferences. And they're like, well, these probably belong more to PyData. And instead there'd be yet another talk about, threads and, whatever, some web framework. And it's like, that was an interesting dynamic to see that there was, I mean, at the time it was a little annoying because we wanted to try to get more users and get more people talking about these things. And PyCon is a huge venue, right? It's thousands of Python programmers. But then also came to appreciate that, having an ecosystem that allows parallel innovation is not bad, right? There are people doing embedded Python stuff. There's people doing web programming, there's people doing scripting, there's cyber uses of Python. I think ultimately at some point, if your slide mold covers so much stuff, you have to respect that different things are growing in different areas and different niches. Now, at some point that has to come together and the central body has to provide resources. The principle here is subsidiarity. Give resources to the various groups to then allocate as they see fit in their niches. That would be a really helpful dynamic. But again, it's a volunteer community. It's not like they had that many resources to start with.
You're one of the most impactful humans in the Python ecosystem. So you're an engineer, leader of engineers, but you're also a philosopher. So let's talk both in this conversation about programming and philosophy. First, programming. What to you is the best or maybe the most beautiful feature of Python? Or maybe the thing that made you fall in love or stay in love with Python?
Well, those are three different things. What I think is most beautiful, what made me fall in love, what made me stay in love. When I first started using it was when I was a C++ computer graphics performance nerd.
In the 90s?
In late 90s. And that was my first job out of college. And we kept trying to do more and more like abstract and higher order programming in C++, which at the time was quite difficult. With templates, the compiler support wasn't great, etc. So when I started playing around with Python, that was my first time encountering really first-class support for types, for functions, and things like that. And it felt so incredibly expressive. So that was what kind of made me fall in love with it a little bit. And also, once you spend a lot of time in a C++ dev environment, the ability to just whip something together that basically runs and works the first time is amazing. So really productive scripting language. I mean, I knew Perl, I knew Bash. I was decent at both, but Python just made everything. It made the whole world accessible, right? I could script this and that and the other network things, little hard drive utilities. I could write all of these things in the space of an afternoon. Mm-hmm. And that was really, really cool. So that's what made me fall in love.
Is there something specific you could put your finger on that you're not programming in Perl today? Like why Python for scripting?
I think there's not a specific thing as much as the design motif of both the creator of the language and the core group of people that built the standard library around him. There was a taste to it. I mean, Steve Jobs, used that term, in somewhat of a arrogant way, but I think it's a real thing that it was designed to fit. A friend of mine actually expressed this really well. He said, Python just fits in my head. And there's nothing better to say than that. Now people might argue modern Python, there's a lot more complexity, but certainly as version 1.5.2, I think was my first version, that fit in my head very easily. So that's what made me fall in love with it.
Okay, so the most beautiful feature of Python that made you stay in love. It's like over the years, what has you do a double take and you return to often as a thing that just brings you a smile?
I really still like the ability to play with meta classes and express higher order things when I have to create some new object model to model something, right? It's easy for me because I'm pretty expert as a Python programmer. I can easily put all sorts of lovely things together and use properties and decorators and other kinds of things and create something that feels very nice. So that to me, I would say that's tied with the NumPy and vectorization capabilities. I love thinking in terms of the matrices and the vectors and these kind of data structures. So I would say those two are kind of tied for me.
So the elegance of the NumPy data structure, like slicing through the different multidimensional.
Yeah, there's just enough things there. It's a very simple, comfortable tool. Just it's easy to reason about what it does when you don't stray too far.
Some basic questions about people maybe that are more like beginners in this field. What's the best programming language to learn if you're interested in machine learning?
I would say Python, just because it's the easiest one to learn. And also a lot of programming in machine learning happens in Python. So if you don't know any other programming language, Python is actually going to get you a long way.
Yeah, it seems like sort of it's a toss-up question because it seems like Python is so much dominating the space now. But I wonder if there's interesting alternative. Obviously, there's like Swift, and there's a lot of interesting alternatives popping up, even JavaScript. So or R, more like for the data science applications. But it seems like Python more and more is actually being used to teach like introduction to programming at universities.
Right.
So it just combines everything very nicely. Let's start with a fun question. If we're living in a simulation, what programming language do you think it's written in? And maybe from a software engineering perspective, what do you think are some of the design principles that it operates under?
You know, there are a lot of really lovely papers. Like one came out of MSR, the Autodidactic Universe. Did you have a chance to see that? Oh, you got to read it. It's like April of 2021. It's just brand new. But basically, the idea is that the universe is like some sort of giant self-learning system that can self-evolve, almost like Nomic. And then you got Wolfram running around saying, hey, we can come up with these like very simple rules and we can reconstruct all of reality at some arbitrary point. So I have absolutely no idea what's right. You know, I look at it kind of like a formal system, and I say, well, if you're stuck within the system, it's hard to actually understand that you're inside the system. You know, it's kind of like an object language to a meta language. And, you know, there's this thing that is outside of it, but because you're constrained and limited by the simulation, you can't really understand the nature of the thing that's outside of it. It's almost like Minecraft. You can build these redstone computers within Minecraft and simulate and emulate things within it, but you really can't go outside of that environment.
The people outside of it can formally prove that it's correct or whatever, but the creatures inside of the system can't hope to perfectly understand it and prove something about it.
Well, also the question is, it's a computation question. You know, does P equal NP? Because you'd have to be able to emulate all of these.
How long will it take?
Yeah, exactly. And so I have no clue what type of language it would have to look like, but it would probably not be anything we're used to at the moment. It'd have to be something else, and we'd have to have some more fundamental resolution of the relationship of these formal systems and how they get extended. So that's like a 22nd century question instead of a 21st century.
Do you find the Stephen Wolfram idea compelling? It's a very different way of programming, which is you set some rules, you set some initial conditions, and let it run and see what happens.
Yeah, and it's not a new concept. I mean, like the Santa Fe Institute's been doing that for a long time, and you can use it for economic modeling, and you can show that in certain cases, there's this concept of simple rules evolving into a complex system is somewhat more predictive than trying to build a complex top-down model for things. And I guess there's some analogies to these things in AI where, you know, you start with some simple things and then somehow it just figures stuff out in its environment over time, and much better than if you actually tried to model it with Prolog or, you know, something like that. So that is exciting because you get to just do a few things, let the thing run, and then see what happens. And that's a lot of fun. In fact, it got so exciting, Wolfram came to us and he said, hey, let's do an NFT marketplace. And I said, what do you want to do? And he said, I got all these universes to sell. And I said, okay, well, that's going to be fun. So we're going to set up an auction system or something like that with him. And I think maybe end of this month or next month, we'll figure out how to do NFTs on Cardano with Wolfram universes. So as soon as we can sell one, I'll give you one, and then we can all just claim that we're living in some sort of Wolfram simulation.
I don't know how much money I have, but I'm going to give everything I have to get Rule 30, which is one of his universes that he's created. One of the first ones where he discovered some interesting complexities.
I think Rule 30 is Turing complete, or is that 45? I can't remember which one.
You know your stuff.
Yeah.
Actually, I'm not sure if they proved anything about Rule 30 in terms of whether it's Turing complete or not.
Okay.
But there's fun competitions on it, which is trying to predict something about Rule 30, about the way it evolves. And so far, nobody's been able to do it. Just like looking at the middle column, try to predict as the system evolves, say anything like conclusive about the future of the system as it evolves. It's fascinating. It's both beautiful that simple rules can create that kind of complexity, and it's also sad that we can't like make perfect sense of it, like perfectly predict the future. Even though it's all simple and deterministic, we can't say something conclusive about like when the thing will end. When will this little cellular automata like evolve in a certain way? And then nuclear weapons will be invented and they blow each other up, and then it'll just be this empty 1D cellular automata.
Well, doesn't that make it fun, though?
Yeah, it's fun, but when you're trying to create, and we'll talk about something that operates the economy and the way humans transact and cooperate and fall in love and work together, then you'd like to be a little bit more formal and try to say something conclusive. If this entire universe is just cellular automata, then being conclusive is kind of hopeless, generally speaking. And the hope is, I guess, that there will be pockets of within the cellular automata where you could be predictive, where you can formally show that something is true, and then you can rely on that. You'll be resilient and all those kinds of things, even though the rest of the thing is a giant mess that's unpredictable.
Didn't they call that Laplace's demon?
Yes.
Yeah.
Well, I wonder what the demon is up to these days. So before we go into this fascinating Darwinian evolution of cryptocurrencies, let me ask you sort of a basic programming question. There's a fascinating aspect to your work with Cardano that you use Haskell as to build the infrastructure. But even stepping back more, looking at this landscape, another place where Darwinian evolution operates, looking at this landscape of programming languages, you as an engineer, you as a philosopher, both, what programming languages do you think are interesting? And more practically, what programming languages, if you were to advise like students today, should they learn?
Yeah. So there's the pedagogy of learning how to program and to express the theory of computer science. Like you have to learn how to write algorithms. You have to learn what data structures are. You have to be able to do analysis of these things. And that probably I think the debate is over Python is probably the best language, or JavaScript to get started with, because they're very useful. The libraries are amazing. There's just tons of online materials. Even MIT is now teaching their introduction to computer science in Python. And they used to do Lisp. I mean, these guys were hardcore.
I still love Lisp.
Oh man, it's great. You know, these are your father's parentheses. They're elegant weapons from a time long ago. But you know, that's a great starting point. And it's not about falling in love with a language. It's just falling in love with computing. It's about falling in love with having a dialogue with a computer and thinking about, well, how would I solve that? How would I interact with that? What does this need to look like? Functional programming is what we've chosen to use for Cardano, mostly because we're living in the academic world. We've written 105 papers. And the problem is you have to translate that work into code. And the gap between an imperative language like a C++ or C and these academic rigorous papers is extremely large. Mm-hmm. And so there's going to be a lot of semantical ambiguity between those two. And what I mean by that is that you might end up implementing a wrong thing. You might think that what you've built is the paper, but the computer's not going to tell you that because the paper is written in prose and maybe typed up in LaTeX or something. But there's no proof chain, evidence chain that you can show that there's no ambiguity. When you look at a functional language, you're a little closer to math. And so as a consequence, the translation of the papers that we spent so damn long writing and writing proofs about and so forth to code is much smaller. Now, the downside is these functional languages tend to be a bit more academic, and they tend to have not necessarily the best Windows support, and the libraries aren't so good. And also, they tend to be a little slower when compared as a whole on average to languages like C, for example. So it's really a question of, okay, what are you designing for version 1? Are you designing for performance, and are you designing for developer accessibility? Or are you designing for correctness, and are you designing for a high fidelity representation of the protocol? Okay, so Haskell was chosen as kind of the version 1 because we knew that the kinds of people who think about that are also the kinds of people that would have an easy time reading a paper like Ouroboros and working their way through all of this. And they would do a pretty good job writing a formal specification and then translating that into running code. Then once you have that, you have a blueprint that you can actually reason about, maintain. And if you really wanted to, you could then turn that into a Rust code base or into a Java code base. Going the other way around would be, you know, kind of pointless and counterproductive. The other side of it is that Haskell code or functional code tends to be significantly more concise. And I actually have a real life example of that. So if you take a look at Mantis, we implemented a full Ethereum node in Scala. It's only about 14 or 15,000 lines of code. And you compare that with like C++ Bitcoin, I think that's 120, 150,000 lines of code. So it's almost 10 times smaller. And so less code, less to read. And you tend to read code significantly more than you would write code. So it's always an advantage for maintenance, understandability, documentation, and other sort of things when you have more concise code bases. And also it's a lot easier for you to apply stronger tools to a functional code base like static analysis or property-based testing or these types of things than an imperative code base. But the thing is, it's almost like a religion. It's like or language. It's like saying what's French versus Russian versus English. Everybody has their adherents. They say, oh, well, they have the best poetry here. Or
Russian, yeah, wins.
There you go. Always, right? Russian. Everybody has their favorite tools and their favorite languages. But it just comes down to what problems are you trying to solve and what problem domain do you live in. If you're inventing new protocols based on science, you're going to take the time to write a paper, go through the peer review process, as you've done personally. You know how hard it can be to get into a conference and go through that and get your ass kicked. Then you also have to apply the exact same level of care to the engineering side in terms of the implementation of that, or else you will make a mistake, and that mistake will probably be an exploit in the system that destroys the security properties of the system. So we really had no choice but to go to some notion of functional. The question was, what's the Goldilocks language? Do you use a hybrid language like Scala and F# or Clojure, where you still have some connection to understandable things like .NET or the JVM? Or do you go to an overly academic language like Idris or Agda or, Isabel? And there you can really dial up the correctness and write all kinds of crazy proofs. But by the way, it's like the 7 people who write your code, they go on vacation a lot. You'll never get anything done. So Haskell kind of felt like a nice middle ground between those two, where if we needed to pull in to the left, we could. If you wanted to pull into the right, you could as well. That said, it's really amazing to see what the hybrid languages have done. If I was a new student in computer science and I said, learn any language to grow your career from, Scala 3 is probably the language to go with.
Interesting.
Yeah, it's great because it's like you want it to be like Java, it's Java, and it looks kind of like a Java program. You want it to be like Python and scripted, and you use a REPL, you can do that. You want to go hardcore dependent object types and do like weird proofs and stuff and the functional, you do all that. You have access to all of these things, and Martin Odersky is a brilliant guy. He's done some phenomenal work, basically, because he was one of the guys who created the JVM, and he's worked on compilers for over 20 years. He did a lot of really hardcore work on trying to build a concise, nice, modern language that does a little bit of everything. And it's got great applications in data science and in AI. And it's also heavily used in modern companies. Like Netflix uses Scala for all of their microservice architecture.
Interesting.
Yeah, so that's a great language. And it's easy to pick up, and it's easy to hire people into it. You just find these Eastern European guys who were Java programmers for 10 years, 15 years, and they got tired of making $20 an hour, so they picked up Scala so they can make $35 an hour. And they're really good at it,
Yeah.
And that's a great gateway drug because, like Quick Check in Haskell, you have Scala Check in Scala. You can also do model checking. You can also go and use a TLA spec and make it work with Scala and so forth. So it gets you a little bit of everything. And, you can then move around that entire design space in a beautiful way.
So the recommendation is maybe if you want to go vanilla, you go Python and JavaScript.
When you're getting started.
It's the getting started.
Because that'll get you everything. You can do web scrapers and anything. It's
like
just
all of us
fun.
experiment with drugs in undergrad. That's where Scala 3 comes in. It's a gateway drug to then potentially more hardcore functional languages like Haskell. Do you think C and C++ still has a role?
No, I think Rust has completely replaced the need for them. Go and Rust. Those are the two twins of doom. I mean, Google created Go just to get rid of C. They hated C that much. And then Rust is just a phenomenal language as well.
Hate can be a great motivator.
Yeah.
Huge.
I don't know if you know Brendan Eich. He wrote JavaScript in 10 days. And that's an interesting story. It makes me wonder, and it was, famously for many years considered to be a pretty crappy programming language. Still is, perhaps. It's been improving sort of consistently. But the interesting thing about that guy is, he doesn't get any awards. You don't get a Nobel Prize or a Fields Medal or
for inventing a crappy piece of software code
that is currently the number one programming language in the world and is increasingly running the back end of the internet.
Well, does he know why everybody uses it? Like, that would be an interesting thing. Was it the right thing at the right time? Because like when stuff like JavaScript came out, like there was a move from writing C programs in C++ to, let's call what they call managed code frameworks, where you write simple code, it might be interpreted, it has lots of libraries, productivity is high, and you don't have to be an expert. So, Java was supposed to solve all the world's problems. It was complicated. JavaScript came out, after a bunch of other scripting languages. I'm not an expert on it, but was it the right thing at the right time? Or was there something, clever? Because he wasn't the only one.
There's a few elements.
And maybe if he figured out what it was, then he'd get a prize. Like that.
Constructive theory.
Yeah. Maybe his problem is he hasn't defined this. Or he just needs a good promoter.
Well, I think there was a bunch of blog posts written about it, which is like wrong is right, which is like doing the crappy thing fast, just like hacking together the thing that answers some of the needs, and then iterating over time, listening to developers, like listening to people who actually use the thing. This is something you can do more in software.
Yep.
But the right time, like you have to have a good instinct of when is the right time for the right tool, and make it super simple and just get it out there. The problem is, this is true with hardware, this is less true with software, is there's backward compatibility that just drags behind you as you try to fix all the mistakes of the past. But the timing
was good.
There's something about that. And it wasn't accidental. You have to like give yourself over to you have to have this like broad sense of what's needed now. Both scientifically and like the community, and just like this, it was obvious that there was the interesting thing about JavaScript is everything that ran in the browser at the time, like Java and I think other like Scheme, other programming languages, they were all in a separate external container. And then JavaScript was literally just injected into the web page. It was the dumbest possible thing, running in the same thread as everything else. And like, it was inserted as a comment. So JavaScript code is inserted as a comment in the HTML code. And it's either genius or super dumb, but it's like,
right. So it had no apparatus for like a virtual machine and container. No. It just executed in the framework of the program that's already running.
And it was,
that's cool.
And then because something about that accessibility, the ease of its use, resulted in then developers innovating of how to actually use it. I mean, I don't even know what to make of that, but it does seem to echo across different software, like stories of different software. PHP has the same story, really crappy language that just took over the world.
Well, we just have a joke that the random length instruction set, variable length instruction set's always won, even though they're obviously worse. Like nobody knows why. x86 is arguably the worst architecture, on the planet. It's one of the most popular ones.
I know you've talked about this in quite a few places, but you have created one of the most popular programming languages in the world. It's the programming language that I first learned about object-oriented programming with. I think it's a programming language that a lot of people use in a lot of different places and millions of devices today, Java. So the absurd question, but can you tell the origin story of Java?
So long time ago at Sun, in about 1990, there was a group of us who were kind of worried that there was stuff going on in the universe of computing that the computing industry was missing out on. And so a few of us started this project at Sun that really got going. I mean, we started talking about it in 1990, and it really got going in 91. And it was all about, what was happening in terms of, computing hardware, processors and networking and all of that was outside of the computer industry. And that was everything from the sort of early glimmers of cell phones that were happening then to, you look at elevators and locomotives and process control systems in factories and all kinds of audio equipment and video equipment. They all had processors in them, and they were all doing stuff with them. And it sort of felt like there was something going on there that we needed to understand. And
So C and C++ was in the air already.
oh no, C and C++ absolutely owned the universe at that time. Everything was written in C and C++.
So where was the hunch that there was a need for a revolution?
Well, so the need for a revolution was not about a language. It was just as simple and vague as there are things happening out there.
We need to understand them.
We need to understand them. And so a few of us went on several somewhat epic road trips.
Literal road trips?
Literal road trips. It's like get on an airplane, go to Japan, visit, Toshiba and Sharp and Mitsubishi and Sony and all of these folks. And, because we worked for Sun, we had, folks who were willing to give us introductions. We visited, Samsung and, a bunch of Korean companies, and we went all over Europe. We went to, places like Philips and Siemens and Thomson. And
what did you see there?
For me, one of the things that sort of leapt out was that they were doing all the usual computer things that people had been doing like 20 years before. The thing that really leapt out to me was that they were sort of reinventing computer networking, and they were making all the mistakes that people in the computer industry had made. And since I had been doing a lot of work in the networking area, we'd go and, visit, company X, they'd describe this networking thing that they were doing. And just without any thought, I could tell them like the 25 things that were going to be complete disasters with that thing that they were doing. Mm-hmm. And I don't know whether that had any impact on any of them, but that particular story of, sort of repeating the disasters of the computer science industry, was there. And and one of the things we thought was, well, maybe we could do something useful here with like bringing them forward somewhat, but also at the same time, we learned a bunch of things from these, mostly consumer electronics companies. And, high on the list was that they viewed their relationship with the customer as sacred. They were never, ever willing to make trade-offs for safety. Right. So one of the things that had always made me nervous in the computer industry was that people were willing to make trade-offs in reliability to get performance. They want faster. It breaks a little more often because it's fast. Maybe you run it a little hotter than you should, or like the one that always blew my mind was the way that the folks at Cray supercomputers got their division to be really fast. Was that they did Newton-Raphson approximations. Uh-huh. And so, the bottom several bits of, A over B were essentially random numbers.
What could possibly go wrong?
What could go wrong? Right. And, just figuring out how to nail the bottom bit, how to make sure that, if you put a piece of toast in a toaster, It's not going to kill the customer. It's not going to burst into flames and burn the house down.
So those are, I guess, those are the principles that were inspiring. But how did, from the days of Java is called Oak because of a tree outside the window story that a lot of people know, how did it become this incredible, like, powerful language?
Well, so it was a bunch of things. So we, after all that, we started, the way that we decided that we could understand things better was by building a demo, building a prototype of something.
Got it.
So, kind of because it was easy and fun, we decided to build a control system for some home electronics, TV, VCR, that kind of stuff. And as we were building it, we sort of discovered that there were some things about standard practice in C programming that were really getting in the way. And it wasn't exactly, because we were writing all this C code and C++ code that we couldn't write it to do the right thing, but that one of the things that was weird in the group was that we had a guy whose his sort of top level job was he was a business guy. He was sort of an MBA kind of person, think about business plans and all of that. And, there were a bunch of things that were kind of, and we would talk about things that were going wrong and, or things that were going wrong, things that were going right. And, as we thought about, things like the requirements for security and safety, some low-level details in C, like naked pointers.
Yeah.
And, so back in the early 90s, it was well understood that, the number one source of like security vulnerabilities
is pointers.
Was just bugs.
Yeah.
Right. And it was like, 50, 60, 70% of all security vulnerabilities were bugs. And the vast majority of them were like buffer overflows.
Yeah. So you're like, we have to fix this.
We have to make sure that this cannot happen. And that was kind of the original thing for me was this cannot continue. And one of the things I find really entertaining this year was, I forget which rag published it, but there was this article that came out that was an examination. It was sort of the result of an examination of all the security vulnerabilities in Chrome. And Chrome is like a giant piece of C++ code. And 60 or 70% of all the security vulnerabilities were stupid pointer tricks. And I thought, it's 30 years later and we're still there.
Still there.
And we're still there. And, that's one of those, slap your forehead and just want to cry.
So would you attribute, or is that too much of a simplification, but would you attribute the creation of Java to to C pointers? An obvious problem.
Well, that was one of the trigger points.
Concurrency, you've mentioned.
Concurrency was a big deal. Because when you're interacting with people, the last thing you ever want to see is the thing like waiting. And, issues about the software development process, when faults happen, can you recover from them? What can you do to make it easier to create and eliminate complex data structures? What can you do to fix, one of the most common C problems, which is storage leaks, and its evil twin, the freed but still being used piece of memory. You know, you free something and then you keep using it.
Oh, yeah.
You know, so when I was originally thinking about that, I was thinking about that in terms of sort of safety and security issues. And one of the things I sort of came to understand was that it wasn't just about safety and security, but it was about developer velocity, right? So, and I got really religious about this because at that point I had spent an ungodly amount of my life hunting down mystery pointer bugs.
Yeah.
And, you know, like 2/3 of my time as a software developer was, you know, because the mystery pointer bugs tend to be the hardest to find because they tend to be very, very statistical. The ones that hurt, they're like a 1 in a million chance.
But nevertheless create an infinite amount of suffering.
Right. Because when you're doing 1 billion operations a second,
yeah,
you know, 1 in a million chance means it's going to happen. And so I got really religious about this thing about, you know, making it so that if something fails, it fails immediately and visibly. And, you know, one of the things that was a real attraction of Java to lots of development shops was that, you know, we get our code up and running twice as fast.
You mean like the entirety of the development process, debugging, all that kind of stuff?
Yeah. If so if you measure time from, you know, you first touch fingers to keyboard until you get your first demo out, not much different. But if you look from fingers touching keyboard to solid piece of software that you could release in production, it would be way faster.
And I think what people don't often realize, there's things that really slow you down, like hard to catch bugs probably is the thing that really slows down that.
It really slows things down. But also there were, you know, one of the things that you get out of object-oriented programming is a strict methodology about, you know, what are the interfaces between things, and being really clear about how parts relate to each other. And what that helps with is so many times what people do is they kind of like sneak around the side. So if you've built something and people are using it, and you say, well, okay, you know, I built this thing, you use it this way, and then you change it in such a way that it still does what you said it does. It just does it a little bit different. But then you find out that somebody out there was sneaking around the side.
Yep.
They had sort of tunneled in a back door, and this person, their code broke.
Yep. And
because they were sneaking through a side door. And normally the attitude is dummy. But a lot of times, you know, you can't get away. You can't just slap their hand and tell them to not do that.
Right.
Because, you know, it's, you know, somebody's, you know, some bank's, you know, account reconciliation system.
Right.
that, you know, some developer decided, oh, I'm lazy, you know, I'll just sneak through the back door.
And because the language allows it, I mean, you can't even get mad at them.
And so one of the things I did that on the one hand upset a bunch of people was that I made it so that you really couldn't go through back doors, right? So the whole point of that was to say, if you need, you know, if the interface here isn't right, the wrong way to deal with that is to go through a back door.
Yep.
The right way to deal with it is to walk up to the developer of this thing and say,
change the interface.
Fix it.
Yep.
Right. And so it was kind of like a social engineering thing.
Yeah.
And
it's brilliant.
And people ended up discovering that really made a difference. in terms of, and a bunch of this stuff, if you're just like screwing around writing your own, like, class project scale stuff, a lot of this stuff isn't quite so important because, you're, both sides of the interface. But, when you're building, sort of larger, more complex pieces of software that have a lot of people working on them, and especially when they like span organizations, having really having clarity about how that stuff gets structured, saves your life.
Yeah.
And, especially, there's so much software that is fundamentally untestable, until you do the real thing. Right.
It's better to write good code in the beginning as opposed to writing crappy code and then trying to fix it and like trying to scramble and figure out and through testing figure out where the bugs are.
Yeah, it's like which shortcut caused that rocket to not get where it was needed to go.
So I think one of the most beautiful ideas philosophically and technically is of a virtual machine, the Java virtual machine. Again, apologize to romanticize things, but how did the idea of the JVM come to be? How to you radical of an idea it is? Because it seems to me to be just a really interesting idea in the history of programming. And what is it?
So the Java virtual machine, you can think of it in different ways. Because it was carefully designed to have different ways of viewing it. So one view of it that most people don't really realize is there is that you can view it as sort of an encoding of the abstract syntax tree in reverse Polish notation. I don't know if that makes any sense at all. I could explain it and that would blow all of our time.
Yeah.
But the other way to think of it, and the way that it ends up being explained is that it's like the instruction set of an abstract machine that's designed such that you can translate that abstract machine to a physical machine. And the reason that that's important, so if you wind back to the early 90s when we were talking to all of these companies doing consumer electronics, and you talk to the purchasing people, there were interesting conversations with purchasing. So if you look at how these devices come together, they're sheet metal and gears and circuit boards and capacitors and resistors and stuff. And everything you buy has multiple sources, right? So you can buy a capacitor from here, you can buy a capacitor from there, and you've got kind of a market. So, so that you can actually get a decent price for a capacitor. But CPUs, and particularly in the early 90s, CPUs were all different and all proprietary. So if you used a chip from Intel, you had to be an Intel customer for till the end of time. Because if you wrote a bunch of software, when you wrote software using whatever technique you wanted, and C was particularly bad about this because there was a lot of properties of the underlying machine that came through. So
you were stuck. So the code you wrote, you were stuck to that particular machine.
You were stuck to that particular machine, which meant that they couldn't decide, Intel is screwing us. Mm-hmm. I'll start buying chips from, Bob's Better Chips. This drove like the purchasing people absolutely insane that they were welded into this decision, and they would have to make this decision before the first line of software was written.
It's funny that you're talking about the purchasing people. So that's one perspective, right? There's a lot of other perspectives that all probably hated this idea.
Right.
But from a technical aspect, just like the creation of an abstraction layer that's agnostic to the underlying machine from the perspective of the developer, I mean, that's brilliant.
Right. Well, and so that's like across the spectrum of providers of chips. But then there's also the time thing, because, as you went from one generation to the next generation to the next generation, they were all different, and you would often have to rewrite your software.
Oh, you mean generations of CPU of machines of different kinds?
Yeah. So like one of the things that sucked about a year out of my life was when Sun went from the Motorola 68010 processor to the 68020 processor. Mm-hmm. Then they had a number of differences, and one of them hit us really hard, and I ended up being the point guy on the worst case of where the new instruction cache architecture hurt us.
Well, okay, so I mean, when did this idea? I mean, okay, so yeah, you articulate a really clear fundamental problem in all of computing, but where do you get the guts to think we can actually solve this?
In our conversations with all of these vendors, these problems started to show up, and I kind of had this epiphany because it reminded me of a summer job that I had in grad school. So back in grad school, my thesis advisor, well, I had two thesis advisors for bizarre reasons. One of them was a guy named Raj Reddy. The other one was Bob Sproul. And Raj, I love Raj. I love both of them. But
Raj is amazing.
So the department had bought a bunch of like early workstations from a company called Three Rivers Computer Company. And Three Rivers Computer Company was a bunch of electrical engineers who wanted to do as little software as possible. So they knew that they'd need to have like compilers and an OS and stuff like that, and they didn't want to do any of that. And they wanted to do that for as close to zero money as possible. So what they did was they built a machine whose instruction set was literally the bytecode for UCSD Pascal, the P code. And so we had a bunch of software that was written for this machine. Mm-hmm. And for various reasons, the company wasn't doing terrifically well. We had all this software on these machines, and we wanted it to run on other machines, principally the VAX. And so Raj asked me if I could come up with a way to port all of this software
translate
from the PERC machines to VAXes. And I think what he had in mind was something that would translate from like Pascal to C, or Pascal to, actually at those times, pretty much you could translate to C or C. And if you didn't like translating to C, you could translate to C. There was, it's like the Henry Ford, any color you want, it's just so long as it's black. And And I went, that's really hard.
Fascinating.
And I noticed that, and I was like looking at stuff and I went, ooh, I bet I could rewrite the P code into VAX assembly code. And then I started to realize that, there were some properties of P code that made that really easy, some properties that made it really hard. So I ended up writing this thing that translated from P code on the Three Rivers perks into assembly code on the VAX. And I actually got higher quality code than the C compiler. And so everything just got really fast. It was really easy. It was like, wow, I thought that was a sleazy hack because I was lazy. And in actual fact, it worked really well. And I tried to convince people that was maybe a good thesis topic.
Yeah.
And nobody was it was like, nah.
Really? Yeah. It's kind of a brilliant idea, right?
Well,
maybe you weren't able to articulate the big picture of it.
Yeah. And I think, that was a key part. But so then, clock comes forward a few years and it's like, we got to be able to, if they want to be able to switch from, this weird microprocessor to that weird and totally different microprocessor, how do you do that? And I kind of went, oh, maybe by doing something kind of in the space of, Pascal P code, I could do like multiple translators. And I spent some time thinking about that and thinking about, what worked and what didn't work when I did the P code to VAX translator. And I talked to some of the folks who were involved in Smalltalk because Smalltalk also did a bytecode. And then I kind of went, yeah, I want to do that.
Yeah.
Because that actually, and it had the other advantage that you could either interpret it or compile it. And interpreters are usually easier to do, but not as fast as a compiler. So I figured, good, I can be lazy again. Sometimes I think that most of my good ideas are driven by laziness. And often I find that some of people's stupidest ideas are because they're insufficiently lazy. They just want to build something really complicated. And it's like, it doesn't need to be that complicated. Yeah. And so that's how that came out.
Mm-hmm.
And, but that also turned into kind of a almost a religious position on my part, which got me in several other fights. So like one of the things that was a real difference was the way that arithmetic worked. Once upon a time, there were, it wasn't always just 2's complement arithmetic. There were some machines that had 1's complement arithmetic, which was like almost anything built by CDC. Mm-hmm. And occasionally there were machines that were decimal arithmetic. And I was like, this is crazy. Pretty much 2's complement integer arithmetic has 1. So
let's just do that.
Just do that. One of the other places where there was a lot of variability was in the way that floating point behaved. And that was causing people throughout the software industry much pain because you couldn't do a numerical computing library that would work on CDC and then have it work on an IBM machine and work on a DEC machine. And as a part of that whole struggle, there had been this big body of work on floating point standards, And this thing emerged that came to be called IEEE 754, which is the floating point standard that pretty much has taken over the entire universe. And at the time I was doing Java, it had pretty much completed taking over the universe. There were still a few pockets of holdouts, but I was like, it's important to be able to say what 2 + 2 means.
Yeah.
And so I went that. And one of the ways that I got into fights with people was that there were a few machines that did not implement IEEE 754 correctly.
Well, of course, that's all short-term kind of fights. I think in the long term, I think this vision is won out.
Yeah, and I think it's and it worked out over time. I mean, the biggest fights were with Intel because they had done some strange things with rounding. They had done some strange things with their transcendental functions, which turned into a mushroom cloud of weirdness.
And in the name of optimization, but from the perspective of the developer, that's not good.
Well, their issues with transcendental functions were just stupid.
Okay, so that's not even a trade-off. That's just absolutely
They were doing range reduction for sine and cosine.
Oh wow! Okay.
Using a slightly wrong value for pi.
Got it. We're at 10 minutes, so in the interest of time, 2 questions. So one about Android and one about life. So one, I mean, we could talk for many more hours. I hope eventually we might talk again. So with your kind of early love or appreciation of the beauty of mathematics, do you see a parallel between that world and the world of programming?
Programming is all about logical structure, understanding the patterns that come out of computation, understanding it's often like, the path through the graph of possibilities to find a short route.
Meaning like find a short program that gets the job done, kind of thing. But so then on the topic of irrational numbers, do you see programming? You just painted it so cleanly. It's a little this trajectory to find like a nice little program, but do you see it as fundamentally messy? Maybe unlike mathematics?
I don't think of it as, you watch somebody who's good at math do math, and, often it's fairly messy. Sometimes it's kind of magical. When I was a grad student, one of the students, his name was Jim Sachs, he had this reputation of being sort of a walking, talking human theorem proving machine. And if you were having a hard problem with something, you could just accost him in the hall and say, Jim, and he would do this funny thing where he would stand up straight. His eyes would kind of defocus. He'd go, just like like something in today's movies. You could just, and then he'd straighten up and say n log n and walk away. and you'd go, well, okay, so n log n is the answer. How did he get there? By which time he's, down the hallway somewhere.
Yeah. It's just the oracle, the black box that just gives you the answer.
Yeah, and then you have to figure out the path from the question to the answer.
Let's go to the art of computer programming. In 1962, you set the table of contents for this magnum opus, right?
Yep.
It was supposed to be a single book with 12 chapters. Now today, what is it, 57 years later, you're in the middle of volume 4 of 7. And
in the middle of volume 4B is
4B.
more precisely.
Can I ask you for an impossible task, which is try to summarize the book so far, maybe by giving a little examples. So from the sorting and the search and the combinatorial algorithms, if you were to give a summary, a quick elevator summary.
Elevator, that's great. Yeah, right.
Well, depending how many floors there are in the building.
Yeah.
Course.
The first volume, called Fundamental Algorithms, talks about something that you can't, the stuff you can't do without. You have to know the basic concepts of what is a program, what is an algorithm, and it also talks about a low-level machine, so you can have some kind of an idea what's going on, and it has basic concepts of input, output, and subroutines, induction, right? Mathematical preliminary. So the thing that makes my book different from a lot of others is that I try to not only present the algorithm, but I try to analyze them, which means quantitatively I say not only does it work, but it works this fast. Mm-hmm. Okay, and so I need math for that. And then there's the standard way to structure data inside and represent information in the computer. So that's all volume 1. Volume 2 it's called semi-numerical algorithms, and here we're writing programs, but we're also dealing with numbers. Algorithms deal with any kinds of objects, but specific when there's objects are numbers, well then we have certain special paradigms that apply to things that involve numbers, and so there's arithmetic on numbers, and there's matrices full of numbers, there's random numbers, and there's power series full of numbers. There's different algebraic concepts that have numbers in structured ways.
And arithmetic in the way a computer would think about arithmetic. So floating point
arithmetic, high precision arithmetic, not only addition, subtraction, multiplication, but also comparison of numbers. So then volume 3 talks about.
I like that one. Sorting and search.
I
love sorting.
Right. So here, we're not dealing necessarily with numbers because you sort letters and other objects, and searching we're doing all the time with Google nowadays. But I mean, we have to find stuff. So again, algorithms that underlie all kinds of applications. None of these volumes is about a particular application, but the applications are examples of why people want to know about sorting, why people want to know about random numbers. So then volume 4 goes into combinatorial algorithm. This is where we have zillions of things to deal with, and here we keep finding cases where one good idea can make something go more than 1 million times faster, and we're dealing with problems that are probably never going to be solved efficiently, but that doesn't mean we give up on them, and we have this chance to have good ideas and go much faster on them. So that's combinatorial algorithms, and those are the ones that are. Yeah, I mean, you say sorting is most fun for you. Well,
it's true, it's fun,
but
too.
Combinatorial algorithms are the ones that I always enjoyed the most, because that's when my skill at programming had the most payoff. And the difference between an obvious algorithm that you think of first thing and a good and an interesting subtle algorithm that not so obvious, but runs circles around the other one. That's where computer science really comes in, and a lot of these combinatorial methods were found first in applications to artificial intelligence or cryptography, and in my case, I just liked them, and it was associated more with puzzles.
Do you like them most in the domain of graphs and graph theory?
Graphs are great because they're terrific models of so many things in the real world, right. and you throw in numbers on a graph, and you got a network, and so there you have many more things. So, but combinatorial in general is any arrangement of objects that has some kind of a higher structure, non-random structure. And okay, is it possible to put something together satisfying all these conditions? Like I mentioned arrows a minute ago. Is there a way to put these numbers on a bunch of boxes that are pointing to each other? Is that going to be possible at all?
That's volume 4.
That's volume 4.
What does the future hold?
Volume 4A was part 1. And what happened was in 1962, when I started writing down a table of contents, it wasn't going to be a book about computer programming in general. It was going to be a book about how to write compilers. And I was asked to write a book explaining how to write a compiler. And at that time, there were only a few dozen people in the world who had written compilers, and I happened to be one of them. So, and I also had some experience writing for like the campus newspaper and things like that. So I thought, okay, great. I'm the only person I know who's written a compiler but hasn't invented any new techniques for writing compilers, and all the other people I knew had super ideas, but I couldn't see that they would be able to write a book that would describe anybody else's ideas but their own. So I could be the journalist, and I could explain what all these cool ideas about compiler writing were. And then I started putting down, well, yeah, you need to have a chapter about data structures. You need to have some introductory material. I want to talk about searching, because a compiler writer has to look up the variables in a symbol table and find out which when you write the name of a variable in one place, it's supposed to be the same as the one you put somewhere else. So you need all these basic techniques, and I had to know some arithmetic and stuff. So I threw in these chapters, and I threw in a chapter on combinatorics because that was what I really enjoyed programming the most. But there weren't many algorithms known about combinatorial methods in 1962. So that was a kind of a short chapter, but it was sort of thrown in just for fun. And chapter 12 was going to be actual compilers, applying all the stuff in chapters 1 to 11 to make compilers. Well, okay, so that was my table of contents from 1962. And during the 70s, the whole field of combinatorics went through a huge explosion. People talk about a combinatorial explosion, and they usually mean by that the number of cases goes up. You change n to n plus 1, and all of a sudden your problem has gotten more than 10 times harder. But there was an explosion of ideas about combinatorics in the 70s to the point that, take 1975, I bet you more than half of all the journals of computer science were about combinatorial methods.
What's the art in the art of programming? Why is there, of the few words in the title, why is art one of them?
Yeah, well, that's what I wrote my Turing lecture about, and so when people talk about art, it really, what the word means is something that's not in nature. So when you have artificial intelligence, the art comes from the same root, saying that this is something that was created by human beings. And then it's gotten a further meaning, often of fine art, which adds this beauty to the mix and says, we have things that are artistically done, and this means not only done by humans, but also done in a way that's elegant and brings joy and has I guess Tolstoy versus Dostoevsky,
right?
Going back, but anyway, it's that part that says that it's done well as not only different from nature. In general, then art is what human beings are specifically good at, and when they say artificial intelligence, well, they're trying to mimic human beings.
But there's an element of fine art and beauty. You are one.
That's what I try to also say, that you can write a program and make a work of art. Mm-hmm.
So the graphical component, are you seeing the magic in the mechanism of creating that?
I think I went back and forth. As a student, we had an incredibly small budget of computer time that we could use. It was actually measured. I once got in trouble with one of my professors because I had overspent the department's budget. Mm-hmm. It's a different story. But so I actually wanted the efficient implementation because I also wanted to explore what would happen with a larger number of generations and a larger sort of size of the board. And so once the implementation was flawless, I would feed it different patterns, and then I think maybe there was a follow-up article where there were patterns that were like gliders, mm-hmm. patterns that repeated themselves after a number of generations, but translated one or two positions to the right or up or something like that. Mm-hmm. And there were, I remember things like glider guns. Well, you can Google Conway's Game of Life. It is still people still go awe and ooh over it.
For a reason, because it's not really well understood why. I mean, this is what Stephen Wolfram is obsessed about.
Okay.
He's just we don't have the mathematical tools to describe the kind of complexity that emerges in these kinds of systems. And the only way you can do it is to run it.
I'm not convinced that it's sort of a problem that lends itself to classic mathematical analysis.
No. And so one theory of how you create an artificial intelligence or an artificial being is you kind of have to, same with the game of life, you kind of have to create a universe and let it run. That creating it from scratch in a design way, coding up a Python program that creates a fully intelligent system may be quite challenging. That you might need to create a universe, just like the game of life is.
Well, you might have to experiment with a lot of different universes before there is a set of rules that doesn't essentially always just end up repeating itself in a trivial way.
Yeah, and Stephen Wolfram works with these simple rules. Says that it's kind of surprising how quickly you find rules that create interesting things. You shouldn't be able to, but somehow you do. And so maybe our universe is laden with rules that will create interesting things that might not look like humans, but emergent phenomena that's interesting may not be as difficult to create as we think.
Sure.
But C++, and all of that leads up to Python. Haskell too, and all that's before Python, MATLAB, these kind of different communities, different languages. So can you talk about that world? I know that sort of Python came out of ABC, which I actually never knew that language. I just, having researched this conversation, went back to ABC, mm-hmm. and it looks remarkably, it has a lot of annoying qualities, but underneath those, like all caps and so on, but underneath that, there's elements of Python that they're already there.
That's where I got all the good stuff.
All the good stuff. So, but in that world, you're swimming in these programming languages. Were you focused on just the good stuff in your specific circle? Or did you have a sense of what is everyone chasing? You said that every programming language is built to scratch an itch. Mm-hmm. Were you aware of all the itches in the community? And if not, or if yes, I mean, what itch were you trying to scratch with Python?
Well, I'm glad I wasn't aware of all the itches, because I would probably not have been able to do anything. I mean, if you're trying to solve every problem at once,
you'll solve nothing.
Well, yeah, it's too overwhelming. Yeah. And so I had a very, very focused problem. I wanted a programming language that sat somewhere in between shell scripting and C. And now, arguably, there is like one is higher level, one is lower level. And Python is sort of a language of an intermediate level, although it's still pretty much at the high level end. But I was thinking about much more about, I want a tool that I can use to be more productive as a programmer in a very specific environment. And I also had given myself a time budget for the development of the tool. And that was sort of about 3 months for both the design, like thinking through what are all the features of the language syntactically and semantically, and how do I implement the whole pipeline from parsing the source code to executing it.
So I think both with the timeline and the goals, it seems like productivity was at the core of it as a goal. So like for me in the 90s and the first decade of the 21st century, I was always doing machine learning, AI. Programming for my research was always in C++.
Wow.
And then the other people who are a little more mechanical engineering, electrical engineering are MATLAB-y. They're a little bit more MATLAB focused. Mm-hmm. Those are the world, and maybe a little bit Java too. But people who are more interested in emphasizing the object-oriented nature of things. So, but then in last 10 years or so, especially with the oncoming of neural networks and these packages that are built on Python to interface with neural networks, I switched to Python, and it's just, I've noticed a significant boost that I can't exactly, because I don't think about it, but I can't exactly put into words why I'm just much, much more productive. Just being able to get the job done much, much faster. So how do you think, whatever that qualitative difference is, I don't know if it's quantitative. It could be just a feeling. I don't know if I'm actually more productive, but how do you think about?
You probably are.
Yeah, well, that's right. I think there's elements. Let me just speak to one aspect that I think that was affecting my productivity. Is C++ was, I really enjoyed creating performant code and creating a beautiful structure where everything that, this kind of going into this, especially with the newer and newer standards of templated programming, of just really creating this beautiful formal structure, that I found myself spending most of my time doing that as opposed to parsing a file and extracting a few keywords or whatever the task I was trying to do. So what is it about Python? How do you think of productivity in general as you were designing it now, sort of through the last 3 decades? What do you think it means to be a productive programmer? And how did you try to design it into the language?
There are different tasks. And as a programmer, it's useful to have different tools available that sort of are suitable for different tasks.
Right.
So I still write C code. I still write shell code. But I write most of my things in Python. Why do I still use those other languages? Because sometimes the task just demands it. And, well, I would say most of the time the task actually demands a certain language, because the task is not write a program that solves problem X from scratch, but it's more like fix a bug in existing program X or add a small feature to an existing large program. But even if you're not constrained in your choice of language by context like that, there is still the fact that if you write it in a certain language, then you sort of you have this balance between how long does it take you to write the code, mm-hmm. and how long does the code run.
Right.
And when you're in in the phase of exploring solutions, you often spend much more time writing the code than running it, because every time you've run it, you see that the output is not quite what you wanted, and you spend some more time coding. And a language like Python just makes that iteration much faster, because there are fewer details. There is a large library. There are fewer details that you have to get right before your program compiles and runs. There are libraries that do all sorts of stuff for you, so you can sort of very quickly take a bunch of existing components, put them together, and get your prototype application running. Just like when I was building electronics, I was using a breadboard most of the time. So I had this like sprawled out circuit that if you shook it, it would stop working because it was not put together very well, but it functioned, and all I wanted was to see that it worked and then move on to the next schematic or design or add something to it. Once you've sort of figured out, oh, this is the perfect design for my radio or light sensor or whatever, then you can say, okay, how do we design a PCB for this? How do we solder the components in a small space? How do we make it so that it is robust against, say, voltage fluctuations or mechanical disruption? I mean, I know nothing about that when it comes to designing electronics, but I know a lot about that when it comes to writing code.
So the initial steps are efficient, fast, and there's not much stuff that gets in the way. But you're kind of describing from like Darwin described the evolution of species, right? You're observing of what is true about Python. Now, if you take a step back, if the act of creating languages is art, and you had 3 months to do it, initial steps, so you just specified a bunch of goals, sort of things that you observe about Python. Perhaps you had those goals, but how do you create the rules, the syntactic structure, the features that result in those? So I have in the beginning, and I have follow-up questions about through the evolution of Python too. But in the very beginning, when you're sitting there creating the lexical analyzer or whatever,
evolution was still a big part of it, because I said to myself, I don't want to have to design everything from scratch. I'm going to borrow features from other languages that I like.
Oh, interesting. So you basically, you first observe what you like.
Yeah. And so that's why if you're 17 years old and you want to sort of create a programming language, you're not going to be very successful at it, because you have no experience with other languages. Whereas I was in my, let's say, mid-30s, I had written parsers before, so I had worked on the implementation of ABC. I had spent years debating the design of ABC with its authors, with its designers. I had nothing to do with the design. It was designed fully as it was ended up being implemented when I joined the team. But so you borrow ideas and concepts and very concrete sort of local rules from different languages, like the indentation and certain other syntactic features from ABC, but I chose to borrow string literals and how numbers work from C and various other things.
So then if you take that further, so you've had this funny sounding, but I think surprisingly accurate, or at least practical title of benevolent dictator for life for for the last 3 decades or whatever. Or no, not the actual title, but functionally speaking. So you had to make decisions, design decisions. can you maybe let's take Python 2, so releasing Python 3 as an example.
Mm-hmm.
It's not backward compatible to Python 2 in ways that a lot of people know. So what was that deliberation, discussion, decision like? Yeah, what was the psychology of that experience? Do you regret any aspects of how that experience undergone?
Well, yeah. So it was a group process, really. At that point, even though I was BDFL in name, and certainly everybody sort of respected my position as the creator and the current sort of owner of the language design, I was looking at everyone else for feedback. Sort of Python 3.0 in some sense was sparked by other people in the community pointing out, oh, well, there are a few issues that sort of bite users over and over. Can we do something about that? Mm-hmm. And for Python 3, we took a number of those Python words, as they were called at the time, and we said, can we try to sort of make small changes to the language that address those words? Mm. And we had sort of, in the past, we had always taken backwards compatibility very seriously. And so many Python words in earlier versions had already been resolved because they could be resolved while maintaining backwards compatibility, or sort of using a very gradual path of evolution of the language in a certain area. And so we were stuck with a number of words that were widely recognized as problems, not like roadblocks, but nevertheless sort of things that some people trip over, and you know that that's always the same thing that people trip over when they trip. And we could not think of a backwards compatible way of resolving those issues.
But it's still an option to not resolve the issues, right?
And so, yes, for a long time, we had sort of resigned ourselves to, well, okay, the language is not going to be perfect in this way and that way and that way. And we sort of, certain of these, I mean, there are still plenty of things where you can say, well, that particular detail is better in Java or in R or in Visual Basic or whatever. Mm-hmm. And we're okay with that because, well, we can't easily change it. It's not too bad. We can do a little bit with user education, or we can have a static analyzer or warnings in the parser or something. But there were things where we thought, well, these are really problems that are not going away. They're getting worse in the future. We should do something about it.
Do something. But ultimately, there is a decision to be made, right?
Yes.
So was that the toughest decision in the history of Python you had to make as the benevolent dictator for life? Or if not, what are there, maybe even on the smaller scale, what was the decision where you were really torn up about?
Well, the toughest decision was probably to resign.
All right, let's go there. Hold on a second then. Let me just, because in the interest of time too, because I have a few cool questions for you. I mean, let's touch a really important one because it was quite dramatic and beautiful in certain kinds of ways. In July this year, 3 months ago, you wrote, now that PEP 572 is done, I don't ever want to have to fight so hard for a PEP and find that so many people despise my decisions. I would like to remove myself entirely from the decision process. I'll still be there for a while as an ordinary core developer, and I'll still be available to mentor people, possibly more available. But I'm basically giving myself a permanent vacation from being BDFL, benevolent dictator for life. And you all will be on your own. First of all, it's almost Shakespearean. I'm not going to appoint a successor. So what are you all going to do? Create a democracy, anarchy, a dictatorship, a federation? So that was a very dramatic and beautiful. set of statements. It's open-ended nature. Called the community to create a future for Python. There's this kind of beautiful aspect to it.
Wow.
So, what and dramatic, what was making that decision like? What was on your heart, on your mind? Stepping back now, a few months later, take me through your mind.
I'm glad you like the writing because it was actually written pretty quickly. It was literally something like, after months and months of going around in circles, I had finally approved PEP 572, which I had a big hand in its design, although I didn't initiate it originally. I sort of gave it a bunch of nudges in a direction that would be better for the language.
Sorry, just to ask, is async IO that's the one or no?
No, PEP 572 was actually a small feature which is assignment expressions.
Oh, assignment expressions. Okay.
That had been. There was just a lot of debate where a lot of people claimed that they knew what was Pythonic and what was not Pythonic, and they knew that this was going to destroy the language. This was like a violation of Python's most fundamental design philosophy. And I thought that was all bullshit because I was in favor of it. And I would think I know something about Python's design philosophy. So I was really tired and also stressed of that thing. And literally, after sort of announcing I was going to accept it, a certain Wednesday evening, I had finally sent the email, it's accepted. Now let's just go implement it. So I went to bed feeling really relieved. That's behind me. And I wake up Thursday morning, 7 a.m., and I think, well, that was the last one that's going to be such a terrible debate, and that's going to be that's the last time that I let myself be so stressed out about a PEP decision.
Yeah.
I should just resign. I've been sort of thinking about retirement for half a decade. I've been joking and sort of mentioning retirement, sort of telling the community some point in the future, I'm going to retire. Yeah. Don't take that FL part of my title too literally. And I thought, okay, this is it. I'm done. I had the day off. I wanted to have a good time with my wife. We were going to a little beach town nearby. And in, I think, maybe 15, 20 minutes, I wrote that thing that you just called Shakespearean. And the funny thing is,
I'm gonna get so much crap for calling it Shakespearean.
I didn't even realize what a monumental decision it was, because 5 minutes later, I read a link to my message back on Twitter, where people were already discussing on Twitter, Guido resigned as the BDFL. And I had posted it on an internal forum that I thought was only read by core developers. Mm-hmm. So I thought I would at least have one day before the news would sort of get out.
The on your own aspect had also an element of it was quite a powerful element of the uncertainty that lies ahead. But can you also just briefly talk about, like, for example, I play guitar as a hobby for fun. And whenever I play, people are super positive. They're super friendly. They're like, this is awesome. This is great. But sometimes I enter as an outside observer, I enter the programming community, and there seems to sometimes be camps on whatever the topic. And the two camps, the two or plus camps, are often pretty harsh at criticizing the opposing camps. As an onlooker, I may be totally wrong on this.
Yeah, holy wars are sort of a favorite activity in the programming community.
And what is the psychology behind that? Is that okay for a healthy community to have? Is that a productive force ultimately for the evolution of a language,
Well, if everybody is patting each other on the back and never telling the truth,
yes,
it would not be a good thing. I think there is a middle ground where sort of being nasty to each other is not okay, but there is a middle ground where there is healthy ongoing criticism and feedback that is very productive. And you mean at every level you see that. I mean, someone proposes to fix a very small issue in a code base. Chances are that some reviewer will sort of respond by saying, well, actually, you can do it better the other way.
Right.
When it comes to deciding on the future of the Python core developer community, we now have, I think, 5 or 6 competing proposals for a constitution.
So that future, do you have a fear of that future? Do you have a hope for that future?
I'm very confident about that future. By and large, I think that the debate has been very healthy and productive. And I actually, when I wrote that resignation email, I knew that Python was in a very good spot and that the Python core development community, the group of 50 or 100 people who sort of write or review most of the code that goes into Python, those people get along very well most of the time. A large number of different areas of expertise are represented. Different levels of experience in the Python core dev community, different levels of experience completely outside it, in software development in general, large systems, small systems, embedded systems. So I felt okay resigning because I knew that the community can really take care of itself.
And out of a grab bag of future feature developments, let me ask if you can comment maybe on all very quickly. Concurrent programming, parallel computing, async IO. These are things that people have expressed hope, complained about, whatever, have discussed on Reddit. Async IO, so the parallelization in general. Packaging, I was totally clueless on this. I just used pip to install stuff, but apparently there's pip-env, poetry, there's these dependency packaging systems that manage dependencies and so on. They're emerging, and there's a lot of confusion about what's the right thing to use. Then also functional programming, the ever, are we going to get more functional programming or not? This kind of idea, and of course the GIL as the connected to the parallelization, I suppose, the global interpreter lock problem. Can you just comment on whichever you want to comment on?
Well, let's take the GIL and parallelization and async IO as one topic. Mm-hmm. I'm not that hopeful that Python will develop into a sort of high concurrency, high parallelism language. That's sort of the way the language is designed, the way most users use the language, the way the language is implemented, all make that a pretty unlikely future.
So you think it might not even need to, really, the way people use it? It might not be something that should be of great concern.
I think async IO is a special case because it sort of allows overlapping IO and only IO. And that is a sort of best practice of supporting very high throughput IO, many connections per second. I'm not worried about that. I think async IO will evolve. There are a couple of competing packages. We have some very smart people who are sort of pushing us in sort of to make async IO better. Parallel computing, I think that Python is not the language for that. There are ways to work around it, but you can't expect to write an algorithm in Python and have a compiler automatically parallelize that. What you can do is use a package like NumPy, and there are a bunch of other very powerful packages that sort of use all the CPUs available, because you tell the package, here's the data, here's the abstract operation to apply over it, go at it, and then we're back in the C++ world. But those packages are themselves implemented usually in C++.
That's right. That's where TensorFlow and all these packages come in, where they parallelize across GPUs, for example. They take care of that for you. So in terms of packaging, can you comment on the future of packaging in Python?
Packaging has always been my least favorite topic. It's a really tough problem, because the OS and the platform want to own packaging, but their packaging solution is not specific to a language. Like, if you take Linux, there are two competing packaging solutions for Linux, or for Unix in general, but they all work across all languages. And several languages like Node, JavaScript, and Ruby and Python all have their own packaging solutions that only work within the ecosystem of that language. Well, what should you use? That is a tough problem. My own approach is I use the system packaging system to install Python, and I use the Python packaging system then to install third-party Python packages. That's what most people do. 10 years ago, Python packaging was really a terrible situation. Nowadays, pip is the future. There is a separate ecosystem for numerical and scientific Python based on Anaconda. Those two can live together. I don't think there is a need for more than that.
Great.
So that's packaging.
That's well, at least for me, that's where I've been extremely happy. I didn't even know this was an issue until it was brought up. Well, in the interest of time, let me sort of skip through a million other questions I have. So I watched the 5.5 hour oral history that you've done with the Computer History Museum. And the nice thing about it, it gave this, because of the linear progression of the interview, it gave this feeling of a life, a life well lived with interesting things in it. Sort of I would say, a good spend of this little existence we have on Earth. So outside of your family, looking back, what about this journey are you really proud of? Are there moments that stand out, accomplishments, ideas? Is it the creation of Python itself that stands out as a thing that you look back and say, damn, I did pretty good there?
Well, I would say that Python is definitely the best thing I've ever done. And I wouldn't sort of say just the creation of Python, but the way I sort of raised Python like a baby. I didn't just conceive a child, but I raised a child. And now I'm setting the child free in the world. And I've set up the child to sort of be able to take care of himself. And I'm very proud of that.
And as the announcer of Monty Python's Flying Circus used to say, and now for something completely different, do you have a favorite Monty Python moment, or a moment in Hitchhiker's Guide or any other literature, show, movie that cracks you up when you think about it?
Oh, you can always play me the dead parrot sketch.
Oh, that's brilliant.
Yeah.
That's my favorite as well.
It's pushing up the daisies.
Okay. Guido, thank you so much for talking with me today. Appreciate
Lex,
it.
this has been a great conversation.
good enough.
But what do you think the future of programming looks like? What do you hope the future of programming looks like if we zoom in on the computational fields, on data science, on machine learning?
I hope Swift is successful because the goal of Swift, the way Chris Lattner describes it, is to be infinitely hackable. And that's what I want. I want something where me and the people I do research with and my students can look at and change everything from top to bottom. There's nothing mysterious and magical and inaccessible. Unfortunately, with Python, it's the opposite of that because Python's so slow. It's extremely unhackable. You get to a point where it's like, okay, from here on down it's C. So your debugger doesn't work in the same way. Your profiler doesn't work in the same way. Your build system doesn't work in the same way. It's really not very hackable at all.
What's the part you would like to be hackable? Is it for the objective of optimizing training of neural networks, inference of neural networks? Is it performance of the system? Or is there some non-performance related, just
It's everything.
idea?
I mean, in the end, I want to be productive as a practitioner. So that means that, so like at the moment, our understanding of deep learning is incredibly primitive. There's very little we understand. Most things don't work very well, even though it works better than anything else out there.
Right.
There's so many opportunities to make it better. So you look at any domain area, like, I don't know, speech recognition with deep learning or natural language processing classification with deep learning or whatever. Every time I look at an area with deep learning, I always see like, oh, it's terrible. There's lots and lots of obviously stupid ways to do things that need to be fixed. So then I want to be able to jump in there and quickly experiment and make them better.
You think the programming language is has a role in that?
Huge role, yeah. So currently, Python has a big gap in terms of our ability to innovate, particularly around recurrent neural networks and natural language processing, because it's so slow. The actual loop where we actually loop through words, we have to do that whole thing in CUDA C. So we actually can't innovate with the kernel, the heart of that most important algorithm. And it's just a huge problem. And this happens all over the place. So we hit, research limitations. Another example, convolutional neural networks, which are actually the most popular architecture for lots of things, maybe most things in deep learning. We almost certainly should be using sparse convolutional neural networks, but only like 2 people are, because to do it, you have to rewrite all of that CUDA C level stuff. And just researchers and practitioners don't. So like there's just big gaps in like what people actually research on, what people actually implement because of the programming language problem.
So you think it's just too difficult to write in CUDA C, that a higher level programming language like Swift should enable the easier fooling around creative stuff with RNNs or with sparse convolution neural networks?
Kind of.
Who's at fault? Who's in charge of making it easy for a researcher to play around?
I mean, no one's at fault. It's just nobody's got around to it yet, it's hard, right? And I mean, part of the fault is that we ignored that whole APL kind of direction. Nearly everybody did for 60 years, 50 years. But recently, people have been starting to reinvent pieces of that and kind of create some interesting new directions in the compiler technology. So the place where that's particularly happening right now is something called MLIR, which is something that, again, Chris Lattner, the Swift guy, is leading. And because it's actually not going to be Swift on its own that solves this problem, because the problem is that currently writing a acceptably fast, GPU program is too complicated, regardless of what language you use.
Right.
And that's just because if you have to deal with the fact that I've got, 10,000 threads and I have to synchronize between them all, and I have to put my thing into grid blocks and think about warps and all this stuff, it's just so much boilerplate that to do that well, you have to be a specialist at that, and it's going to be a year's work to, optimize that algorithm in that way. But with things like tensor comprehensions and tile and MLIR and TVM, there's all these various projects which are all about saying, let's let people create like domain-specific languages for tensor computations. These are the kinds of things we do generally on the GPU for deep learning, and then have a compiler which can optimize that tensor computation. A lot of this work is actually sitting on top of a project called Halide, which is a mind-blowing project where they came up with such a domain-specific language. In fact, two. One domain-specific language for expressing this is what my tensor computation is, and another domain-specific language for expressing this is the kind of the way I want you to structure the compilation of that, like do it block by block and do these bits in parallel. And they were able to show how you can compress the amount of code by 10x compared to optimized GPU code and get the same performance. So that's like, so these other things are kind of sitting on top of that kind of research, and MLIR is pulling a lot of those best practices together. And now we're starting to see work done on making all of that directly accessible through Swift, so that I could use Swift to kind of write those domain-specific languages. And hopefully we'll get then Swift CUDA kernels written in a very expressive and concise way that looks a bit like J and APL, and then Swift layers on top of that, and then a Swift UI on top of that. And, you know, it'll be so nice if we can get to that point.
Now, does it all eventually boil down to CUDA and NVIDIA GPUs?
Unfortunately, at the moment it does, but one of the nice things about MLIR, if AMD ever gets their act together, which they probably won't, is that they or others could write MLIR backends for other GPUs or other tensor computation devices, of which today there are an increasing number, like GraphCore or Vertex AI or whatever. So, yeah, being able to target lots of backends would be another benefit of this. And the market really needs competition, because at the moment, NVIDIA is massively overcharging for their kind of enterprise class cards, because there is no serious competition, because nobody else is doing the software properly.
In the cloud, there is some competition, right? But
not really, other than TPUs, perhaps.
TPUs,
but TPUs are almost unprogrammable at the moment.
So you can't. The TPUs has the same problem that you can't.
It's even worse. So TPUs, Google actually made an explicit decision to make them almost entirely unprogrammable, because they felt that there was too much IP in there, and if they gave people direct access to program them, people would learn their secrets. So you can't actually directly program the memory in a TPU. You can't even directly like create code that runs on and that you look at on the machine that has the GPU. It all goes through a virtual machine. So all you can really do is this kind of cookie cutter thing of like plug in high level stuff together, which is just super tedious and annoying and totally unnecessary.
So what was so you've used and studied quite a few programming languages. Can you give an overview of what you've used? What are the pros and cons of each?
Well, my favorite programming environment almost certainly was Microsoft Access back in like the earliest days. So that was Visual Basic for applications, which is not a good programming language, but the programming environment was fantastic. It's like the ability to create, user interfaces and tie data and actions to them and create reports and all that. I've never seen anything as good. There's things nowadays like Airtable, which are like small subsets of that, which people love for good reason, but unfortunately nobody's ever achieved anything like that.
What is that? If you could pause on that for a second.
Oh, Access?
Is it
fundamentally
a database?
It was a database program that Microsoft produced, part of Office, and it kind of withered, but basically it lets you in a totally graphical way create tables and relationships and queries and tie them to forms and set up, event handlers and calculations. And it was very complete powerful system designed for not massive scalable things, but for like useful little applications that I loved.
So what's the
quickly
connection
building.
between Excel and Access?
So very close. So Access kind of was the relational database equivalent, if you like. So people still do a lot of that stuff that should be in Access in Excel because they know it. Excel's great as well. So, but it's just not as rich a programming model as VBA combined with a relational database. So I've always loved relational databases, but today programming on top of a relational database is just a lot more of a headache. You generally either need to kind of, you need something that connects, that runs some kind of database server, unless you use SQLite, which has its own issues. Then you kind of often, if you want to get a nice programming model, you'll need to like add an ORM on top. And then, I don't know, there's all these pieces to tie together. And it's just a lot more awkward than it should be. There are people that are trying to make it easier. So in particular, I think of F#, Don Syme, who him and his team have done a great job of making something like a database appear in the type system. So you actually get like tab completion for fields and tables and stuff like that. Anyway, so that was so like that whole VBA Office thing, I guess, was a starting point, which I still miss. And I got into standard Visual Basic, which...
Well, that's interesting, just to pause on that for a second. It's interesting that you're connecting programming languages to the ease of management of data.
Yeah.
So in your use of programming languages, you always had a love and a connection with data.
I've always been interested in doing useful things for myself and for others, which generally means getting some data and doing something with it and putting it out there again. So that's been my interest throughout. So I also did a lot of stuff with AppleScript back in the early days. So it's kind of nice being able to get the computer and computers to talk to each other and to do things for you. And then I think that the programming language I most loved then would have been Delphi, which was Object Pascal, created by Anders Helsberg, who previously did Turbo Pascal and then went on to create .NET and then went on to create TypeScript. Delphi was amazing because it was like a compiled, fast language that was as easy to use as Visual Basic.
Delphi, what is it similar to in more modern languages?
Visual Basic.
Visual Basic.
Yeah, but a compiled fast version. So I'm not sure there's anything quite like it anymore. If you took like C# or Java and got rid of the virtual machine and replaced it with something you could compile a small type binary. I feel like it's where Swift could get to with the new Swift UI and the cross-platform development going on. Like that's one of my dreams, is that we'll hopefully get back to where Delphi was. There is actually a free Pascal project nowadays called Lazarus, which is also attempting to kind of recreate Delphi. So they're making good progress.
So, okay, Delphi, that's one of your favorite programming languages.
Or at least programming environments. Again, I'd say Pascal's not a nice language. If you wanted to know specifically about what languages I like, I would definitely pick J as being an amazingly wonderful language.
What's J?
J, are you aware of APL?
I am not,
okay,
except from doing a little research on work you've done.
Okay, so not at all surprising you're not familiar with it because it's not well known, but it's actually one of the main families of programming languages going back to the late 50s, early 60s. So there was a couple of major directions. One was the kind of Lambda calculus Alonzo Church direction, which I guess kind of Lisp and Scheme and whatever, which has a history going back to the early days of computing. The second was the kind of imperative /OO, algo, Simula, going on to C, C++, so forth. There was a third, which are called array-oriented languages, which started with a paper by a guy called Ken Iverson, which was actually a math theory paper, not a programming paper. It was called Notation as a Tool for Thought. And it was the development of a new type of math notation. And the idea is that this math notation was much more flexible, expressive, and also well-defined than traditional math notation, which is none of those things. Math notation is awful. And so he actually turned that into a programming language. And because this was the early 50s, late 50s, all the names were available. So he called his language a programming language, or APL.
APL, wow.
So APL is a implementation of notation as a tool for thought, by which he means math notation. And Ken and his son went on to do many things, but eventually they actually produced a new language that was built on top of all the learnings of APL, and that was called J. And J is the most expressive, composable language of, beautifully designed language I've ever seen.
Does it have object-oriented components? Does it have that kind of thing? Or
Not really. It's an array-oriented language. It's the third path.
Are you saying array?
Array-oriented, yeah.
So what does it mean to be array-oriented?
So array-oriented means that you generally don't use any loops, but the whole thing is done with kind of a extreme version of broadcasting, if you're familiar with that NumPy/Python concept. So you do a lot with one line of code. It looks a lot like math notation.
So it's basically
highly compact. And the idea is that you can because you can do so much with one line of code, a single screen of code is very unlikely you very rarely need more than that to express your program. And so you can kind of keep it all in your head, and you can kind of clearly communicate it. It's interesting. The APL created two main branches, K and J. J is this kind of like open source niche community of crazy enthusiasts like me. And then the other path, K, was fascinating. It's an astonishingly expensive programming language, which many of the world's most ludicrously rich hedge funds use. So the entire K machine is so small it sits inside level 3 cache on your CPU, and it easily wins every benchmark I've ever seen in terms of data processing speed. But you don't come across it very much because it's like $100,000 per CPU to run it.
Right.
But it's like this path of programming languages is just so much more powerful in every way than the ones that almost anybody uses every day.
So it's all about computation. It's really focusing
pretty heavily focused on computation. I mean, so much of programming is data processing by definition, and so there's a lot of things you can do with it. But yeah, there's not much work being done on making like user interface toolkits or whatever. I mean, there's some, but they're not great.
At the same time, you've done a lot of stuff with Perl and Python.
Yeah.
So where does that fit into the picture of J and K and APL and?
Well, it's just much more pragmatic. Like in the end, you kind of have to end up where the libraries are. Because to me, my focus is on productivity. I just want to get stuff done and solve problems. So Perl was great. I created an email company called Fastmail, and Perl was great because back in the late 90s, early 2000s, it just had a lot of stuff it could do. I still had to write my own monitoring system and my own web framework, my own whatever, because like none of that stuff existed. But it was a super flexible language to do that in.
And you used Perl for Fastmail. You used it as a backend, so everything was written in Perl.
Yeah, everything was Perl.
Why do you think Perl hasn't succeeded or hasn't dominated the market, where Python really takes over a lot of the tasks?
Well, I mean, Perl did dominate. It was
for a time
everything, everywhere. But then the guy that ran Perl, Larry Wall, kind of just didn't put the time in anymore. And no project can be successful if there isn't, particularly one that started with a strong leader that loses that strong leadership. So then Python has kind of replaced it. Python is a lot less elegant language in nearly every way, but it has the data science libraries, and a lot of them are pretty great. So I kind of use it because it's the best we have, but it's definitely not.
70% of our time on core business, 20% on adjacent business, and 10% on other. Mm-hmm. And he proved mathematically, of course, he's a brilliant mathematician, that you needed that 10%, right, to make the sum of the growth work. And it turns out he was right.
So getting into the world of artificial intelligence, you've talked quite extensively and effectively to the impact in the near term, the positive impact of artificial intelligence, whether it's especially machine learning in medical applications, in education, and just making information more accessible, right? In the AI community, there is a kind of debate. So there's this shroud of uncertainty as we face this new world with artificial intelligence in it. And there's some people, like Elon Musk, you've disagreed on, at least on the degree of emphasis he places on the existential threat of AI. So I've spoken with Stuart Russell, Max Tegmark, who share Elon Musk's view, and Yoshio Bengio, Steven Pinker, who do not. And so there's a lot of very smart people who are thinking about this stuff, disagreeing, which is really healthy, of course. So what do you think is the healthiest way for the AI community to, and really for the general public to think about AI and the concern of the technology being mismanaged in some kind of way?
So the source of education for the general public has been robot killer movies.
Right.
And Terminator, et cetera. And the one thing I can assure you we're not building are those kinds of solutions. Furthermore, if they were to show up, someone would notice and unplug them, right? So as exciting as those movies are, and they're great movies, were the killer robots to start, we would find a way to stop them, right? Mm-hmm. Yeah. So I'm not concerned about that. And much of this has to do with the time frame of conversation. Right. So you can imagine a situation 100 years from now, mm-hmm. when the human brain is fully understood and the next generation of brilliant MIT scientists have figured all this out. Mm-hmm. We're going to have a large number of ethics questions, right, around science and thinking and robots and computers and so forth and so on. So it depends on the question of the time frame. In the next 5 to 10 years, we're not facing those questions. What we're facing in the next 5 to 10 years is how do we spread this disruptive technology as broadly as possible to gain the maximum benefit of it. The primary benefit should be in healthcare and in education. Mm-hmm. Healthcare because it's obvious. We're all the same, even though we somehow believe we're not. As a medical matter, the fact that we have big data about our health will save lives, allow us to deal with skin cancer and other cancers, ophthalmological problems. There's people working on psychological diseases and so forth using these techniques. I can go on and on. Mm-hmm. The promise of AI in medicine is extraordinary. There are many, many companies and startups and funds and solutions, and we will all live much better for that. The same argument in education. Can you imagine that for each generation of child and even adult, you have a tutor educator that's AI-based, mm-hmm. that's not a human but is properly trained, that helps you get smarter, helps you address your language difficulties or your math difficulties or what have you? Why don't we focus on those two? The gains societally of making humans smarter and healthier are enormous, right? And those translate for decades and decades, and we'll all benefit from them. There are people who are working on AI safety, which mm-hmm. is the issue that you're describing. And there are conversations in the community that should there be such problems, what should the rules be like? Mm-hmm. Google, for example, has announced its policies with respect to AI safety, which I certainly support, and I think most everybody would support. And they make sense, right? So it helps guide the research. but the killer robots are not arriving this year, and they're not even being built.
And on that line of thinking, you said the time scale. In this topic or other topics, have you found it useful on the business side or the intellectual side to think beyond 5-10 years, to think 50 years out? Has it ever been useful or productive?
In our industry, there are essentially no examples of 50-year predictions that have been correct. Let's review AI, right? AI, which was largely invented here at MIT and a couple of other universities in the 1956, 1957, 1958, the original claims were a decade or two. And when I was a PhD student, I studied AI a bit, and it entered, during my looking at it, a period which is known as AI winter, which went on for about 30 years, which is a whole generation of scientists and a whole group of people who didn't make a lot of progress because the algorithms had not improved and the computers had not improved. It took some brilliant mathematicians, starting with a fellow named Jeff Hinton at Toronto and Montreal, who basically invented this deep learning model, which powers us today. The seminal work there was 20 years ago. And in the last 10 years, it's become popularized. So think about the time frames for that level of discovery. It's very hard to predict. Many people think that we'll be flying around in the equivalent of flying cars. Who knows? My own view, if I want to go out on a limb, is to say that when we know a couple of things about 50 years from now. We know that there'll be more people alive. We know that we'll have to have platforms that are more sustainable because the Earth is limited, in the ways we all know, and that the kind of platforms that are going to get built will be consistent with the principles that I've described. They will be much more empowering of individuals. They'll be much more sensitive to the ecology because they have to be. They just have to be. I also think that humans are going to be a great deal smarter. And I think they're going to be a lot smarter because of the tools that I've discussed with you. And of course, people will live longer. Life extension is continuing apace. A baby born today has a reasonable chance of living to 100, right? Which is pretty exciting. It's well past the 21st century, so we better take care of them.
And you mentioned an interesting statistic on some very large percentage, 60, 70% of people may live in cities.
Today, more than half the world lives in cities. And one of the great stories of humanity in the last 20 years has been the rural to urban migration. This has occurred in the United States. It's occurred in Europe. It's occurring in Asia, and it's occurring in Africa. When people move to cities, the cities get more crowded. But believe it or not, their health gets better. Their productivity gets better. Their IQ and educational capabilities improve. So it's good news that people are moving to cities, but we have to make them livable and safe.
So you first of all, you are, but you've also worked with some of the greatest leaders in the history of tech. What insights do you draw from the difference in leadership styles of yourself, Steve Jobs, Elon Musk, Larry Page, now the new CEO, Sundar Pichai, and others, from the, I would say, calm sages to the mad geniuses?
One of the things that I learned as a young executive is that there's no single formula for leadership. They try to teach one, but that's not how it really works. There are people who just understand what they need to do and they need to do it quickly. Those people are often entrepreneurs. They just know and they move fast. There are other people who are systems thinkers and planners. That's more who I am. Somewhat more conservative, more thorough in execution, a little bit more risk averse. There's also people who are sort of slightly insane, right? In the sense that they are emphatic and charismatic and they feel it and they drive it and so forth. There's no single formula to success. There is one thing that unifies all of the people that you named, which is repository that GitHub represents and that open source libraries represent, is an enormous bank of knowledge of all of the people who are doing that. And one of the lessons that I learned at Google was that the world is a very big place and there's an awful lot of smart people. And an awful lot of them are underutilized. So here's an opportunity, for example, building parts of programs, building new ideas to contribute to the greater of society.
So in that moment in the 70s, the inspiring moment where there was nothing and then you created something through programming, that magical moment, So in 1975, I think, you've created a program called Lex, which I especially like because my name is Lex. So thank you. Thank you for creating a brand that established a reputation that's long-lasting, reliable, and has a big impact on the world and still used today. So thank you for that. But more seriously, in that time, in the 70s, as an engineer, personal computers were being born. Do you think you would be able to predict the 80s, 90s, and the aughts of where computers would go?
I'm sure I could not and would not have gotten it right. I was the beneficiary of the great work of many, many people who saw it clearer than I did. With Lex, I worked with a fellow named Michael Lesk, who was my supervisor, and he essentially helped me architect and deliver a system that's still in use today. After that, I worked at Xerox Palo Alto Research Center, where the Alto was invented. And the Alto is the predecessor of the modern personal computer, or Macintosh and so forth. And the Altos were very rare, and I had to drive an hour from Berkeley to go use them. But I made a point of skipping classes and doing whatever it took to have access to this extraordinary achievement. I knew that they were consequential. What I did not understand was scaling. I did not understand what would happen when you had 100 million as opposed to 100. And so since then, and I have learned the benefit of scale, I always look for things which are going to scale to platforms, right? So mobile phones, Android, all those things. The world is there are many, many people in the world. People really have needs. They really will use these platforms, and you can build big businesses on top of them.
So it's interesting. So when you see a piece of technology, now you think, what will this technology look like when it's in the hands of 1 billion people?
That's right. So an example would be that the market is so competitive now that if you can't figure out a way for something to have 1 million users or 1 billion users, it probably is not going to be successful because something else will become the general platform and your idea will become a lost idea or a specialized service with relatively few users. So it's a path to generality. It's a path to general platform use. It's a path to broad applicability. Now, there are plenty of good businesses that are tiny, so luxury goods, for example. But if you want to have an impact at scale, you have to look for things which are of common value, common pricing, common distribution, and solve common problems. The problems that everyone has. And by the way, people have lots of problems. Information, medicine, health, education, and so forth. Work on those problems.
Mm-hmm. Like you said, you're a big fan of the middle class.
Because there's so many of them.
There's so many of them.
By definition.
So any product, anything that has a huge impact that improves their lives is a great business decision, and it's just good for society.
And there's nothing wrong with starting off in the high end as long as you have a plan to get to the middle class. There's nothing wrong with starting with a specialized market in order to learn and to build and to fund things. So you start a luxury market to build a general purpose market. But if you define yourself as only a narrow market, someone else can come along with a general purpose market that can push you to the corner, can restrict the scale of operation, can force you to be a lesser impact than you might be. So it's very important to think in terms of broad businesses and broad impact, even if you start in a little corner somewhere.
So as you look to the 70s, but also in the decades to come, and you saw computers, did you see them as tools, or was there a little element of another entity? I remember a quote saying AI began with our dream to create the gods. Is there a feeling when you wrote that program that you were creating another entity, giving life to something?
I wish I could say otherwise, but I simply found the technology platforms so exciting. That's what I was focused on. I think the majority of the people that I've worked with, and there are a few exceptions, Steve Jobs being an example, really saw this as a great technological play. I think relatively few of the technical people understood the scale of its impact. So I used NCP, which is a predecessor to TCP/IP. It just made sense to connect things. We didn't think of it in terms of the internet and then companies and then Facebook and then Twitter and then, politics and so forth. We never did that build. We didn't have that vision. And I think most people, it's a rare person who can see compounding at scale. Most people can see, if you ask people to predict the future, they'll give you an answer of 6 to 9 months or 12 months. because that's about as far as people can imagine. But there's an old saying, which actually was attributed to a professor at MIT a long time ago, that we overestimate what can be done in 1 year, and we underestimate what can be done in a decade. And there's a great deal of evidence that these core platforms at hardware and software take a decade, right? So think about self-driving cars. Self-driving cars were thought about in the 90s. There were projects around them. The first DARPA Grand Challenge was roughly 2004. So that's roughly 15 years ago. And today we have self-driving cars operating in a city in Arizona, right? So 15 years. And we still have a ways to go before they're more generally available.
So you've spoken about the importance, you just talked about predicting into the future. You've spoken about the importance of thinking 5 years ahead and having a plan for those 5 years.
Yeah, the way to say it is that almost everybody has a 1 year plan. Almost no one has a proper 5 year plan. And the key thing to having a 5 year plan is to having a model for what's going to happen under the underlying platforms. So here's an example. Moore's law as we know it, the thing that powered improvements in CPUs, has largely halted in its traditional shrinking mechanism because the costs have just gotten so high. And it's getting harder and harder. But there's plenty of algorithmic improvements and specialized hardware improvements. So you need to understand the nature of those improvements and where they'll go in order to understand how it will change the platform. In the area of network connectivity, what are the gains that are going to be possible in wireless? It looks like there's an enormous expansion of wireless connectivity at many different bands, right? And that we will primarily, historically, I've always thought that we were primarily going to be using fiber, but now it looks like we're going to be using fiber plus very powerful high bandwidth, sort of short distance connectivity to bridge the last mile, right? That's an amazing achievement. If you know that, then you're going to build your systems differently. By the way, those networks have different latency properties, right? Because they're more symmetric. The algorithms feel faster for that reason.
And so when you think about whether it's a fiber or just technologies in general, so there's this Barbara Wooden poem or quote that I really like. It's from the champions of the impossible rather than the slaves of the possible that evolution draws its creative force. So in predicting the next 5 years, I'd like to talk about the impossible and the possible.
Well, and again, one of the great things about humanity is that we produce dreamers.
Right.
Right. We literally have people who have a vision and a dream. They are, if you will, disagreeable in the sense that they disagree with they disagree with what the sort of zeitgeist is. They say there is another way. They have a belief. They have a vision. If you look at science is always marked by such people who went against some conventional wisdom, collected the knowledge at the time, and assembled it in a way that produced a powerful platform.
And you've been amazingly honest about, in an inspiring way, about things you've been wrong about predicting, and you've obviously been right about a lot of things. But in this kind of tension, how do you balance as a company in predicting the next 5 years, the impossible, planning for the impossible? So listening to those crazy dreamers, letting them run away and make the impossible real, make it happen, and slow, that's how programmers often think, and slowing things down and saying, well, this is the rational, this is the possible, the pragmatic, the dreamer versus the pragmatist, I would say.
So it's helpful to have a model which encourages a predictable revenue stream as well as the ability to do new things. So in Google's case, we're big enough and well enough managed and so forth that we have a pretty good sense of what our revenue will be for the next year or two, at least for a while. And so we have enough cash generation that we can make bets. And indeed, Google has become Alphabet, so the corporation is organized around these bets. And these bets are in areas of fundamental importance to the world, whether it's artificial intelligence, medical technology, self-driving cars, connectivity through balloons, on and on and on. And there's more coming and more coming. So one way you could express this is that the current business is successful enough that we have the luxury of making bets. And another one that you could say is that we have the wisdom of being able to see that a corporate structure needs to be created to enhance the likelihood of the success of those bets. So we essentially turned ourselves into a conglomerate of bets and then this underlying corporation, Google, which is itself innovative. So in order to pull this off, you have to have a bunch of belief systems. And one of them is that you have to have bottoms up and tops down. The bottoms up we call 20% time. And the idea is that people can spend 20% of the time on whatever they want. And the top down is that our founders in particular have a keen eye on technology and they're reviewing things constantly. So an example would be that they'll hear about an idea or I'll hear about something and it sounds interesting. Let's go visit them. And then let's begin to assemble the pieces to see if that's possible. And if you do this long enough, you get pretty good at predicting what's likely to work.
So that's a beautiful balance that's struck. Is this something that applies at all scale? So in the
seems to be that Sergey, again, 15 years ago, it came up with a concept called 10% of the budget should be on things that are unrelated. It was called 70-20-10.
Can do it too.
So is there differences in your view? Not saying which is better or so on, but difference in the different implementations of C++. Why are there several sort of maybe naive questions for me? GCC, Clang, so
this is a very reasonable question. When I designed C++, most languages had multiple implementations because if you run on an IBM, if you run on a Sun, if you run on a Motorola, there was just many, many companies, and they each have their own compilation structure, their old compilers. It was just fairly common that there was many of them. And I wrote C front assuming that other people would write compilers for C++ if I was successful. And furthermore, I wanted to utilize all the back-end infrastructures that were available. I soon realized that my users were using 25 different linkers. I couldn't write my own linker. Yes, I could, but I couldn't write 25 linkers and also get any work done on the language. And so it came from a world where there was many linkers, many optimizers, many compiler front ends, not to start, but many operating systems. The whole world was not an 86 and a Linux box or something, whatever is the standard today. In the old days, they said a VAX. So basically, I assumed there would be lots of compilers. It was not a decision that there should be many compilers. It was just a fact. That's the way the world is. And yes, many compilers emerged, and today there's at least 4 front ends, Clang, GCC, Microsoft, and EDG, Edis Design Group. They supply a lot of the independent organizations and the embedded systems industry. And there's lots and lots of backends. We have to think about how many dozen backends there are, because different machines have different things. Especially in the embedded world, the machines are very different. The architectures are very different. And so having a single implementation was never an option. Now, I also happen to dislike monocultures.
Monocultures.
They are dangerous, because whoever owns the monoculture can go stale, and there's no competition, and there's no incentive to innovate. There's a lot of incentive to put barriers in the way of change, because, hey, we own the world, and it's a very comfortable world for us, and who are you to mess with that? So I really am very happy that there's 4 front ends for C++. Clang's great, but GCC was great, but then it got somewhat stale. Clang came along, and GCC is much better now.
Competition
Microsoft is much better now. So at least a low number of front end puts a lot of pressure on standards compliance and also on performance and error messages and compile time speed, all this good stuff that we want.
Do you think, crazy question, there might come along, do you hope there might come along implementation of C++ written, given all of its history, written from scratch? So written today from scratch.
Well, Clang and the LLVM is more or less written from scratch.
But there's been C++ 11, 14, 17, 20. You know, there's been a lot of
sooner or later somebody is going to try again. There has been attempts to write new C++ compilers, and some of them has been used and some of them has been absorbed into others and such. Yeah, it'll happen.
So C++ is an object-oriented programming language that creates, especially with its newer versions, as we'll talk about, higher and higher levels of abstraction. So how do you design, let's even go back to the origin of C++, how do you design something with so much abstraction that's still efficient and is still something that you can manage, do static analysis on, you can have constraints on, they can be reliable, all those things we've talked about. So create to me, there's a slight tension between high level abstraction and efficiency.
That's a good question. I could probably have a year's course just trying to answer it. Yes, there's a tension between efficiency and abstraction, but you also get the interesting situation that you get the best efficiency out of the best abstraction. And my main tool for efficiency, for performance, actually is abstraction. So let's go back to how C++ got there.
Yeah.
You said it was object-oriented programming language. I actually never said that. It's always quoted, but I never did. I said C++ supports object-oriented programming,
but it's not,
and other techniques. And that's important, because I think that the best solution to most complex, interesting problems require ideas and techniques from things that has been called object-oriented, data abstraction, functional, traditional C-style code. All of the above. Mm-hmm. And so when I was designing C++, I soon realized I couldn't just add features. If you just add what looks pretty or what people ask for or what you think is good, one by one, you're not going to get a coherent whole. What you need is a set of guidelines that guides your decisions. Should this feature be in or should this feature be out? How should a feature be modified before it can go in and such? And there's in the book I wrote about that, the design and evolution of C++, there's a whole bunch of rules like that. Most of them are not language technical. They're things like don't violate static type system, because I like static type system for the obvious reason that I like things to be reliable on reasonable amounts of hardware. But one of these rules is the zero overhead principle.
The what kind of principle?
The zero overhead principle. Mm-hmm. It basically says that if you have an abstraction, it should not cost anything compared to write the equivalent code at a lower level. So if I have, say, a matrix multiply, it should be written in such a way that you could not drop to the C level of abstraction and use arrays and pointers and such and run faster. And so people have written such matrix multiplications, and they've actually gotten code that ran faster than Fortran, because once you had the right abstraction, you can eliminate You can eliminate temporaries, and you can do loop fusion and other good stuff like that. That's quite hard to do by hand and in a lower level language. And there's some really nice examples of that. And the key here is that matrix multiplication, the matrix abstraction, allows you to write code that's simple and easy. You can do that in any language. But with C++, it has the features so that you can also have this thing run faster than if you hand-coded it. Now, people have given that lecture many times, I and others, and a very common question after the talk, where you have demonstrated that you can outperform Fortran for dense matrix multiplication, people come up and says, yeah, but that was C++. If I rewrote your code in C, how much faster would it run? And the answer is much slower. This happened the first time, actually back in the 80s, with a friend of mine called Doug McElroy, who demonstrated exactly this effect. And so the principle is you should give programmers the tools so that their abstractions can follow the zero overhead principle. Furthermore, when you put in a language feature in C++ or a standard library feature, you try to meet this. It doesn't mean it's absolutely optimal, but it means if you hand code it with the usual facilities in the language, in C++, in C, you should not be able to better it. Usually you can do better if you use embedded assembler for machine code for some of the details to utilize part of a computer that the compiler doesn't know about. But you should get to that point before you beat the abstraction.
So that's a beautiful ideal to reach for.
And we meet it quite often.
Quite often. So where's the magic of that coming from? There's some of it is the compilation process, so the implementation of C++. Some of it is the design of the feature itself, the guidelines. So I've recently and often talked to Chris Lattner, Clang. What, just out of curiosity, is your relationship in general with the different implementations of C++, as you think about, you and committee and other people in C++, think about the design of new features or design of previous features, in trying to reach the ideal of zero overhead? Does the magic come from the design, the guidelines, or from the implementations?
And not all. You go for programming technique, programming language features, and implementation techniques. You need all three.
And how can you think about all three at the same time?
It takes some experience, it takes some practice, and sometimes you get it wrong, but after a while you sort of get it right. I don't write compilers anymore, but Brian Kernighan pointed out that one of the reasons C++ succeeded was some of the craftsmanship I put into the early compilers. And of course, I did the language design. Of course, I wrote a fair amount of code using this kind of stuff. And I think most of the successes involves progress in all three areas together. A small group of people can do that. 2-3 people can work together to do something like that. It's ideal if it's one person that has all the skills necessary, but nobody has all the skills necessary in all the fields where C++ is used. So if you want to approach my ideal in, say, concurrent programming, you need to know about algorithms for concurrent programming, you need to know the trickery of lock-free programming, you need to know something about the compiler techniques, and then you have to know some of the the application areas where this is, like some forms of graphics or some forms of web serving kind of stuff. And that's very hard to get into a single head, but small groups.
And what was the first programming language, if I may ask it this way, that you fell in love with?
I think I'll call 60, and After that, I remember Snowball. I remember Fortran, didn't fall in love with that. I remember Pascal, didn't fall in love with that. It all got in the way of me. And then I discovered assembler, and that was much more fun. And from there, I went to microcode.
So you were drawn to you found the low-level stuff beautiful.
I went through a lot of languages, and then I spent significant time in assembler and microcode. That was sort of the first really profitable things, and I paid for my master's, actually. And then I discovered Simula, which was absolutely great.
Simula
was the extension of Algol 60, done primarily for simulation, but basically they invented object-oriented programming at inheritance and runtime polymorphism while they were doing it. And that was a language that taught me that you could have the problems of a program grow with the size of the program rather than with the square of the size of the program. That is, you can actually modularize very nicely. And that was a surprise to me. It was also a surprise to me that a stricter type system than Pascal's was helpful, whereas Pascal's type system got in my way all the time. So you need a strong type system to organize your code well, but it has to be extensible and flexible.
Let's get into the details a little bit. If you remember, what kind of type system did Pascal have? What typing system did Algol 60 have?
Basically, Pascal was sort of the simplest language that Nikolaus Wirth could define that served the needs of Nikolaus Wirth at the time. And it has a sort of a highly moral tone to it. That is, if you can say it in Pascal, it's good, and if you can't, it's not so good. Whereas Simula allowed you basically to build your own type system. So instead of trying to fit yourself into Nikolaus Wirth's world, Christian Nygaard's language and Ole Johan Dahl's language allowed you to build your own. So it's sort of close to the original idea of you build a domain-specific language. As a matter of fact, what you build is a set of types and relations among types that allows you to express something that's suitable for an application.
So when you say types, stuff you're saying has echoes of object-oriented programming.
Yes, they invented it. Every language that uses the word class for type is a descendant of Simula, directly or indirectly. Christian Nygaard and Ole Johan Dahl were mathematicians, and they didn't think in terms of types. But they understood sets and classes of elements, and so they called their types classes. And basically in C++, as in Simula, a class is a user-defined type.
So can you try the impossible task and give a brief history of programming languages from your perspective? So we started with Algol 60, Simula, Pascal, but that's just the 60s and 70s.
I can try. The most sort of interesting and major improvement of programming languages was Fortran, the first Fortran. Because before that, all code was written for a specific machine, and each specific machine had a language, assembly language or macroassembler or some extension of that idea. But you are writing for a specific machine in the language of that machine. Mm-hmm. And Bacchus and his team at IBM built a language that would allow you to write what you really wanted. That is, you could write it in a language that was natural for people. Now, these people happen to be engineers and physicists, so the language that came out was somewhat unusual for the rest of the world. But basically, they said formula translation because they wanted to have the mathematical formulas translated into the machine. Mm-hmm. And as a side effect, they got portability, because now they are writing in the terms that the humans used and the way humans thought. And then they had a program that translated it into the machine's needs. And that was new, and that was great. And it's something to remember. We want to raise the language to the human level, but we don't want to lose the efficiency. So,
and that was the first step towards the human.
That was the first step. And of course, there were a very particular kind of humans. Business people were different, so they got COBOL instead, and et cetera, et cetera. And Simula came out, no, let's not go to Simula yet. Let's go to Algol. Fortran didn't have, at the time, the notions of, not a precise notion of type, not a precise notion of scope, not a set of translation phases that was what we have today, lexical, syntax, semantics. It was sort of a bit of a model in the early days, but hey, they'd just done the biggest breakthrough in the history of programming, right? So you can't criticize them for not having gotten all the technical details right. So we got Algol. That was very pretty, and most people in commerce and science considered it useless because it was not flexible enough and it wasn't efficient enough, and et cetera, et cetera. But that was a breakthrough from a technical point of view. And then Simula came along to make that idea more flexible, and you could define your own types. And that's where I got very interested. Christian Nygaard, who's the main idea man behind Simula.
That was late 60s.
This was late 60s. Was a visiting professor in Aarhus. And so I learned object-oriented programming by sitting around and, well, in theory, discussing with Christian Nygaard. But Christian, once he gets started and in full flow, it's very hard to get a word in edgeways with.
You're just listening.
So it was great. I learned it from there.
Not to romanticize the notion, but it seems like a big leap to think about object-oriented programming. It's really a leap of abstraction.
Yes.
And was that as big and beautiful of a leap as it seems from now in retrospect, or was it an obvious one at the time?
It was not obvious, and many people have tried to do something like that, and most people didn't come up with something as wonderful as Simula. Lots of people got their PhDs and made their careers out of forgetting about Simula or never knowing it. For me, the key idea was basically I could get my own types. And that's the idea that goes further into C++, where I can get better types and more flexible types and more efficient types. But it's still the fundamental idea. When I want to write a program, I want to write it with my types that is appropriate to my problem and under the constraints that I'm under with hardware, software, environment, etc. And that's the key idea. People picked up on the class hierarchies and the virtual functions and the inheritance, and that was only part of it. It was an interesting and major part, and still a major part in a lot of graphic stuff, but it was not the most fundamental. It was when you wanted to relate one type to another, you don't want them all to be independent. The classical example is that you don't actually want to write a city simulation with vehicles where you say, well, if it's a bicycle, write the code for turning a bicycle to the left. If it's a normal car, turn right the normal car way. If it's a fire engine, turn right the fire engine way, da-da-da-da-da-da. You get these big case statements, and bunches of if statements and such. Instead, you tell the base class that that's the vehicle and say turn left the way you want to. And this is actually a real example. They used it to simulate and optimize the emergency the emergency services for somewhere in Norway back in the 60s.
Wow.
So this was one of the early examples for why you needed inheritance and you needed a runtime polymorphism because you wanted to handle this set of vehicles in a manageable way. You can't just rewrite your code each time a new kind of vehicle comes along.
Yeah, that's a beautiful, powerful idea. And of course, it stretches through your work through C++, as we'll talk about. But I think you structured it nicely. What other breakthroughs came along in the history of programming languages? If we were to tell the history in that way.
Obviously, I'm better telling the part of the history that is the path I'm on, as opposed to all the paths.
Yeah, you skipped the hippie John McCarthy and Lisp, one of my favorite languages.
But Lisp is not one of my favorite languages.
Yes.
It's obviously important. It's obviously interesting. Lots of people write code in it, and then they rewrite it into C or C++ when they want to go to production.
Yes.
It's in the world I'm at, which are constrained by performance, reliability, issues, deployability, cost of hardware. I don't like things to be too dynamic. It is really hard to write a piece of code that's perfectly flexible, that you can also deploy on a small computer, and that you can also put in, say, a telephone switch in Bogota. What's the chance, if you get an error and you find yourself in the debugger, that the telephone switch in Bogota on late Sunday night has a programmer around?
Right.
The chance is zero. And so a lot of things I think most about can't afford that flexibility. I'm quite aware that maybe 70-80% of all code are not under the kind of constraints I'm interested in. But somebody has to do the job I'm doing because you have to get from these high-level flexible languages to the hardware.
The stuff that lasts for 10, 20, 30 years is robust, operates under very constrained conditions. Yes, absolutely.
That's right.
And it's fascinating and beautiful in its own way. It's C++ is one of my favorite languages, and so is Lisp. So I can embody two for different reasons as a programmer.
I understand why Lisp is popular, and I can see the beauty of the ideas, and similarly with Smalltalk. It's just not as relative. It is not as relevant in my world. And by the way, I distinguish between those and the functional languages, where I go to things like ML and Haskell. Different kind of languages. They have a different kind of beauty, and they're very interesting. And I actually try to learn from all the languages I encounter to see what is there that would make working on the kind of problems I'm interested in, with the kind of constraints that I'm interested in, what can actually be done better? Because we can surely do better than we do today.
You mentioned that you hope there will be one unified set of guidelines in the future for how to construct a programming language. So perhaps not one programming language, but a unification of how we build programming languages. If you remember such statements.
I have some trouble remembering it, but I know the origin of that idea.
So maybe you can talk about sort of C++ has been improving. There's been a lot of programming language. Where does the arc of history taking us? Do you hope that there is a unification about the languages with which we communicate in the digital space?
Well, I think that languages should be designed not by clobbering language features together and doing slightly different versions of somebody else's ideas, but through the creation of a set of principles, rules of thumbs, whatever you call them. I made them for C++, and we're trying to teach people in the standards committee about these rules, because a lot of people come in and says, I've got a great idea, let's put it in the language. And then you have to ask, why does it fit in the language? Why does it fit in this language? It may fit in another language and not here, or it may fit here and not the other language. So you have to work from a set of principles, and you have to develop that set of principles. And one example that I sometimes remember is I was sitting down with some of the designers of Common Lisp. Mm-hmm. And we were talking about languages and language features, and obviously we didn't agree about anything because, well, Lisp is not C++ and vice versa.
It's too many parentheses.
But suddenly we started making progress. I said I had this problem and I developed it according to these ideas. And they said, why? We had that problem, different problem, and we developed it with the same kind of principles. And so we worked through large chunks of C++ and large chunks of Common Lisp and figured out we actually had similar sets of principles of how to do it. But the constraints on our designs were very different, and the aims for the usage was very different. But there was commonality in the way you reason about language features and the fundamental principles you are trying to do.
So do you think that's possible so there, just like there is perhaps a unified theory of physics, of the fundamental forces of physics, I'm sure there is commonalities among the languages, but there's also people involved that help drive the development of these languages. Do you have a hope or an optimism that there will be a unification? If you think about physics and Einstein towards a simplified language, do you think that's possible?
Let's remember, sort of modern physics, I think, started with Galileo in the 1300s. So they've had 700 years to get going. Yeah. Modern computing started in about 49. We've got, 70 years. They have 10 times. Yeah. And furthermore, they are not as bothered with people using physics the way we are worried about programming is done by humans. Sure. So each have problems and constraints the others have, but we are very immature compared to physics. So I would look at sort of the philosophical level and look for fundamental principles, like you don't leak resources, you shouldn't. You don't take errors at runtime that you don't need to. You don't violate some kind of type system. There's many kinds of type systems, but when you have one, you don't break it, etc., etc. There will be quite a few, and it will not be the same for all languages. But I think if we step back at some kind of philosophical level, we would be able to agree on sets of principles that applied to sets of problem areas. And within an area of use, like in C++'s case, what used to be called systems programming, the area between the hardware and the fluffier parts of the system, you might very well see a convergence. So these days you see Rust having adopted RAII, and sometimes accuses me for having borrowed it. 20 years before they discovered it. But we're seeing some kind of convergence here instead of relying on garbage collection all the time. The garbage collection languages are doing things like the dispose patterns and such that imitates some of the construction destruction stuff, and they're trying not to use the garbage collection all the time and things like that. So there's a conversion, but I think we have to step back to the philosophical level, agree on principles, and then we'll see some convergences, and it will be application domain.
And then there's this idea of concepts.
Yes.
That puts some. Now, I've never even. I don't know if it was ever available in any form, but it puts some constraints on the stuff you can parameterize, essentially.
Let me try and explain this.
Yes.
So, yes, it wasn't there 10 years ago. We have had versions of it that actually work for the last 4 or 5 years. It was a design by Gabidos Reyes, Drew Sutton, and me. We were professors and postdocs in Texas at the time. And the implementation by Andrew Sutton has been available for that time. And it is part of C++20. And there's a standard library that uses it. So this is becoming really very real. It's available in Clang and GCC, GCC for a couple of years, and I believe Microsoft is soon going to do it. We expect all of C++20 to be available in all the major compilers in 20. But this kind of stuff is available now. Yeah. I'm just saying that because otherwise people might think I was talking about science fiction. And so what I'm going to say is concrete. You can run it today. And there's production uses of it. So the basic idea is that when you have a generic component, like a sort function, the sort function will require at least 2 parameters. One, a data structure with a given type, and a comparison criteria. And these things are related, but obviously you can't compare things if you don't know what the type of things you compare. And so you want to be able to say, I'm going to sort something, and it is to be sortable. What does it mean to be sortable? You look it up in the standard. It has to be a sequence with a beginning and an end. Mm-hmm. There has to be random access to that sequence. And there has to be the element types has to be comparable.
Which
by default,
means
by less than
operator can operate on.
Yes.
Some logical operator can operate.
Basically, what concepts are? They're compile time predicates. They're predicates you can ask. Are you a sequence? Yes, I have begin and end. Are you a random access sequence? Yes, I have subscripting and plus. Is your element type something that has a less than? Yes, I have a less than. And so basically that's the system. And so instead of saying I will take a parameter of any type, it'll say I'll take something that's sortable. And it's well defined. And so you say, okay, you can sort with less than. I don't want less than. I want greater than or something I invent. So you have 2 parameters, the sortable thing and the comparison criteria. And the comparison criteria will say, well, I can, you can write it saying it should operate on the element type and it has the comparison operations. So that's simply the fundamental thing. It's compile time predicates. Do you have the properties I need? Mm-hmm. So it specifies the requirements of the code on the parameters that it gets. It's very similar to types, actually.
But operating in the space of concepts.
Concepts. The word concept was used by Alex Stefanov, who is sort of the father of generic programming in the context of C++. There's other places that use that word, but the way we call it generic programming is Alex's. And he called them concepts because he said they're the sort of the fundamental concepts of an area, so they should be called concepts. And we've had concepts all the time. If you look at the KNR book about C has arithmetic types and it has integral types. It says so in the book. And then it lists what they are, and they have certain properties. The difference today is that we can actually write a concept that will ask a type, are you an integral type? Mm-hmm. Do you have the properties necessary to be an integral type? Do you have plus, minus, divide, and such?
So maybe the story of concepts, because I thought it might be part of C++ 11. COX, whatever it was at the time. What was why didn't it, we'll talk a little bit about this fascinating process of standards, because I think it's really interesting for people. It's interesting for me, but why did it take so long? What shapes did the idea of concepts take? What were the challenges?
Back in 87 or thereabouts.
1987? Wow.
In 1987 or thereabouts, when I was designing templates, obviously I wanted to express the notion of what is required by a template, of its arguments. And so I looked at this. And basically for templates, I wanted three properties. I wanted to be very flexible. It had to be able to express things I couldn't imagine, because I know I can't imagine everything, and I've been suffering from languages that try to constrain you to only do what the designer thought good. Mm-hmm. I didn't want to do that. Secondly, it had to run faster, as fast or faster than handwritten code. So basically, if I have a vector of t and I take a vector of char, it should run as fast as you build a vector of char yourself, without parameterization. And thirdly, I wanted to be able to express the constraints of the arguments, have proper type checking of the interfaces. And neither I nor anybody else at the time knew how to get all three. And I thought, for C++, I must have the two first. Otherwise, it's not C++. And it bothered me for another couple of decades that I couldn't solve the third one. I mean, I was the one that put function argument type checking into C. I know the value of good interfaces. I didn't invent that idea. It's very common. But I did it. And I wanted to do the same for templates, of course, and I couldn't. So it bothered me. Then we tried again, 2002, 2003. Gabidos Reyes and I started analyzing the problem, explained possible solutions. It was not a complete design. A group in University of Indiana, an old friend of mine, they started a project at Indiana, and we thought we could get a good system of concepts in another 2 or 3 years. That would have made C++ 11 to C++ 06 or 07. Well, it turned out that I think we got a lot of the fundamental ideas wrong. They were too conventional. They didn't quite fit C++, in my opinion. Didn't serve implicit conversions very well. It didn't serve mixed type arithmetic, mixed type computations very well. A lot of stuff came out of the functional community, and that community didn't deal with multiple types in the same way as C++ does, had more constraints on what you could express, and didn't have the draconian performance requirements. And basically, we tried very hard. We had some successes, but it just in the end didn't compile fast enough, was too hard to use, and didn't run fast enough unless you had optimizers that was beyond the state of the art. They still are. So we had to do something else. Basically, it was the idea that a set of parameters defines a set of operations, and you go through an interaction table, just like for virtual functions, and then you try to optimize the interaction away to get performance. And we just couldn't do all of that.
What do you make of JavaScript in general? So you're talking in the Platonic sense about languages, about what they're good at, what their philosophy of design is, but there's also a large user base behind each of these languages, and they use it in the way sometimes maybe it wasn't really designed for.
That's right.
JavaScript is used way beyond probably what it was designed for.
Let me say it this way. When you build a tool, you do not know how it's going to be used. You try to improve the tool by looking at how it's being used and when people cut their fingers off and try and stop that from happening. But really, you have no control over how something is used. So I'm very happy and proud of some of the things C++ is being used at, and some of the things I wish people wouldn't do. Bitcoin mining being my favorite example. It uses as much energy as Switzerland, and mostly serves criminals.
Yeah.
But back to the languages, I actually think that having JavaScript run in the browser was an enabling thing for a lot of things. Yes, you could have done it better, but people were trying to do it better, and they were using sort of more principled language designs, but they just couldn't do it right. And the non-professional programmers that write lots of that code just couldn't understand them. So it did an amazing job for what it was. It's not the prettiest language, and I don't think it ever will be the prettiest language, but let's not be bigots here.
So what was the origin story of C++?
Yeah.
You basically gave a few perspectives of your inspiration of object-oriented programming. You had a connection with C, and performance efficiency was a thing you were drawn to.
Efficiency and reliability. You have to get both.
What's reliability?
I really want my telephone calls to get through, and I want the quality of what I am talking coming out at the other end. The other end might be in London or wherever. So you don't want the system to be crashing. If you're doing a bank, you mustn't crash. It might be your bank account that is in trouble. There's different constraints. Like in games, it doesn't matter too much if there's a crash. Nobody dies and nobody gets ruined. But I'm interested in the combination of performance, partly because of sort of speed of things being done, part of being able to do things that is necessary to have reliability of larger systems. If you spend all your time interpreting a simple function call, you are not going to have enough time to do proper signal processing to get the telephone calls to sound right. Either that, or you have to have 10 times as many computers and you can't afford your phone anymore. It's a ridiculous idea in the modern world because we've solved all of those problems.
I mean, they keep popping up in different ways because we tackle bigger and bigger problems, so efficiency remains always an important aspect.
But you have to think about efficiency not just as speed, but as an enabler to important things. And one of the things it enables is reliability, is dependability. When I press the pedal, the brake pedal of a car, it is not actually connected directly to anything but a computer.
Yeah.
That computer better work.
Let's talk about reliability just a little bit. So modern cars have ECUs, have millions of lines of code today. So this is certainly especially true of autonomous vehicles, where some of the aspect of the control or driver assistance systems that steer the car to keep it in the lane and so on. So how do you think, I talk to regulators, people in the government who are very nervous about testing the safety of these systems of software. Ultimately, software that makes decisions that could lead to fatalities. So how do we test software systems like these?
First of all, safety, like performance and like security, is the system's property. People tend to look at one part of a system at a time and saying something like, this is secure. That's all right. I don't need to do that. Yeah, that piece of code is secure. I'll buy your operator.
Right.
If you want to have reliability, if you want to have performance, if you want to have security, you have to look at the whole system.
I did not expect you to say that, but that's very true. Yes.
I'm dealing with one part of the system and I want my part to be really good, but I know it's not the whole system. Furthermore, making an individual part perfect may actually not be the best way of getting the highest degree of reliability and performance and such. There's people who say C++ is type safe, not type safe. You can break it. Sure, I can break anything that runs on a computer. I may not go through your type system. If I wanted to break into your computer, I'll probably try SQL injection.
And it's very true. If you think about safety or even reliability at a system level, especially when a human being is involved, it starts becoming hopeless pretty quickly in terms of proving that something is safe to a certain level.
Yeah.
Because there's so many variables, it's so complex.
Well, let's get back to something we can talk about and actually make some progress on.
Yes.
We can look at C++ programs and we can try and make sure they crash less often. The way you do that is largely by simplification. It is not. The first step is to simplify the code, have less code, have code that are less likely to go wrong. It's not by runtime testing everything. It is not by big test frameworks that you're using. Yes, we do that also. But the first step is actually to make sure that when you want to express something, you can express it directly in code rather than going through endless loops and convolutions in your head before it gets down the code. That if the way you're thinking about a problem is not in the code, there is a missing piece that's just in your head. And the code, you can see what it does, but it cannot see what you thought about it unless you have expressed things directly. When you express things directly, you can maintain it. It's easier to find errors. It's easier to make modifications. It's actually easier to test it. And lo and behold, it runs faster. And therefore, you can use a smaller number of computers, which means there's less hardware that can possibly break. So I think the key here is simplification. But it has to be, to use the Einstein quote, as simple as possible and no simpler.
Not simpler. But
there are other areas with under constraints where you can be simpler than you can be in C++. But in the domain I'm dealing with, that's the simplification I'm after.
What are the key features of C++? And let's use that as a way to sort of talk about the evolution of C++, the new feature. So at the highest level, what are the features that were there in the beginning and what features got added?
Let's first get a principle or an aim in place. C++ is for people who want to use hardware really well and then manage the complexity of doing that through abstraction. And so the first facility you have is a way of manipulating the machines at a fairly low level. That looks very much like C. It has loops, it has variables, it has pointers like machine addresses. It can access memory directly. It can allocate stuff in the absolute minimum of space needed on the machine. There's a machine-facing part of C++, which is roughly equivalent to C. I said C++ could beat C, and it can. Doesn't mean I dislike C. If I disliked C, I wouldn't have built on it. Furthermore, after Dennis Ritchie, I'm probably the major contributor to modern C. And, well, I had lunch with Dennis most days for 16 years, and we never had a harsh word between us. So these C versus C++ fights are for people who don't quite understand what's going on. Then the other part is the abstraction. And there, the key is the class, which is a user-defined type. And my idea for the class is that you should be able to build a type that's just like the built-in types in the way you use them, in the way you declare them, in the way you get the memory, and you can do just as well. So in C++ there's an int, as in C. You should be able to build an abstraction, a class, which we can call capital int, that you can use exactly like an integer and run just as fast as an integer. There's the ideal right there. And of course, you probably don't want to use the int itself, but it has happened. People have wanted integers that were range checked so that you couldn't overflow and such, especially for very safety critical applications like the fuel injection for a marine diesel engine for the largest ships. This is a real example, by the way. This has been done. They built themselves an integer that was just like integer, except that it couldn't overflow. If there was an overflow, you went into the error handling. And then you built more interesting types. You can build a matrix, which you need to do graphics, or you could build a GNOME for a video game.
And all of these are classes, and they appear just like the built-in types.
Exactly.
In terms of efficiency and so on. So what else is there?
And flexibility.
So, I don't know, for people who are not familiar with object-oriented programming, there's inheritance. There's a hierarchy of classes. You can, just like you said, create a generic vehicle that can turn left.
So what people found was that you don't actually know. How do I say this? A lot of types are related. That is, the vehicles, all vehicles are related. Bicycles, cars, fire engines, tanks. They have some things in common and some things that differ. And you would like to have the common things common and having the differences specific. And when you didn't want to know about the differences, like just turn left. Mm-hmm. You don't have to worry about it. That's how you get the traditional object-oriented programming coming out of Simula, adopted by Smalltalk and C++ and all the other languages. The other kind of obvious similarity between types comes when you have something like a vector. Mm-hmm. Fortran gave us the vector as called array of doubles. Mm-hmm. But the minute you have a vector of doubles, you want a vector of double precision doubles and for short doubles for graphics. And why should you not have a vector of integers while you're at it, or a vector of vectors and a vector of vectors of chess pieces? Now you have a board, right? So this is, you express the commonality as the idea of a vector, and the variations come through parameterization. And so here we get the two fundamental ways of abstracting, or of having similarities of types in C++. There's the inheritance and there's a parameterization. There's the object-oriented programming and there's the generic programming.
Mm-hmm. With the templates for the generic programming.
Yep.
So you've presented it very nicely, but now you have to make all that happen and make it efficient. So generic programming with templates, there's all kinds of magic going on, especially recently, that you can help catch up on. But it feels to me like you can do way more than what you just said with templates. You can start doing this kind of meta programming, this kind of...
You can do meta programming also. I didn't go there in that explanation. We're trying to be very basics, but go back on to the implementation. If you couldn't implement this efficiently, if you couldn't use it so that it became efficient, it has no place in C++ because it will violate the zero overhead principle. So when I had to get object-oriented programming inheritance, I took the idea of virtual functions from Simula. Virtual functions is a similar term. Class is a similar term. If you ever use those words, say thanks to Christian Nygaard and Ole Johan Dahl. And I did the simplest implementation I knew of, which was basically a jump table. So you get the virtual function table, the function goes in, does an indirection through a table and get the right function. That's how you pick the right thing there. And I thought that was trivial. It's close to optimal. And it was obvious. It turned out the Simula had a more complicated way of doing it, and therefore was slower. And it turns out that most languages have something that's a little bit more complicated, sometimes more flexible, but you pay for it. Mm-hmm. And one of the strengths of C++ was that you could actually do this object-oriented stuff, and your overhead compared to ordinary functions, there's no indirection, is sort of in 5, 10, 25% for just the call. It's down there. It's not 2. And that means you can afford to use it. Furthermore, in C++, you have the distinction between a virtual function and a non-virtual function. If you don't want any overhead, if you don't need the indirection that gives you the flexibility in object-oriented programming, just don't ask for it. So the idea is that you only use virtual functions if you actually need the flexibility. So it's not zero overhead, but it's zero overhead compared to any other way of achieving the flexibility. Mm-hmm. Now, over to parameterization. Basically, the compiler looks at the template, say the vector, and it looks at the parameter, and then combines the two and generates a piece of code that is exactly as if you've written a vector of that specific type.
Yes.
So that's the minimal overhead. If you have many template parameters, you can actually combine code that the compiler couldn't usually see at the same time, and therefore get code that is faster than if you had handwritten the stuff. Unless you are very, very clever.
So the thing is, parameterized code, the compiler fills stuff in during the compilation process, not during runtime.
That's right. And furthermore, it gives all the information it's gotten, which is the template, the parameter, and the context of use. It combines the three and generates good code.
Yeah. But it can generate... Now, it's a little outside of what I'm even comfortable thinking about, but it can generate a lot of code.
Yes.
And how do you... So I remember being both amazed at the power of that idea and how ugly the debugging looked.
Yes, debugging can be truly horrid. Come back to this because I have a solution. Anyway, the debugging was ugly. The code generated by C++ has always been ugly because there's these inherent optimizations. A modern C++ compiler has front-end, middle-end, and back-end optimizations. Even CFront back in 83 had front-end and back-end optimizations. I actually took the code, generated an internal representation, munged that representation to generate good code. Mm-hmm. So people say it's not a compiler, it generates C. The reason it generated C was I wanted to use C's code generators that was really good at back-end optimizations. But I needed front-end optimizations, and therefore the C I generated was optimized C. The way a really good handcrafted optimizer human could generate it, and it was not meant for humans. It was the output of a program, and it's much worse today. And with templates, it gets much worse still. So it's hard to combine simple debugging with optimal code, because the idea is to drag in information from different parts of the code to generate good code, machine code, and that's not readable. So what people often do for debugging is they turn the optimizer off. And so you get code that when something in your source code looks like a function call, it is a function call. When the optimizer is turned on, it may disappear, the function call, it may inline. And so one of the things you can do is you can actually get code that is smaller than the function call, because you eliminate the function preamble and return, and there's just the operation there. One of the key things when I did templates was I wanted to make sure that if you have, say, a sort algorithm, and you give it a sorting criteria, if that sorting criteria is simply comparing things with less than, the code generated should be the less than, not a indirect function call to a comparison object, which is what it is in the source code. But we really want down to the single instruction. And but anyway, turn off the optimizer, and you can debug. The first level of debugging can be done, and I always do, without the optimization on, because then I can see what's going on. But get back to the standardization. We are standardizing C++ under ISO rules, which are a very open process. People come in, there's no requirements for education or experience.
So you've started to develop C++, and there's a whole... When was the first standard established? What is that like, the ISO standard? Is there a committee that you're referring to?
Sure.
There's a group of people. What's that like? How often do you meet?
Okay.
What's the discussion
I'll
like?
try and explain that. So sometime in early 1989, two people, one from IBM, one from HP, turned up in my office and told me I would like to standardize C++. This was a new idea to me, and I pointed out that it wasn't finished yet, it wasn't ready for formal standardization and such. And they said, no, Bjarne, you haven't gotten it. You really want to do this. Our organizations depend on C++. We cannot depend on something that's owned by another corporation that might be a competitor. Of course, we could rely on you, but you might get run over by a bus.
Right. The old bus.
We really need to get this out in the open. It has to be standardized under formal rules, and we are going to standardize it under ISO rules. And you really want to be part of it, because basically otherwise we'll do it ourselves. And we know you can do it better. So through a combination of arm twisting and flattery, we got started. So in late 89, there was a meeting in DC at the, actually, no, it was not ISO then, it was ANSI, the American National Standard we're doing. We met there. We were lectured on the rules of how to do an ANSI standard. There was about 25 of us there, which apparently was a new record for that kind of meeting. And some of the old C guys that has been standardizing C was there, so we got some expertise in. So the way this works is that it's an open process. Anybody can sign up if they pay the minimal fee, which is about $1,000. Still less than, it's a little bit more now. And I think it's $1,280. It's not going to kill you.
Right.
And we have 3 meetings a year. This is fairly standard. We tried 2 meetings a year for a couple of years. That didn't work too well. So 3 1-week meetings a year, and you meet and you have technical discussions, and then you bring proposals forward for votes. The votes are done one vote per organization. So you can't have, say, IBM come in with 10 people and dominate things. That's not allowed.
And these are organizations that extensively use C++.
Yes.
Because it's basically...
Or individuals.
Or individuals. I mean, it's a bunch of people in a room deciding the design of a language based on which a lot of the world's systems run.
That's right. Well, I think most people would agree it's better than if I decided it, or better than if a single organization like AT&T decided it.
I don't know if everyone agrees to that, by the way. Bureaucracies have their critics too.
Yes, they're look, standardization is not pleasant. Yeah. It's horrifying.
It's like democracy. Right?
But exactly, as Churchill says, democracy is the worst way except for all the others, right? And it's, I would say, the same with formal standardization. But anyway, so we meet and we have these votes, and that determines what the standard is. A couple of years later, we extended this so it became worldwide. We have standard organizations that are active in currently 15 to 20 countries, and another 15 to 20 are sort of looking and voting based on the rest of the work on it. And we meet 3 times a year. Next week, I'll be in Cologne, Germany, spending a week doing standardization, and we'll vote out the committee draft of C++20, which goes to the national standards committees for comments and requests for changes and improvements. Then we do that, and there's a second set of votes where hopefully everybody votes in favor. This has happened several times. The first time we finished, we started in the first technical meeting was in 1990. The last was in 98. We voted it out. That was the standard that people used till 11 or a little bit past 11. And it was an international standard. All the countries voted in favor. It took longer with 11, and I'll mention why, but all the nations voted in favor. And we work on the basis of consensus. That is, we do not want something that passes 60-40, because then we're going to get dialects and opponents, and people complain too much. They all complain too much, but basically it has no real effect. The standards has been obeyed. They have been working to make it easier to use many compilers, many computers, and all of that kind of stuff. And so it was traditional with ISO standards to take 10 years. We did the first one in 8, brilliant. And we thought we were going to do the next one in 6 because now we are good at it.
Right.
It took 13.
Yeah, it was named OX.
It was named OX.
Hoping that you would at least get it within the aughts, the single digits.
I thought we would get. I thought we would get 6, 7, or 8.
The confidence of youth.
Yeah, that's right. Well, the point is that this was sort of like a second system effect. That is, we now knew how to do it, and so we're going to do it much better, and we got more ambitious. And it took longer. Furthermore, there is this tendency, because it's a 10-year cycle, or age, doesn't matter. Just before you're about to ship, somebody has a bright idea.
Yeah.
And so we really, really must get that in. We did that successfully with the STL.
Yeah.
We got the standard library that gives us all the STL stuff. That basically, I think it saved C++. It was beautiful.
Yeah.
And then people tried it with other things, and it didn't work so well. They got things in, but it wasn't as dramatic, and it took longer and longer and longer. So after C++ 11, which was a huge improvement, and what most people are using today, we decided never again. And so how do you avoid those slips? And the answer is that you ship more often, so that if you have a slip on a 10-year cycle, by the time you know it's a slip, there's 11 years till you get it.
Yeah.
Now with a 3-year cycle, there is about 4 years till you get it. Like the delay between feature freeze and shipping, so you always get 1 or 2 years more. And so we shipped 14 on time, we shipped 17 on time, and we will ship 20 on time. It'll happen. And furthermore, this gives a predictability that allows the implementers, the compiler implementers, the library implementers, they have a target and they deliver on it. 11 took 2 years before most compilers were good enough. 14, most compilers were actually getting pretty good in 14. 17, everybody shipped in 17.
Wow.
We are going to have at least almost everybody ship almost everything in 20. And I know this because they're shipping in 19. Predictability is good. Delivery on time is good. And so, yeah.
That's great. So
that's how it works.
So let's talk about programming languages, if it's okay.
Sure.
At the highest absurd philosophical level, because I
don't get romantic on me, Lex.
I will forever get romantic and torture you. I apologize. Why do programming languages even matter?
Okay, well, thank you very much. So you're saying why should you care about any one programming language, or why do we care about programming computers, or
no? Why do we care about programming language design, creating effective programming languages, choosing one programming languages versus another programming language? Why we keep struggling and improving through the evolution of these programming languages?
Sure. Okay, so I mean, I think you have to come back to what are we trying to do here, right? So we have these beasts called computers that are very good at specific kinds of things, and we think it's useful to have them do it for us, right? Now you have this question of how best to express that, because you have a human brain still that has an idea in its head, and you want to achieve something, right? So, well, there's lots of ways of doing this. You can go directly to the machine and speak assembly language, and then you can express directly what the computer understands. That's fine. You can then have higher and higher and higher levels of abstraction up until machine learning, and you're designing a neural net to do the work for you. The question is, where along this way do you want to stop, and what benefits do you get out of doing so? And so programming languages in general, you have C, you have Fortran, and Java, and Ada, Pascal, Swift. You have lots of different things. They all have different trade-offs, and they're tackling different parts of the problems. Now, one of the things that most programming languages do is they're trying to make it so that you have pretty basic things like portability across different hardware. So you've got, I'm going to run on an Intel PC, I'm going to run on a RISC-V PC, I'm going to run on ARM phone or something like that. Fine. I want to write one program and have it portable. And this is something that assembly doesn't do. Now, when you start looking at the space of programming languages, this is where I think it's fun, because programming languages all have trade-offs, and most people will walk up to them and they look at the surface level of syntax and say, oh, I like curly braces, or I like tabs, or I like, semicolons or not, or whatever, right? Subjective, fairly subjective, very shallow things. But programming languages, when done right, can actually be very powerful. And the benefit they bring is expression. Okay. And if you look at programming languages, there's really kind of two different levels to them. One is the down in the dirt, nuts and bolts of how do you get the computer to be efficient, stuff like that, how they work, type systems, compiler stuff, things like that. The other is the UI. And the UI for a programming language is really a design problem, and a lot of people don't think about it that way.
And the UI, you mean all that stuff with the braces and
that stuff's the UI. And what it is, and UI means user interface. And so what's really going on is it's the interface between the guts and the human. And humans are hard, right? Humans have feelings. They have things they like. They have things they don't like. And a lot of people treat programming languages as though humans are just kind of abstract creatures that cannot be predicted. But it turns out that actually there is better and worse. Like, people can tell when a programming language is good or when it was an accident, right? And one of the things with Swift in particular is that a tremendous amount of time by a tremendous number of people have been put into really polishing and making it feel good. But it also has really good nuts and bolts underneath it.
You said that Swift makes a lot of people feel good. How do you get to that point? So how do you predict that, tens of thousands, hundreds of thousands of people are going to enjoy using the user experience of this programming language?
Well, you can look at it in terms of better and worse, right? So if you have to write lots of boilerplate or something like that, you will feel unproductive. And so that's a bad thing. You can look at it in terms of safety. If, like, C, for example, is what's called a memory unsafe language. And so you get dangling pointers and you get all these kind of bugs that then you have to spend tons of time debugging, and it's a real pain in the butt, and you feel unproductive. And so by subtracting these things from the experience, you get, happier people.
But again, keep interrupting. I'm sorry, but
it's so hard to deal with.
If you look at the people that are most productive on Stack Overflow, they have a set of priorities.
Yeah.
That may not always correlate perfectly with the experience of the majority of users. If you look at the most upvoted, quote unquote, correct answer on Stack Overflow, it usually really prioritizes like safe code, proper code, stable code, that kind of stuff, as opposed to, like, if I want to use goto statements in my basic, right? I want to use goto statements. Like, what if 99% of people want to use goto statements? So you use completely improper, unsafe syntax.
I don't think that people actually, like, if you boil it down and you get below the surface level, people don't actually care about gotos or if statements or things like this. They care about achieving a goal.
Yeah.
Right. So the real question is, I want to set up a web server and I want to do a thing and I want to do whatever. Like, how quickly can I achieve that, right? And so from a programming language perspective, there's really two things that matter there. One is what libraries exist, and then how quickly can you put it together, and what do the tools around that look like, right? And when you want to build a library that's missing, what do you do? Okay, now this is where you see huge divergence in the force between worlds. So the key thing to think about with programming languages, and you think about what a programming language is there for, is it's about making a human more productive, right? And so, like, there's an old, I think it's a Steve Jobs quote about it's a bicycle for the mind, right? You can definitely walk, but you'll get there a lot faster if you can bicycle on your way. And
a programming language is a bicycle for the mind.
Yeah,
it's basically wow, that's a really interesting way to think about it.
By raising the level of abstraction, now you can fit more things in your head. By being able to just directly leverage somebody's library, you can now get something done quickly. In the case of Swift UI is this new framework that Apple has released recently for doing UI programming. And it has this declarative programming model which defines away entire classes of bugs. It builds on value semantics and many other nice Swift things. And what this does is allows you to just get way more done with way less code. And now your productivity as a developer is much higher, right? And so that's really what programming languages should be about. Is it's not about tabs versus spaces or curly braces or whatever. It's about how productive do you make the person. And you can only see that when you have libraries that were built with the right intention that the language was designed for. And with Swift, I think we're still a little bit early, but Swift UI and many other things that are coming out now are really showing that. And I think that they're opening people's eyes.
It's kind of interesting to think about like how that, the knowledge of something, of how good the bicycle is, how people learn about that. So I've used C++. Now, this is not going to be a trash talking session about C++, but I used C++ for a really long time.
Go there if you want. I have the scars.
I feel like I spent many years without realizing like there's languages that could, for my particular lifestyle, brain style, thinking style, there's languages that could make me a lot more productive in the debugging stage, in the development stage, and thinking like the bicycle for the mind. I can fit more stuff into my...
Python's a great example of that, right? I mean, a machine learning framework in Python is a great example of that. It's just very high abstraction level. And so you can be thinking about things on a like very high level algorithmic level instead of thinking about, okay, well, am I copying this tensor to a GPU or not? Right? It's not what you want to be thinking about.
And that was
okay. Yeah. And so you look at Python, for example. Python is really good at assembling things, but it's not so great at building all the libraries. And so what you get, because of performance reasons, other things like this, is you get Python layered on top of C. Mm-hmm. For example, and that means that doing certain kinds of things, well, it doesn't really make sense to do in Python. Instead, you do it in C, and then you wrap it, and then you're living in two worlds, and two worlds never is really great because tooling and the debugger doesn't work right, and like all these kinds of things.
Can you clarify a little bit what you mean by Python is not good at building libraries? Meaning it doesn't make it conducive.
Certain kinds of libraries.
No, but just the actual meaning of the sentence.
Yeah.
Meaning like it's not conducive to developers to come in and add libraries, or or the language, or is it the duality of it's a dance between Python and C and
Python's amazing. Python's a great language. I did not mean to say that Python is bad for libraries. What I meant to say is there are libraries that Python's really good at that you can write in Python, but there are other things like if you want to build a machine learning framework, you're not going to build a machine learning framework in Python because of performance, for example, or you want GPU acceleration or things like this. Instead, what you do is you write a bunch of C or C++ code or something like that, and then you talk to it from Python. Right. And so this is because of decisions that were made in the Python design, and those decisions have other counterbalancing forces. But the trick when you start looking at this from a programming language perspective is you sort of say, okay, cool. How do I build this catalog of libraries that are really powerful? And how do I make it so that then they can be assembled into ways that feel good and they generally work the first time? Because when you're talking about building a thing, you have to include the debugging, the fixing, the turnaround cycle, the development cycle, all that kind of stuff into the process of building the thing. It's not just about pounding out the code. And so this is where things like catching bugs at compile time is valuable, for example. But if you dive into the details in this, Swift, for example, has certain things like value semantics, which is this fancy way of saying that when you treat a variable like a value, it acts like a mathematical object would. Okay, so you have used PyTorch a little bit. Mm-hmm. In PyTorch, you have tensors. Tensors are an n-dimensional grid of numbers. Very simple. You can do plus and other operators on them. It's all totally fine. But why do you need to clone a tensor sometimes? Have you ever run into that?
Yeah.
Okay, and so why is that? Why do you need to clone a tensor?
It's the usual object thing that's in Python.
Yeah. So in Python, and just like with Java and many other languages, this isn't unique to Python. In Python, it has a thing called reference semantics, which is the nerdy way of explaining this. And what that means is you actually have a pointer to a thing instead of the thing. Okay. Now, this is due to a bunch of implementation details that you don't want to go into. But in Swift, you have this thing called value semantics. And so when you have a tensor in Swift, it is a value. If you copy it, it looks like you have a unique copy. And if you go change one of those copies, then it doesn't update the other one because you just made a copy of this thing, right?
So that's like highly error prone in at least computer science, math centric disciplines about Python. That like the thing you would expect to behave
like math,
it doesn't behave like math, and in fact, quietly doesn't behave like math, and then can ruin the entirety of your math
exactly.
thing.
Well, and then it puts you in debugging land again.
Yeah.
Right now you just want to get something done, and you're like, wait a second, where do I need to put clone?
Yeah.
In what level of this stack, which is very complicated, which I thought I was reusing somebody's library, and now I need to understand it to know where to clone a thing, right?
And hard to debug, by the way.
Exactly, right? And so this is where programming languages really matter, right? So in Swift, having value semantics, so that both you get the benefit of math working like math, right? But also the efficiency that comes with certain advantages there, certain implementation details there really benefit you as a programmer, right?
Can you clarify the value semantics? Like, how do you know that a thing should be treated like a value?
Yeah, so Swift has a pretty strong culture and good language support for defining values. And so if you have an array, so tensors are one example that the machine learning folks are very used to. Just think about arrays. Same thing, where you have an array, you create an array, you put 2 or 3 or 4 things into it, and then you pass it off to another function.
Mm-hmm.
What happens if that function adds some more things to it? Well, you'll see it on the side that you pass it in, right? This is called reference semantics. Now, what if you pass an array off to a function, it squirrels it away in some dictionary or some other data structure somewhere, right? Well, it thought that you just handed it that array, but then you return back and that reference to that array still exists in the caller, and they go and put more stuff in it,
Mm-hmm.
right? The person you handed it off to may have thought they had the only reference to that, and so they didn't know that this was going to change underneath the covers. And so this is where you end up having to do clone. So like, I was passed a thing, I'm not sure if I have the only version of it, so now I have to clone it. So what value semantics does is it allows you to say, hey, so in Swift, it defaults to value semantics.
So it defaults to value semantics, and then because most things should
end
be
up
treated
being
like values, then it makes sense for that to be the default.
And one of the important things about that is that arrays and dictionaries and all these other collections that are aggregations of other things also have value semantics. And so when you pass this around to different parts of your program, you don't have to do these defensive copies. And so this is great for two sides, right? It's great because you define away the bug, which is a big deal for productivity, the number one thing most people care about. But it's also good for performance, because when you're doing a clone, so you pass the array down to the thing, and it's like, I don't know if anybody else has it, I have to clone it. Well, you just did a copy of a bunch of data. It could be big. And then it could be that the thing that called you is not keeping track of the old thing. So you just made a copy of it, and you may not have had to.
Yeah.
And so the way the value semantics work is in Swift is that it uses this thing called copy on write, which means that you get the benefit of safety.
That's cool.
And performance. And it has another special trick, because if you think certain languages like Java, for example, they have immutable strings. And so what they're trying to do is they provide value semantics by having pure immutability. Functional languages have pure immutability in lots of different places, and this provides a much safer model than it provides value semantics. The problem with this is if you have immutability, everything is expensive. Everything requires a copy. For example, in Java, if you have a string X and a string Y, and you append them together, we have to allocate a new string to hold XY.
If they're immutable.
Well, and strings in Java are immutable, and if there's optimizations for short ones, and it's complicated, but generally think about them as a separate allocation. And so when you append them together, you have to go allocate a third thing, because somebody might have a pointer to either of the other ones, right? And you can't go change them, so you have to go allocate a third thing. Because of the beauty of how the Swift value semantic system works out, if you have a string in Swift and you say, hey, put in X, right? And they say, append on Y, Z, W, what? It knows that there's only one reference to that. And so it can do an in-place update. And so you're not allocating tons of stuff on the side. You don't have all these problems. When you pass it off, you can know you have the only reference. If you pass it off to multiple different people, but nobody changes it, they can all share the same thing. So you get a lot of the benefit of a purely mutable design, and so you get a really nice sweet spot that I haven't seen in other languages.
Yeah, that's interesting. Like I thought there was going to be a philosophical like narrative here that you're gonna have to pay a cost for it, because it sounds like I think value semantics is beneficial for easing of debugging or minimizing the risk of errors, like bringing the errors closer to the source, bringing the symptom of the error closer to the source of the error, however you say that. But you're saying there's not a performance cost either if you implement it correctly.
Well, so there's trade-offs with everything. And so if you are doing very low-level stuff, then sometimes you can notice the cost. But then what you're doing is you're saying, what is the right default? So coming back to user interface, when you talk about programming languages, one of the major things that Swift does that makes people love it, that is not obvious when it comes to designing a language, is this UI principle of progressive disclosure of complexity. Okay, so Swift, like many languages, is very powerful. The question is, when do you have to learn the power as a user? So Swift, like Python, allows you to start with like print hello world, right? Certain other languages start with like public static void main class, like all the ceremony, right?
Yeah.
And so you go to teach a new person, hey, welcome to this new thing. Let's talk about public access control classes. Wait, what's that? Yeah. String system.out println, like packages, like right. And so instead, if you take this and you say, hey, we need packages, modules. We need powerful things like classes. We need data structures. We need like all these things. The question is, how do you factor the complexity, and how do you make it so that the normal case scenario is you're dealing with things that work the right way, give you good performance by default. But then as a power user, if you want to dive down to it, you have full C performance, full control over low-level pointers. You can call malloc if you want to call malloc. Mm-hmm. This is not recommended on the first page of every tutorial, but it's actually really important when you want to get work done, right? And so being able to have that is really the design in programming language design. And design is really, really hard. It's something that I think a lot of people kind of outside of UI, again, a lot of people just think is subjective. Like there's nothing, it's just like curly braces or whatever. It's just like somebody's preference. But actually good design is something that you can feel.
There you go. This is a question to ask, what is the most beautiful feature in a programming language? Before I ask it, let me say, like with Python, I remember when I saw list comprehensions.
Yeah.
It was like, when I like really took it in.
Yeah.
I don't know. I just loved it. It was like fun to do. Like it was fun to do that kind of. There was something about it to be able to filter through a list and to create a new list all in a single line was elegant. I could all get into my head, and it just made me fall in love with the language.
Yep.
So let me ask you a question. What do you use the most beautiful feature in a programming language that you've ever encountered in Swift, maybe, and then outside of Swift?
I think the thing that I like the most from a programming language. So I think the thing you have to think about with a programming language, again, what is the goal? You're trying to get people to get things done quickly. And so you need libraries, you need high quality libraries, and then you need a user base around them that can assemble them and do cool things with them, right? And so to me, the question is, what enables high quality libraries? Okay.
Yeah.
And there's a huge divide in the world between libraries who enable high quality libraries versus the ones that put special stuff in the language.
So programming languages that enable
high quality
libraries. Got it.
So what I mean by that is expressive libraries that then feel like a natural integrated part of the language itself. Mm-hmm. So an example of this in Swift is that int and float and also array and string, things like this, these are all part of the library. Like int is not hard-coded into Swift. And so what that means is that because int is just a library thing defined in the standard library, along with strings and arrays and all the other things that come with the standard library, well, hopefully you do like int, but any language features that you needed to define int, you can also use in your own types. So if you wanted to define a quaternion, or something like this, right? Well, it doesn't come in the standard library. There's a very special set of people that care a lot about this, but those people are also important. It's not about classism, right? It's not about the people who care about ints and floats are more important than the people who care about quaternions. And so to me, the beautiful things about programming languages is when you allow those communities to build high quality libraries that feel native, that feel like they're built into the compiler without having to be.
What does it mean for the int to be part of not hard coded in?
Yeah.
So is it like what is an int?
Okay. Int is just a integer. In this case, it's like a 64-bit integer or something like this.
But so like the 64-bit is hard coded or no?
No, none of that's hard coded. So int, if you go look at how it's implemented, it's just a struct in Swift. And so it's a struct, and then how do you add two structs? Well, you define plus. And so you can define plus on int. Well, you can define plus on your thing too. You can define int has like an is odd method or something like that on it. And so yeah, you can add methods onto things. Yeah.
So you can define operators, like how it behaves.
Yeah.
That to you is beautiful when there's something about the language which enables others to create libraries which are not hacky.
Yeah, they feel native. And so one of the best examples of this is Lisp, right? Because in Lisp, all the libraries are basically part of the language, right? Yeah. You write term rewrite systems and things like this. And so
can you, as a counterexample, provide what makes it difficult to write a library that's native? Is it the Python C?
Well, so one example, I'll give you two examples. Java and C++, or Java and C, they both allow you to define your own types, but int is hard-coded in the language. Okay, well, why? Well, in Java, for example, coming back to this whole reference semantic, value semantic thing, int gets passed around by value.
Yeah,
but if you make like a pair or something like that, a complex number, right? It's a class in Java, and now it gets passed around by reference, by pointer, and so now you lose value semantics, right? You lost math. Okay, well, that's not great, right? If you can do something with int, why can't I do it with my type?
Yeah,
right. So that's the negative side of the thing I find beautiful is when you can solve that, when you can have full expressivity, where you as a user of the language have as much or almost as much power as the people who implemented all the standard built-in stuff, because what that enables truly beautiful libraries.
You know, it's kind of weird because I've gotten used to that. That's one, I guess, other aspect of programming language design. You have to think, the old first principles thinking, like, why are we doing it this way? Yeah. By the way, I mean, I remember because I was thinking about the Walrus operator, and I'll ask you about it later, but it hit me that like the equal sign for assignment.
Yeah.
Like, why are we using the equal sign
it's
for
wrong.
assignment?
Yeah. and that's not the only solution, right? So if you look at Pascal, they use colon equals for assignment and equals for equality, and they use like less than greater than instead of the not equal thing.
Yeah.
Like there are other answers here.
So, but like, and yeah, like SQL, but how do you then decide to break convention, to say, you know what? This, everybody's doing it wrong. We're gonna do it right.
Yeah. So it's like an ROI, like return on investment trade-off, right? So if you do something weird, let's just say like not like colon equal instead of equal for assignment, that would be weird with today's aesthetic, right? And so you'd say, cool, this is theoretically better, but is it better in which ways? Like, what do I get out of that? Do I define away a class of bugs? Well, one of the class of bugs that C has is that you can use like, if X equals without equals, if X equals Y.
Yeah.
Right. Well, turns out you can solve that problem in lots of ways. Clang, for example, GCC, all these compilers will detect that as a likely bug, produce a warning.
Do they?
Yeah.
I feel like they didn't. Or Clang does.
Didn't.
GCC didn't. And it's like one of the important things about programming language design is like you're literally creating suffering in the world.
Okay.
Like I feel like I mean, one way to see it is the bicycle for the mind, but the other way is to like minimizing suffering.
Well, you have to decide if it's worth it, right? And so let's come back to that.
Okay.
But if you look at this, and again, this is where there's a lot of detail that goes into each of these things. Equal in C returns a value.
Yep.
That's messed up. That allows you to say X equals Y equals Z. Like that works in C.
Yeah. Is it messed up? You know,
well, so that
most people think it's messed up. I think
it is very by messed up. What I mean is, it is very rarely used for good, and it's often used for bugs.
Yeah,
right. And so
that's a good definition of messed up. Yeah,
you could use. You know, it's in hindsight, this was not such a great idea. Right now, one of the things with Swift that is really powerful, and one of the reasons it's actually good versus it being full of good ideas, is that when we launched Swift 1, we announced that it was public, people could use it, people could build apps, but it was going to change and break. Okay. When Swift 2 came out, we said, hey, it's open source, and there's this open process which people can help evolve and direct the language. So the community at large, like Swift users, can now help shape the language as it is. And what happened is that as part of that process is a lot of really bad mistakes got taken out. Mm-hmm. So for example, Swift used to have the C style plus and minus operators. Like, what does it mean when you put it before versus after? Right. Well, that got cargo culted from C into Swift early on.
What's cargo culted?
Cargo culted means brought forward without really considering it.
Okay.
This is maybe not the most PC term, but
I have to look it up in Urban Dictionary. Yeah.
Yeah. So it got pulled. It got pulled into C it got pulled into Swift without very good consideration. And we went through this process, and one of the first things got ripped out was plus and minus because they lead to confusion. They have very little value over saying, X plus equals 1, and X plus equals 1 is way more clear. And so when you're optimizing for teachability and clarity and bugs and this multidimensional space that you're looking at, things like that really matter. And so being first principles on where you're coming from and what you're trying to achieve and being anchored on the objective is really important.
Bach, if somebody looked at Don Knuth code, would they be able to tell that this is a distinct style of thinking going on here? What do you think? And what would be the defining characteristic of the style?
Well, my code now is literate programming, so it's a combination of English and C mostly. But if you just looked at the C part of it, you would also probably notice that I don't that I use a lot of global variables that other people don't, and I expand things inline more than instead of calling. Anyway, I have different subset of C that I use.
Okay, but that's a little bit stylistic.
Yeah. But with literate programming, you alternate between English and C or whatever. And
by the way, people listening to this should look up literate programming. It's a very interesting concept that you proposed and developed over the years.
Yeah. That's the most significant thing, I think, to come out of the tech project is that I realized that my programs were to be read by people and not just by computers, and that typography could massively enhance that, and so I mean they're just wonderful. If they're going to look it up, that they should also look up this book called Physically Based Rendering. Mm-hmm. By Matt Farr and anyway, it got an Academy Award, but all the graphic effects you see in movies, are accomplished by algorithms. And this book, the whole book is a literate program. It tells you not only how you do all the shading and bringing images in that you need for animation and textures and so on, but it also you can run the code. Mm-hmm. So I find it an extension of the way of how to teach programming is by is by telling a story as part of the program.
So it works as a program, but it's also readable by humans.
Yes, and especially by me. A week later or a year later.
That's a good test. If you yourself understand the code easily a week or a month or a year later.
Yeah. So it's let's just face it, it's the greatest thing since sliced bread. So.
Programming or literate?
Literate program.
Okay. You heard it here first. Okay. You dodged this question in an interview I listened to. So let me ask you again here. What makes for a beautiful program?
What makes for a beautiful program?
Yeah. What are the characteristics you see? Like you just said, literate programming. What are the characteristics you see in a program that make you sit back and say, that's pretty good?
Well, the reason I didn't answer is because there are dozens and dozens of answers to that. Because each you can define beauty. The same person will define beauty a different way from hour to hour. I mean, it depends on what you're looking for. At one level, it's beautiful just if it works at all. At another level, it's beautiful if it can be understood easily. It's beautiful if it's a literate programming, it's beautiful. It makes you laugh. I mean,
I'm with you. I think beauty, if it's readable, is if you understand what's going on and also understand the elegance of thought behind it. And then also, as you said, wit and humor. I was always, I remember having this conversation. I had this conversation on Stack Overflow, whether humor is good in comments. And I think it is.
Whether humor is good in comments.
Like when you add comments in the code.
Yeah.
I always thought a little bit of humor is good. It shows personality. Mm-hmm. It shows character, shows wit and fun and all those kinds of things of the personality of the programmer.
Yeah. Okay. So a couple days ago, I received a wonderful present from my former editor at Addison Wesley. He's downsizing his house, and he found that somebody at the company had found all of their internal files about the art of computer programming from the 1960s, and they gave it to him. And then before throwing it in the garbage. And then so he said, "Oh yeah, he planned to keep it for posterity, but now he realized that posterity is a bit too much for him to handle, so he sent it to me." And so I just received this big stack of letters, some of which I had written to them, but many of which they had written to early guinea pigs who telling them whether they should publish or not, and one of the things was in the comments to volume 1, the major reader was Bob Floyd, who was my great co-worker in the 60s, died early, unfortunately, but he commented about the humor in it, and so we had we ran it by me, says keep this joke in or not, they also sent it out to focus groups. What do you think about humor in a book about computer programming?
What's the conclusion?
And I stated my philosophy is it said the ideal thing is that it's something where the reader knows that there's probably a joke here if he only understood it, and this is a motivation to understand, to think about it a little bit. But anyway, it's a very delicate humor. It's really each century invents a different kind of humor too. I mean, and different cultures have different kinds of humor.
We talked about Russia a little bit offline. There's dark humor, and there's when a country goes through something difficult,
right? Saturday Night Live and stuff like this,
exactly.
and Jack Benny. I mean, Steve Allen wrote this book about humor, and it was the most boring book. But he was one of my idols. But yeah, it's called The Funny Men or something like that. But yeah, okay. So anyway, I think it's important to know that this is part of life, and it should be fun and not.
Yeah.
And so I wrote this organ composition, which is based on the Bible, but I didn't refrain from putting little jokes in it also in the music.
It's hidden in the music.
It's there, yeah.
A little humor is okay?
Yeah, I mean, not egregious humor. So in this correspondence, there were things I said, yeah, I really shouldn't have done that. But other ones I insisted on, and I've got jokes in there that nobody has figured out yet. In fact, in volume 2, I've got a cryptogram, a message enciphered, and in order to decipher it, you're going to have to break an RSA key, which is larger than people know how to break. And so, if computers keep getting faster and faster, then might be 100 years, but somebody will figure out what this message is, and they will laugh. I mean, I've got a joke in there.
So that one you really have to work for. I don't know if you've heard about this. Can you take on the impossible task and give a brief history of programming languages from your perspective?
So I guess you could say programming languages started probably in the late 40s or something like that. People used to program computers by basically putting in zeros and ones using something like switches on a console, and then, or maybe holes in paper tapes, something like that. So extremely tedious, awful, whatever. And so I think the first programming languages were relatively crude assembly languages where people would basically write a program that would convert mnemonics like add, ADD, into whatever the bit pattern was that corresponded to an add instruction. And they would do the clerical work of figuring out where things were. So you could put a name on a location in a program, and the assembler would figure out where that corresponded to when the thing was all put together and dropped into memory. Early on, and this would be the late 40s and very early 50s, there were assemblers written for the various machines that people used. You may have seen in the paper just a couple of days ago, Tony Burker died. He did this thing in Manchester called Autocode, a language which I knew only by name. But it sounds like it was a flavor of assembly language, sort of a little higher in some ways. And it replaced a language that Alan Turing wrote, which you put in zeros and ones. But you put them in backwards order because that was how the hardware worked. Very strange.
That's right. Yeah, that's right. It's backwards.
So assembly languages, then, let's call that the early 1950s. And so every different flavor of computer has its own assembly language. So the EDSAC had its, and the Manchester had its, and the IBM, whatever, 7090 or 704 or whatever had its, and so on. So everybody had their own assembly language.
And assembly languages have a few commands, addition, subtraction, and branching of some kind, if then type of situation.
Right. They have exactly, in their simplest form at least, one instruction per, or one assembly language instruction per instruction in the machine's repertoire. Right. And so you have to know the machine intimately to be able to write programs in it. And if you write an assembly language program for one kind of machine and then you say, gee, it's nice, I'd like it in a different machine, start over. Okay. So very bad. And so what happened in the late 50s was people realized you could play this game again and you could move up a level in writing or creating languages that were closer to the way that real people might think about how to write code. And there were, I guess, arguably 3 or 4 at that time period. There was Fortran, which came from IBM, which was formula translation, meant to make it easy to do scientific and engineering computations.
I didn't know that. Formula translation.
That's what
wow.
it stood for.
Yeah.
There was COBOL, which is the common business-oriented language that Grace Hopper and others worked on, which was aimed at business kinds of tasks. There was ALGOL, which was mostly meant to describe algorithmic computations. I guess you could argue BASIC was in there somewhere. I think it's just a little later. And so all of those moved the level up. And so they were closer to what you and I might think of as we were trying to write a program. And they were focused on different domains. Fortran for formula translation, engineering computations, let's say, COBOL for business, that kind of thing.
And still used today, at
Still
least
used
Fortran
today.
probably.
Oh, yeah. COBOL, too.
COBOL.
But the deal was that once you moved up that level, then you, let's call it Fortran, you had a language that was not tied to a particular kind of hardware, because a different compiler would compile for a different kind of hardware. And that meant two things. It meant you only had to write the program once, which was very important. And it meant that you could, in fact, if you were a random engineer, physicist, whatever, you could write that program yourself. You didn't have to hire a programmer to do it for you. Might not be as good as you'd get with a real programmer, but it was pretty good. And so it democratized and made much more broadly available the ability to write code.
So it puts the power of programming into the hands of people like you.
Yeah. Anybody who wants to, is willing to invest some time in learning a programming language and is not then tied to a particular kind of computer. And then in the 70s, you get system programming languages, of which C is the survivor. And
what does system programming languages mean?
Programming languages that would take on the kinds of things that were necessary to write so-called system programs, things like text editors or assemblers or compilers or operating systems themselves, those kinds of things. And Fortran...
They have to be feature rich. They have to be able to do a lot of stuff, a lot of memory management, the access processes and all that kind of stuff. Parallel processing.
It's a different flavor of what they're doing. They're much more in touch with the actual machine but in a positive way. That is, you can talk about memory in a more controlled way. You can talk about the different data types that the machine supports in a way and more ways to structure and organize data. And so the system programming languages, there was a lot of effort in that in the, call it the late 60s, early 70s. C is, I think, the only real survivor of that. And then what happens after that, you get things like object-oriented programming languages, because as you write programs in a language like C, at some point scale gets to you and it's too hard to keep track of the pieces, and there's no guardrails or training wheels or something like that to prevent you from doing bad things. So C++ comes out of that tradition.
And then it took off from there. I mean, there's also a slightly parallel track with a little bit of the functional stuff with Lisp and so on. But I guess from that point, it's just an explosion of languages. Yeah, there's the Java story, there's the JavaScript, there's all the stuff that the cool kids these days are doing with Rust and all that. Yeah. So you said you're not a very good programmer.
True.
You're the world's most modest human being. Okay, but you'll continue saying that. I understand how this works, but you do radiate a sort of love for programming. So let me ask, do you think programming is more an art or a science? Is it creativity or kind of rigor?
I think it's some of each. It's some combination. Some of the art is figuring out what it is that you really want to do. What should that program be? What would make a good program? And that's some understanding of what the task is, what the people who might use this program want. And I think that's art in many respects. The science part is trying to figure out how to do it well. And some of that is real computer sciencey stuff, like what algorithm should we use at some point? Mostly in the sense of being careful to use algorithms that will actually work properly, scale properly, avoiding quadratic algorithms when a linear algorithm should be the right thing. That kind of more formal view of it. Same thing for data structures. But also it's, I think, an engineering field as well. And engineering is not quite the same as science, because engineering, you're working with constraints. You have to figure out not only what is a good algorithm for this kind of thing, but what's the most appropriate algorithm given the amount of time we have to compute, the amount of time we have to program, what's likely to happen in the future with maintenance, who's going to pick this up in the future, all of those kind of things that if you're an engineer, you get to worry about. Whereas if you think of yourself as a scientist, well, you can maybe push them over the horizon in a way. And if you're an artist, what's that?
So just on your own personal level, what's your process like of writing a program? Say, small and large, sort of tinkering with stuff. Do you just start coding right away and just kind of evolve iteratively with a loose notion? Or do you plan on a sheet of paper first and then kind of design in what they teach you in the kind of software engineering courses in undergrad or something like that? What's your process like?
It's certainly much more the informal, incremental. First, I don't write big programs at this point. It's been a long time since I wrote a program that was more than, I call it a few hundred or more lines, something like that. Many of the programs I write are experiments for either something I'm curious about or often for something that I want to talk about in a class. And so those necessarily tend to be relatively small. A lot of the kind of code I write these days tends to be for sort of exploratory data analysis, where I've got some collection of data and I want to try and figure out what on earth is going on in it. And for that, those programs tend to be very small. Sometimes you're not even programming, you're just using existing tools like counting things. Or sometimes you're writing awk scripts because 2 or 3 lines will tell you something about a piece of data. And then when it gets bigger, well, then I will probably write something in Python. Because that scales better up to, call it a few hundred lines or something like that. And it's been a long time since I wrote programs that were much more than that.
So what's to you, so you wrote a book, C programming language, and C is probably one of the most important languages in the history of programming languages. If you kind of look at impact, what do you think is the most elegant or powerful part of C? Why did it survive? Why did it have such a long-lasting impact?
I think it found a sweet spot of expressiveness, so you could really write things in a pretty natural way, and efficiency, which was particularly important when computers were not nearly as powerful as they are today. You've got to put yourself back 50 years almost in terms of what computers could do. That's, roughly 4 or 5 generations, decades of Moore's Law, right? So expressiveness and efficiency and, I don't know, perhaps the environment that it came with as well, which was Unix. So it meant if you wrote a program, it could be used on all those computers that ran Unix, and that was all of those computers because they were all written in C, and that was Unix, the operating system itself was portable, as were all the tools. So it all worked together, again, in one of these things where things fed on each other in a positive cycle.
What did it take to write sort of a definitive book, probably a definitive book on all of programming? Like, it's more definitive to a particular language than any other book on any other language, and did 2 really powerful things, which is popularized the language, at least from my perspective, maybe you can correct me, and second is created a standard of how how this language is supposed to be used and applied. So what did it take? Did you have those kinds of ambitions in mind when you were working on that?
Is this some kind of joke? No, of course not.
So it's an accident of timing, skill, and just luck.
A lot of it is clearly timing was good. Dennis and I wrote the book in 1977.
Dennis Ritchie.
Yeah, right. And at that point, Unix was starting to spread. I don't know how many there were, but it would be dozens to hundreds of Unix systems. And C was also available on other kinds of computers that had nothing to do with Unix. And so the language had some potential. And there were no other books on C. And Bell Labs was really the only source for it. And Dennis, of course, was authoritative because it was his language. And he had written the reference manual, which is a marvelous example of how to write a reference manual. Really, really very, very well done. So I twisted his arm until he agreed to write a book, and then we wrote a book. And the virtue or advantage, at least, I guess, of going first is that then other people have to follow you if they're going to do anything. And I think it worked well because Dennis was a superb writer. I mean, he really, really did. And the reference manual in that book is his, period. I had nothing to do with that at all. So just crystal clear prose and very, very well expressed. And then he and I wrote most of the expository material. And then he and I sort of did the usual ping-ponging back and forth, refining it. But I spent a lot of time trying to find examples that would sort of hang together and that would tell people what they might need to know at about the right time that they should be thinking about needing it. And I'm not sure it completely succeeded, but it mostly worked out fairly well.
What do you think is the power of example? I mean, you're the creator, at least one of the first people to do the Hello World program, which is like the example. If aliens discover our civilization hundreds of years from now, it'll probably be Hello World programs, just like a half-broken robot communicating with them with the Hello World. So and that's a representative example. So what do you find powerful about examples?
I think a good example will tell you how to do something, and it will be representative of you might not want to do exactly that, but you will want to do something that's at least in that same general vein. And so a lot of the examples in the C book were picked for these very, very simple, straightforward text processing problems that were typical of Unix. I want to read input and write it out again. There's a copy command. I want to read input and do something to it and write it out again. There's a grep. And so that kind of find things that are representative of what people want to do and spell those out so that they can then take those and see the core parts and modify them to their taste. And I think that a lot of programming books that I don't look at programming books a tremendous amount these days, but when I do, a lot of them don't do that. They don't give you examples that are both realistic and something you might want to do. Some of them are pure syntax. Here's how you add 3 numbers. Well, come on, I could figure that out. Tell me how I would get those 3 numbers into the computer and how I would do something useful with them, and then how I put them back out again, neatly formatted.
And especially if you follow that example, there is something magical of doing something that feels useful.
Yeah, right. And I think it's the attempt, and it's absolutely not perfect, but the attempt in all cases was to get something that was going to be either directly useful or would be very representative of useful things that a programmer might want to do. But within that vein of fundamentally text processing, reading text, doing something, writing text.
So if you can comment on all the other languages, does it break your heart that you'll never get to explore them? Or how do you feel about the full variety?
It's not break my heart, but I would love to be able to try more of these languages. The closest I've come is in a class that I often teach in the spring here. It's a programming class, and I often I have one sort of small example that I will write in as many languages as I possibly can. I've got it in 20 odd languages at this point. And that's, so I do a minimal experiment with a language just to say, okay, I have this trivial task, which I understand the task, and it takes 15 lines in awk and not much more in a variety of other languages. So how big is it? How fast does it run? And what pain did I go through to learn how to do it? And it's like anecdata, right? It's very, very, very narrowly focused.
Anecdata, I like that term. So yeah, but still, it's a little sample because you get to, I think the hardest step of the programming language is probably the first step, right? So there you're taking the first step.
Yeah. And so my experience, with some languages is very positive, like Lua, a scripting language I had never used. And I took my little program. The program is a trivial formatter. It just takes in lines of text of varying lengths, and it puts them out in lines that have no more than 60 characters on each line. So think of it as just kind of the flow of process in a browser or something. So it's a very short program. And in Lua, I downloaded Lua, and in an hour I had it working. Never having written Lua in my life, just going with online documentation. I did the same thing in Scala, which you can think of as a flavor of Java, equally trivial. I did it in Haskell. It took me several weeks, but it did run like a turtle. And I did it in Fortran 90, and it painful, but it worked. Yeah. And I tried it in Rust, and it took me several days to get it working because the model of memory management was just a little unfamiliar to me. And the problem I had with Rust, and it's back to what we were just talking about, I couldn't find good, consistent documentation on Rust. Now, this was several years ago, and I'm sure things have stabilized. But at the time, everything in the Rust world seemed to be changing rapidly. And so you would find what looked like a working example, and it wouldn't work with the version of the language that I had. So it took longer than it should have. Rust is a language I would like to get back to, but probably won't. I think one of the issues, you have to have something you want to do. And if you don't have something that is the right combination, if I want to do it and yet I have enough disposable time, whatever, to make it worth learning a new language at the same time, it's never going to end.
Okay. What's your perfect programming setup? What computer, what operating system, what keyboard, what editor?
Yeah, perfect is too strong a word. It's way too strong a word. What I use by default, I have at this point, a 13-inch MacBook Air, which I use because it's kind of a reasonable balance of the various things I need. I can carry it around. It's got enough computing horsepower. Screen's big enough. The keyboard's okay. And so I basically do most of my computing on that. I have a big iMac in my office that I use from time to time as well, especially when I need a big screen, but otherwise it tends not to be used as much.
Editor.
I use mostly SAM, which is an editor that Rob Pike wrote long ago at Bell Labs. And
did that, sorry to interrupt, does that precede VI? Does that precede Emacs?
It post dates both VI and Emacs. It is derived from Rob's experience with ED and VI.
What's ED?
That's the original Unix editor.
Oh, wow.
Dated probably before you were born.
So what's the history of editors? Can you briefly, because it's such a fact, I use Emacs, I'm sorry to say, sorry to come out with that, but what's the kind of interplay there? So SAM, Emacs, and VI.
So in ancient times, like call it the first time-sharing systems, going back to what we were talking about, there were editors. There was an editor on CTSS that I don't even remember what it was called. It might have been Edit, where you could type text, program text, and it would do something, or document text.
You could save the
and
text,
save it. You could edit it. The usual thing that you would get in an editor. And Ken Thompson wrote an editor called QED, which was very, very powerful. But these were all totally command-based. They were not mouse or cursor-based because it was before mice and even before cursors, because they were running on terminals that printed on paper. Okay, no CRT-type displays, let alone LEDs. And so then when Unix came along, Ken took QED and stripped it way, 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 way down. And that became an editor that he called ED. And it was very simple, but it was a line-oriented editor. And so you could load a file, and then you could talk about the lines 1 through the last line, and you could print ranges of lines. You could add text, you could delete text, you could change text, or you could do a substitute command that would change things within a line or within groups of lines.
So you can work on parts of a file, essentially.
Yeah, you could work on any part of it, the whole thing or whatever, but it was entirely command line based, and it was entirely on paper. Okay, paper. And that meant that you changed real paper. And so if you changed the line, you had to print that line using up another line of paper to see what the change caused. Okay.
Yeah.
So when CRT displays came along, then you could start to use cursor control, and you could sort of move where you were on the screen in
without reprinting every time.
Printing. And there were a number of editors there. The one that I was most familiar with and still use is VI, which was done by Bill Joy. And so that dates from probably the late 70s as a guess. And it took full advantage of the cursor controls. I suspect that Emacs was roughly at the same time, but I don't know. I've never internalized Emacs. So I use, at this point, I stopped using ED, although I still can. I use VI sometimes, and I use SAM when I can.
And SAM is available on most systems?
It is available. You have to download it yourself from typically the Plan 9 operating system distribution. It's been maintained by people there. And so
I'll get home tonight. I'll try it. It's cool. Yeah. It sounds fascinating. Although my love is with Lisp and Emacs, I've went into that hippie world of.
I think it's a lot of things. What religion were you brought up with?
Yeah, that's true. That's true. Most of the actual programming I do is C, C++, and Python, but my weird my religious upbringing is in Lisp. So So what do you think about another language of JavaScript that's this? Well, let me just sort of comment on what I said. When I was brought up, sort of JavaScript was seen as the probably like the ugliest language possible, and yet it's quite arguably, quite possibly taking over not just the front end, the back end of the internet, but possibly in the future taking over everything, because they've now learned to make it very efficient.
Yeah.
And so what do you think about this?
Yeah, well, I think you captured it in a lot of ways. When it first came out, JavaScript was deemed to be fairly irregular and an ugly language. And certainly in the academy, if you said you were working on JavaScript, people would ridicule you. It was just not fit for academics to work on. I think a lot of that has evolved. The language itself has evolved. And certainly the technology of compiling it is fantastically better than it was. And so in that sense, it's a absolutely a viable solution on back ends as well as the front ends. Used well, I think it's a pretty good language. I've written a modest amount of it, and I've played with JavaScript translators and things like that. I'm not a real expert, and it's hard to keep up even there with the new things that come along with it. So I don't know whether it will ever take over the world. I think not, but it's certainly an important language and worth knowing more about.
There's maybe to get your comment on something, which JavaScript and actually most languages, sort of Python, such a big part of the experience of programming with those languages includes libraries, sort of building on top of the code that other people have built. I think that's probably different from the experience that we just talked about from Unix and C days when you're building stuff from scratch. What do you think about this world of essentially building up libraries on top of each other and leveraging them?
Yeah, no, that's a very perceptive kind of question. One of the reasons programming was fun in the old days was that you were really building it all yourself. Yeah. The number of libraries you had to deal with was quite small. Maybe it was printf or the standard library or something like that. And that is not the case today. And if you want to do something you mentioned Python and JavaScript, and those are the two fine examples, you have to typically download a boatload of other stuff, and you have no idea what you're getting. Absolutely nothing. Yeah. I've been doing some playing with machine learning over the last couple of days, and gee, something doesn't work. Well, you pip install this, okay, and down comes another gazillion megabytes of something, and you have no idea what it was. And if you're lucky, it works. And if it doesn't work, you have no recourse. There's absolutely no way you could figure out which in these 1,000 different packages. And I think it's worse in the NPM environment for JavaScript. I think there's less discipline, less control there.
And there's aspects of not just not understanding how it works, but there's security issues, there's robustness issues. So you don't want to run a nuclear power plant using JavaScript, essentially.
Probably not.
So speaking to the variety of languages, do you think that variety is good, or do you think that over time we should converge towards 1, 2, 3 programming languages? That you mentioned to the Bell Lab days when people could sort of the community of it, and the more languages you have, the more you separate the communities. There's the Ruby community, there's the Python community, there's the C++ community. Do you hope that they'll unite one day to just 1 or 2 languages?
I certainly don't hope it. I'm not sure that that's right, because I honestly don't think there is one language that will suffice for all the programming needs of the world. Are there too many at this point? Well, arguably. But I think if you look at the sort of the distribution of how they are used, there's something called a dozen languages that probably account for 95% of all programming at this point. Yeah. And that doesn't seem unreasonable. And then there's another, 2,000 languages that are still in use that nobody uses, or at least don't use in any quantity. But I think new languages are a good idea in many respects, because they're often a chance to explore an idea of how a language might help. I think that's one of the positive things about functional languages. For example, they're a particularly good place where people have explored ideas that at the time didn't seem feasible, but ultimately have wound up as part of mainstream languages as well. I mean, you just go back as early as recursion in Lisp, and then follow forward with functions as first-class citizens and pattern-based languages and, closures and just on and on and on. Lambdas, interesting ideas that showed up first in, let's call it broadly, the functional programming community, and then find their way into mainstream languages.
Yeah, it's a playground for rebels.
Yeah, exactly.
So-
and so I think the languages in the playground themselves are probably not going to be the mainstream, at least for some while, but the ideas that come from there are invaluable.
Okay, another absurd question about intelligent life, because you're an incredible programmer. Outside of everything else we'll talk about, just as a programmer, do you think intelligent beings out there, the civilizations that were out there, had computers and programming? Do we naturally have to develop something where we engineer machines and are able to encode both knowledge into those machines and instructions that process that knowledge, process that information to make decisions and actions and so on? And would those programming languages, if you think they exist, be at all similar to anything we've developed?
So I don't see that much of a difference between quote unquote natural languages and programming languages.
Yeah.
I think there's so many similarities. So when asked the question, what do alien languages look like? I imagine they're not all that dissimilar from ours. And I think translating in and out of them wouldn't be that crazy.
Well, it's difficult to compile like DNA to Python and then to C. I mean, there is a little bit of a gap in the kind of languages we use for Turing machines and the kind of languages nature seems to use. A little bit. Maybe that's just we haven't understood the kind of language that nature uses well yet.
DNA is a CAD model. It's not quite a programming language. It has no sort of serial execution. It's not quite it's a CAD model. So I think in that sense, we actually completely understand it. The problem is, simulating on these CAD models. I played with it a bit this year. Is super computationally intensive. If you want to go down to like the molecular level, where you need to go to see a lot of these phenomena like protein folding. So yeah, it's not that we don't understand it. It just requires a whole lot of compute to kind of compile it.
For our human minds, it's inefficient both for the data representation and for the programming.
Yeah, it runs well on raw nature. Yeah. It runs well on raw nature, and when we try to build emulators or simulators for that, they're mad slow. And I've tried it.
It runs in. You've commented elsewhere. I don't remember where that one of the problems is simulating nature is tough, and if you want to sort of deploy a prototype, I forgot how you put it, but it made me laugh. But animals or humans would need to be involved in order to try to run some prototype code on, like if we're talking about COVID and viruses and so on.
Yeah.
If you were trying to engineer some kind of defense mechanisms, like a vaccine against COVID or all that kind of stuff, that doing any kind of experimentation like you can with like autonomous vehicles would be very technically and ethically costly.
Well, I'm not sure about that. I think you can do tons of crazy biology in test tubes. I think my bigger complaint is more, the tools are so bad.
Like literally? You mean like
I'm not,
libraries and...
I don't know, I'm not pipetting shit. Like you're handing me I gotta... No, there has to be some.
Like automating stuff. And like but human biology is messy. Like it seems...
But like, look at those Theranos videos. They were a joke. It's like a little gantry. It's like a little XY gantry high school science project with the pipette. I'm like, really?
Got to be something better.
You can't build like nice microfluidics and I can program the, computation to biointerface. I mean, this is going to happen. But like right now, if you are asking me to pipette 50 milliliters of solution, I'm out. This is so crude.
Yeah. Okay. let me drag you back to programming for a sec. What maybe 3 to 5 programming languages should people learn, do you think? Like, if you look at yourself, what did you get the most out of from learning?
Well, so everybody should learn C and assembly. We'll start with those two. Right?
Assembly?
Yeah. If you can't code in assembly, you don't know what the computer's doing. You don't understand, you don't have to be great in assembly, but you have to code in it. And then, you have to appreciate assembly in order to appreciate all the great things C gets you. And then you have to code in C in order to appreciate all the great things Python gets you. So I'll just say assembly, C, and Python. We'll start with those 3.
The memory allocation of C and the fact that so assembly is to give you a sense of just how many levels of abstraction you get to work on in modern day programming.
Yeah. Graph coloring for assignment, register assignment, and compilers.
Yeah.
You got to do. The computer only has a certain number of registers. Yet you can have all the variables you want in a C function.
So you get to start to build intuition about compilation, like what a compiler gets you. What else?
Well, then there's kind of so those are all very imperative programming languages. Then there's 2 other paradigms for programming that everybody should be familiar with. One of them is functional. You should learn Haskell and take that all the way through. Learn a language with dependent types like Coq. Learn that whole space, like the very PL theory heavy languages.
And Haskell is your favorite functional? Is that the go-to, you'd say?
Yeah, I'm not a great Haskell programmer. I wrote a compiler in Haskell once. There's another paradigm, and actually there's one more paradigm that I'll even talk about after that I never used to talk about when I would think about this. But the next paradigm is learn Verilog or VHDL. Understand this idea of all of the instructions execute at once. If I have a block in Verilog and I write stuff in it, it's not sequential. They all execute at once. And then think like that. That's how hardware works.
So I guess assembly doesn't quite get you that. Assembly is more about compilation, and Verilog is more about the hardware, giving a sense of what actually is the hardware is doing.
Assembly, C, Python are straight, they sit right on top of each other. In fact, C is kind of coded in C, but you could imagine the first C was coded in assembly, and Python is actually coded in C. So you can straight up go on that.
Got it. And then Verilog gives you that's brilliant. Okay. So,
and then I think there's another one now. Karpathy calls it programming 2.0, which is don't learn TensorFlow, learn PyTorch.
So machine learning. Yeah. We got to come up with a better term than programming 2.0 but yeah.
It's a programming language. Learn it.
I wonder if it can be formalized a little bit better. It feels like we're in the early days of what that actually entails.
Data-driven programming?
Data-driven programming, yeah. But it's so fundamentally different as a paradigm than the others. It almost requires a different skill set. But you think it's still, yeah. And PyTorch versus TensorFlow, PyTorch wins.
It's the 4th paradigm. It's the 4th paradigm that I've kind of seen. There's this, imperative, functional, hardware. I don't know a better word for it. And then ML.
Do you have advice for people that want to, get into programming, want to learn programming? You have a video. What is programming? Noob lessons! ! And I think the top comment is warning. This is not for noobs. Do you have a noob TLDW for that video, but also a noob friendly advice on how to get into programming?
You are never going to learn programming by watching a video called Learn Programming. The only way to learn programming, I think, and the only way everyone I've ever met who can program well learned it all in the same way. They had something they wanted to do, and then they tried to do it. And then they were like, oh, well, okay, this is kind of, it'd be nice if the computer could kind of do this thing. And then, that's how you learn. You just keep pushing on a project. So the only advice I have for learning programming is go program.
Somebody wrote to me a question they were looking to learn about recurrent neural networks. And he's saying, my company's thinking of using recurrent neural networks for time series data, but we don't really have an idea of where to use it yet. we just want to like, do you have any advice on how to learn about these kind of general machine learning questions? And I think the answer is like actually have a problem that you're trying to solve, and just.
I see that stuff. Oh my God, when people talk like that, they're like, I heard machine learning is important. Could you help us integrate machine learning with macaroni and cheese production? You can't help these people. Like, who lets you run anything? Who lets that kind of person run anything?
I think we're all beginners at some point. So
it's not like they're a beginner. It's like, my problem is not that they don't know about machine learning. My problem is that they think that machine learning has something to say about macaroni and cheese production. Or like, I heard about this new technology. How can I use it for why? Like, I don't know what it is, but how can I use it for why?
That's true. And you have to build up an intuition of how, because you might be able to figure out a way, but like the prerequisite is you should have a macaroni and cheese problem to solve first.
Exactly.
And then 2, you should have more traditional, like in the learning process should involve more traditionally applicable problems in the space of whatever that is of machine learning, and then see if it can be applied to macaroni.
At least start with tell me about a problem. Like if you have a problem, you're like, some of my boxes aren't getting enough macaroni in them. Can we use machine learning to solve this problem? Yeah. That's much, much better than how do I apply machine learning to macaroni and cheese?
Okay, let's talk about a fun topic, which is programming. Here's another book idea for you. Let me pitch. What's your perfect programming setup? So like, this by George Hotz. So like, what? Listen, you're
give me a MacBook Air, sit me in a corner of a hotel room, and I'll still have.
So you really don't care. You don't fetishize like multiple monitors, keyboard.
Those things are nice, and I'm not going to say no to them. But do they automatically unlock tons of productivity? No, not at all. I have definitely been more productive on a MacBook Air in a corner of a hotel room.
What about IDE? So which operating system do you love? What text editor do you use? IDE? What is there something that is like the perfect, if you could just say the perfect productivity setup for George Hotz?
Doesn't matter.
Doesn't matter.
It literally doesnn't matter. I guess I code most of the time in Vim. Like literally, I'm using an editor from the 70s. You didn't make anything better. Okay, VS Code is nice for reading code. There's a few things that are nice about it. I think that you can build much better tools. How like IDA's Xrefs work way better than VS Codes. Why?
Yeah, actually, that's a good question. Like, why? I still use Emacs for most. I've actually never. I have to confess something dark.
Yeah.
So I've never used Vim.
Yeah.
I think maybe I'm just afraid that my life has been a waste. I'm not evangelical about Emacs. I think
this is how I feel about TensorFlow versus PyTorch.
Yeah.
Having just we've switched everything to PyTorch now, put months into the switch, I have felt like I've wasted years on TensorFlow. I can't believe it. I can't believe how much better PyTorch is.
Yeah.
I've used Emacs and Vim. Doesn't matter.
Yeah, still just my heart somehow. I fell in love with Lisp. I don't know why. You can't. The heart wants what the heart wants. I don't understand it, but it just connected with me. Maybe it's the functional language that first I connected with. Maybe it's because so many of the AI courses before the deep learning revolution were taught with Lisp in mind. I don't know what it is, but I'm stuck with it. But at the same time, like, why am I not using a modern IDE for some of these programming languages? I don't know.
They're not that much better. I've used modern IDEs too.
But at the same time, so like not to disagree with you, but like I like multiple monitors. Like I have to do work on a laptop, and it's a pain in the ass. And also I'm addicted to the Kinesis weird keyboard. You could see there. Yeah. So you don't have any of that. You can just be on a MacBook.
I mean, look, at work I have 3 24-inch monitors. I have a happy hacking keyboard. I have a Razer Death Header mouse.
But it's not essential for you. What are some, from a programmer perspective, what makes a good programmer? What makes a productive programmer? Is there a device you can give to be a great programmer in this world?
Great question. And there are times in my life I'd probably answer this even better than I hope maybe give an answer today. Because I thought about this numerous times. Like right now, I've spent on so much time recently hiring salespeople that
your mind is a little bit on something else.
On something else. But I reflected on the past, and also, I have the only way I can do this is I have some really great programmers that I work with who lead the teams that they lead. And my goal is to inspire them and hopefully help them, encourage them, and help them encourage with their teams. I would say there's a couple of things. One is curiosity. Like I think a programmer without curiosity is mundane. Like you'll lose interest. You won't do your best work. So it's an affect. It's sort of have some curiosity about things. Mm-hmm. I think 2, don't try to do everything at once. Recognize that we're limited as humans. You're limited as a human, mm-hmm. and each one of us are limited in different ways. We all have our different strengths and skills. So it's adapting the art of programming to your skills. One of the things that always works is to limit what you're trying to solve, mm-hmm. right? So if you're part of a team, usually maybe somebody else has put the architecture together and they've given a portion for you. If you're young, mm-hmm. if you're not part of a team, it's sort of breaking down the problem into smaller parts is essential for you to make progress. Mm-hmm. It's very easy to take on a big project and try to do it all at once, and you get lost, and then you do it badly. And so thinking about, very concretely what you're doing, defining the inputs and outputs, defining what you want to get done. Even just talking about that like writing down before you write code, just what are you trying to accomplish? And being very specific about it really, really helps. I think using other people's work, right? Don't be afraid that somehow you're like you should do it all. Like nobody does.
Stand on the shoulders of giants and copy and paste from Stack Overflow.
Copy and paste from Stack Overflow. It's like, but don't just copy and paste. This is particularly relevant in the era of codecs and the auto-generated code, which is essentially I see as an indexing of Stack Overflow.
Right, exactly.
Essentially, it's like
it's a search engine.
It's a search engine over Stack Overflow, basically. So it's not. I mean, we've had this for a while.
Yeah.
But really, you want to cut and paste, but not blindly. Like, absolutely, I've cut and paste to understand. But then you understand. Oh, this is what this means. Oh, this is what it's doing, and understand as much as you can. So it's critical. That's where the curiosity comes in. If you're just blindly cutting and pasting, you're not going to understand. And so understand, and then be sensitive to hype cycles, right? Every few often there's always test-driven development is the answer. Oh, object-oriented is the answer. Oh, there's always an answer. Agile is the answer. Be cautious of jumping onto a hype cycle. Like, likely there's signal, like there's a thing there that's actually valuable you can learn from, but it's almost certainly not the answer to everything you need.
What lessons do you draw from you having created NumPy and SciPy, like in service of sort of answering the question of what it takes to be a great programmer and giving advice to people?
Yeah.
How can you be the next person to create a SciPy?
Yeah. So one is listen.
Two?
Listen.
To who?
To people that have a problem, right? Which is everybody, right? But listen to many and try to, and then do. Like, you're gonna have to do an experiment, fall down. Don't be afraid to fall down. Don't be afraid. The first thing you do is probably gonna suck, and that's okay, right? It's honestly, I think iteration is the key to innovation, and it's almost that psychological hesitation we have to just iterate. Like, yeah, we know it's not great, but next someone will be better. I mean, just keep learning and keep improving and keep improving. So it's an attitude, and then it doesn't take intense concentration, right? Good things don't happen just. It's not quite like TikTok or like Facebook. You can't scroll your way to good programming, right? There are sincere like hours of deep. Don't be afraid of the deep problem. Like, often people will run away from something because, I can't solve this. And you might be right, but give it an hour, give it a couple of hours and see. And, just 5 minutes not gonna give you that.
Was it lonely when you were building SciPy and NumPy?
Hugely, yeah, absolutely lonely in the sense of you had to have an inner drive. And that inner drive for me always comes from, I have to see that this is right in some angle. I have to believe it, that this is the right approach, the right thing to do. With SciPy, it was like, the world needs libraries in Python. Clearly, Python's popular enough with enough influential people to start, and it needs more libraries. So that is a good in of itself. So I'm going to go do that good. So find a thing that you know is good, and just work on it. So that has to happen, and it is. And you kind of have to have enough realization of your mission to be okay with the naysayer or the fact that not everybody joins you at front. In fact, one thing I've talked to people a lot, I've seen a lot of projects come and some fail. Like not everything I've done has actually worked perfectly. I've tried a bunch of stuff that, okay, that didn't really work, or this isn't working, and why. But you see the patterns. And one of the key things is you can't even know for 6 months. I say 18 months right now. If you're starting a new project, you got to give it a good 18-month run before you even know if the feedback's there. Like you're not going to know in 6 months. You might have the perfect thing, but 6 months from now, it's still emerging. So give it time, because you're dealing with humans, and humans have an inertia energy that just doesn't change that quickly. So
let me ask a silly question, but like you said, you're focused on the sales side of things currently, but back when you were actively programming, maybe in the 90s, you talked about IDEs. What's your a setup that you have that brings you joy? Keyboard, number of screens.
Yeah, I will.
Linux.
I do still like to program some. I just not as much as I used to. I have 2 projects I'm super interested in. Trying to find funding for them. Trying to figure out some good teams for them. But I could talk about those. But I'm an Emacs guy.
Great. Thank the superior editor, everybody. I don't often delete tweets, but one of the tweets I deleted when I said Emacs was better than Vim, and then the hate I got from
is.
I was like, I'm walking away from this.
I do too. I don't push it. I mean, I'm
just joking, of course.
But yeah, exactly. It's kind of like, but
it's
people
fun.
do take the editor seriously,
They take
right?
it. I did it as
but
a
it's
joke.
Your life.
It is. But there's something beautiful to me about Emacs. But for people that love Vim, there's something beautiful to them about that.
I mean, I do use Vim for quick editing, like command line. If I say quick editing, I will still sometimes use it, but not much. Like it's simple, correct a single editor character.
So when you were developing SciPy, you were using Emacs.
Yeah, SciPy and NumPy are all written in Emacs on a Linux box, and CVS, and then SVN version control. Git came later. Like Git has, I love distributed branch stuff. I think Git is pretty complicated, but I love the concept. And also, of course, GitHub is, and then GitLab make Git definitely consumable. But that came later.
Did you ever touch Lisp at all? What were your emotional feelings about all the parentheses?
Great question. So I find myself appreciating Lisp today much more than I did early, because when I came to programming, I knew programming, but I was a domain expert, right? And to me, the parentheses were in the way. It's like, wow, it's just all this, like, it just gets in the way of my thinking about what I'm doing. So why would I have all these, right? That was my initial reaction to it. Now as I appreciate kind of the structure that kind of naturally maps to a logical thinking about a program, I can appreciate them, right? And why it's actually, you could create editors that make it not so problematic, right? Honestly.
Yeah.
So I actually have a much more appreciation of Lisp and things like Clojure, and there's Hy-V, which is a Python, a Lisp that compiles the Python bytecode. I think it's challenging. Like typically these languages are I even saw a whole data science programming system in Lisp that somebody created, which is, cool. But again, I think it's the lack of recognition of the fact that there exists what I call occasional programmers.
Yes.
People that are never going to be programmers for a living. They don't want to have all the cuteness in their head. They want just, it's why BASIC, Microsoft had the right idea with BASIC in terms of having that be the language of Visual Basic, the language of Excel and SQL Server. They should have converted that to Python 10 years ago. Like the world would be a better place if they had. But
there's also there's a beauty and a magic to the history behind a language. In Lisp, some of the most interesting people in the history of computer science and artificial intelligence have used Lisp. So
yes,
you feel.
Well, it's back to that language. When you have a language, you can think in it.
Yeah,
and it helps you think better.
And it attracts a certain kinds of people that think in a certain kind of way, and then that's there. Okay, so what about like small laptop with a tiny keyboard, or is there like three screens?
Good question. I've never gotten into the many screens, to be honest. I mean, and maybe it's because in my head I kind of just swap between windows.
Right.
Like partly because I guess I really can't process 3 screens at once anyway. Like I just am looking at one and I just flip. I flip an application open.
So what about
where it's really helpful is actually when I'm trying to do, here's data and I want to input it from here.
Right.
Like that's the only time I really need another screen.
So now, because you're both a developer, lead developers, but then there's also these businesses and there's salespeople, and you're working with large companies,
operations people, hiring people,
the whole thing. Which operating system is your favorite still at this point? So Linux was the early days.
So yeah, I love Linux as a server side, and it was early days. I had my own Linux desktop. I've been on Mac laptops for 10 years now.
Yeah, this is what leadership looks like. You switch to Mac. Okay, great.
Yeah, pretty much. I mean, just the fact that I had to do PowerPoints, I had to do presentations, and plug in. I just couldn't mess with plugging in laptops. It wouldn't project, and yeah.
So you mentioned also Quantsite Labs and things like that. What was the first computer program you've ever written? Do you remember?
Whoa, that's a good question. I think it was in 4th grade. Just a simple loop in BASIC.
Basic,
yeah, on an Atari 400, I think, or maybe it was an Atari 800. It was a part of a class, and we were just basic loops to print things out.
Did you use go-to statements?
Yes, we use go-to statements.
I remember in the early days, that's when I first realized there's like principles to programming. When I was told that don't use go-to statements, those are bad software engineering principles. Like it goes against what great, beautiful code is. And I was like, oh, okay, there's rules to this game.
I didn't see that until high school when I took an AP computer science course.
Right.
I did a lot of other kinds of just low programming in TI. But finally, when I took an AP computer science course in Pascal.
Wow.
It was Pascal. That's when there are these principles.
Not C or C++?
No, I didn't take C until the next year in college. I had a course in C. But I haven't done much in Pascal, just that AP computer science course.
Now, sorry for the romanticized question, but when did you first fall in love with programming?
Oh, man, good question. I think actually when I was 10, my dad got us a Timex Sinclair, and he was excited about the spreadsheet capability. But I made him get the add-on so we could actually program in BASIC. And just being able to write instructions and have the computer do something. Then we got a TI 99.4a when I was about 12. And it had sprites and graphics and music. You could actually program it to do music. That's when I really sort of fell in love with programming.
So this is a real computer with with memory and storage and processors. So we're not,
the
Timex TI.
The Timex Sinclair was one of the very first. It was a cheap, I think it was still expensive, but it was 2K of memory. We got the 16K add-on pack. Mm-hmm. But yeah, it had memory and you could program it. You had in order to store your programs, you had to attach a tape drive. Remember the sound that would play when you converted the modem that would convert digital bits to audio file. It was set on a tape drive. Still remember that sound, but that was the storage.
And what was the programming language? Do you remember?
It was BASIC.
And
then they had a VisiCalc. And so a little bit of spreadsheet programming in VisiCalc, but mostly just some BASIC.
Do you remember what kind of things drew you to programming? Was it working with data? Was it video games? Games?
Math.
Mathy stuff?
Yeah, I've always loved math. And a lot of people think they don't like math because I think when they're exposed to it early, it's about memory. Mm-hmm. When you're exposed to math early, you have a good short-term memory. You can memorize timetables. Mm-hmm. And I do have a reasonably, not perfect, but a reasonably long little short-term memory buffer. And so I did great at times tables. I said, I'm good at math. But I started to really like math, just the problem-solving aspect. And so computing was problem-solving applied. And so that's always kind of been the draw, kind of coupled with the mathematics.
Did you ever see the computer as like an extension of your mind, like something able to achieve?
Not till later.
Okay.
Yeah, not then.
It's just like a little set of puzzles that you can play with, and you can play with math puzzles. And
yeah, it was too rudimentary early on. Like it was sort of, it was a lot of work to actually take a thought you'd have and actually get it implemented. And that's still work, but it's getting easier. And so, yeah, I would say that's definitely what's attracted me to Python is that was more real, right? I could think in Python. Speaking of foreign language, I only speak another language fluently besides English, which is Spanish. And I remember the day when I would dream in Spanish. And you start to think in that language. And then you actually I do definitely believe that language limits or expands your thinking. There are some languages that actually lead you to certain thought processes.
Yeah, like so I speak Russian fluently, and that's certainly a language that leads you down certain thought processes. Right? Well, yeah, I mean, there's a history of the 2 world wars,
right?
Of millions of people starving to death or near to death throughout its history, of suffering, of injustice, like this promise sold to the people, and then the carpet or whatever is swept from under them. And it's like broken promises, and all of that pain and melancholy is in the language. The sad songs, the sad hopeful songs, the over romanticized, like I love you, I hate you, the sort of the swings between all the various spectrums of emotion. So that's all within the language. The way it's twisted, poetry. There's a strong culture of rhyming poetry. So like the bards, like the sing. There's a musicality to the language too.
Did Dostoevsky write in Russian?
Mm-hmm. Yeah. So like Dostoevsky, Tolstoy, all the
the ones that I know about, which are translated, and I'm curious how the translations.
So Dostoevsky did not use the musicality of the language too much, so it actually translates pretty well because it's so philosophically dense that the story does a lot of the work. But there's a bunch of things that are untranslatable. Certainly the poetry is not translatable. I actually have a few conversations coming up offline and also on this podcast with people who've translated Dostoevsky. And that's for people who work in this field know how difficult that is. Sometimes you can spend months thinking about a single sentence,
right?
In context, like, because there's just the magic captured by that sentence, and how do you translate it just in the right way? Because those words can be really powerful. There's a famous line, "Beauty will save the world," from Dostoevsky. There's so many ways to translate that, and you're right. The language gives you the tools with which to tell the story, but it also leads your mind down certain trajectories and paths.
Yes.
To where over time, as you think in that language, you become a different human being.
Yes.
Yeah.
Yeah, that's a fascinating reality, I think. I know people have explored that, but it's, I guess, rediscovered.
Well, we don't. We live in our own like little pockets. Like, this is the sad thing.
Mm-hmm.
Is I feel like, unfortunately, given time and given getting older, I'll never know the Chinese world, because I don't truly know the language. Same with Japanese. I don't truly know Japanese, and Portuguese and Brazil, that whole South American continent. Like, yeah, I'll go to Brazil and Argentina, but will I truly understand the people if I don't understand the language? And it's sad because I wonder how many geniuses we're missing because so much of the scientific world, so much of the technical world is in English, and so much of it might be lost because we don't have the common language.
I completely agree. I'm very much in that vein of there's a lot of genius out there that we miss, and it's we're sort of fortunate when it bubbles up into something that we can understand or process. There's a lot we miss. So that's why I tend to lean towards really loving democratization or things that empower people, or I very resistant to sort of authoritarian structures. Fundamentally, for that reason, well, several reasons, but it just hurts us.
Yeah,
we're worse off.
So speaking of languages that empower you, so Python was the first language for me that I really enjoyed thinking in.
Yeah,
as you said.
Sounds like you shared my experience too.
So do you remember when you first kind of connected with Python, maybe even fell in love with Python?
It's a good question. It was a process. It took about a year. I first encountered Python in 1997. I was a graduate student studying biomedical engineering at the Mayo Clinic. And I had I'd been involved in taking information from satellites. I was an electrical engineering student, used to taking information and trying to get something out of it, doing some data processing, get information out of it. And I'd done that in MATLAB. I'd done that in Perl. I'd done that in, scripting on a VMS. There's actually a VAX VMS system, and they had their own little scripting tools around Fortran. Done a lot of that. And then as a graduate student, I was looking for something and encountered Python. And because Python had an array, had two things that made me not filter it away. Because I was filtering a bunch of stuff. It was Yorick. I looked at Yorick. I looked at a few other languages that are out there at the time in 1997. But it had arrays. There's a library called Numeric that had just been written in 95, like not too much earlier, by an MIT alum, Jim Huguenin. And I went back and read the mailing list to see the history of how it grew. And there was a very interesting, fascinating to do that, actually, to see how this emergent cooperation, unstructured cooperation happens in the open source world that led to a lot of this collective programming, which is something maybe we might get into a little later about what that looks like.
What gap did Numeric fill?
Numeric filled the gap of having an array object. So
there was no array object.
There was no array. There was a one-dimensional byte concept, but there was no n-dimensional, 2, 3, 4-dimensional tensor, they call it now. I'm still in the category that a tensor is another thing, and it's just an ND array, we should call it, but kind of lost that battle. And
there's many battles in this world, some of which we win, some we lose.
That's exactly right. So, but it was, it had no math to it. So Numeric had math and a basic way to think in arrays. So I was looking for that, and it had complex numbers. A lot of programming languages, and you can see it because if you're just a computer scientist, you think complex numbers are just two floats, so people can build that on. But in practice, a complex number as one of the significant algebras that helps connect a lot of physical and mathematical ideas, particularly to FFT for an electrical engineer, and it's a really important concept. And not having it means you have to develop it several times. And those times may not share an approach. One of the common things in programming, one of the things programming enables is abstractions. But when you have shared abstractions, it's even better. It sort of gets to the level of language of actually we all think of this the same way, which is both powerful and dangerous, right? Because powerful in that we now can quickly make bigger and higher level things on top of those abstractions. Dangerous because it also limits us as to the things we maybe left behind in producing that abstraction, which is at the heart of programming today and actually building around the programming world. So I think it's a fascinating philosophical topic. That
will continue for many years, I think.
For many years.
As we build more and more and more abstractions.
Yes, I often think about, we have a world that's built on these abstractions that, were they the only ones possible? Yeah. Certainly not, but they led to, it's very hard to do it differently.
Yeah.
Like there's an inertia that's very hard to, push away from. That has implications for things like, the Julia language, which you have heard of, I'm sure. And I've met the creators and I like Julia. It's a really cool language, but they've struggled to kind of against the tide of like this inertia of people using Python and there's strategies to approach that, but nonetheless, it's a phenomena. And sometimes, so I love complex numbers and I loved arrays. So I looked at Python and then I had the experience. I did some stuff in Python and I was just doing my PhD. So I was out, my focus was on, I was actually doing a combination of MRI and ultrasound and looking at a phenomena called elastography, which is you push waves into the body and observe those waves, like you can actually measure them. And then you do mathematical inversion to see what the elasticity is. And so that's the problem I was solving, is how to do that with both ultrasound and MRI. I needed some tool to do that with. So I was starting to use Python in 1997. In 1998, I went back, looked at what I'd written, and realized I could still understand it, which is not the experience I'd had when doing Perl in 95, right? I'd done the same thing, and then I looked back and I'd forgotten what it was even saying. Now, I'm not saying it. So that may, hey, this may work. I like this. This is something I can retain without becoming an expert per se. And so that led me to go, I'm going to push more into this. And then that 98 was kind of when I started to fall in love with Python, I would say.
A few peculiar things about Python. So maybe compared to Perl, compared to some of the other languages. So there's no braces.
Yeah.
So space is used, indentation, I should say, is used as part of the language.
Yeah. Right.
So did you, that's quite a leap. Were you comfortable with that leap, or were you just very open-minded?
It's a good question. I was open-minded, so I was cognizant of the concern, and it definitely has specific challenges. Cut and pasting, for example, you're cut and pasting code, and if your editors aren't supportive of that, or you're putting into a terminal, and particularly in the past when terminals didn't necessarily have the intelligence to manage it now IPython and Jupyter Notebooks handle it just fine, so there's really no problem. But in the past, it created some challenges, formatting challenges. Also, mixed tabs and spaces. If editors weren't clear on what was happening, you would have these issues. So there were really concrete reasons about it that I heard and understood. I never really encountered a problem with it personally. Like, it was occasional annoyances, but I really liked the fact that it didn't have all this extra characters, right? That these extra characters didn't show up in my visual field when I was just trying to process understanding a snippet of code.
Yeah, there's a cleanness to it. But I mean, the idea is supposed to be that Perl also has a cleanness to it because of the minimalism of like how many characters it takes to express a certain thing.
Yeah.
So it's very compact.
Yeah.
But what you realize with that compactness comes, there's a culture that prizes compactness. And so the code gets more and more compact and less readable to a point where it's like, like to be a good programmer in Perl, you write code that's basically unreadable.
Right.
There's a culture like
correct, and you're proud of it.
Yeah, you're proud of it.
And it's, right, exactly, and it's like feels good, and it's really selective. Like it means you have to be an expert in Perl to understand it.
Yeah.
Whereas Python allowed you not to have to be an expert. You didn't have to take all this brain energy. You could leverage what I say. You could leverage your English language center, which you're using all the time. I've wondered about other languages, particularly non-Latin based languages. Latin-based languages with the characters are at least similar. I think people have an easier time, but I don't know what it's like to be a Japanese or a Chinese person trying to learn a different syntax. Like, what would computer programming look like in that? I haven't looked at that at all, but it certainly doesn't. Leveraging your Chinese language center. I'm not sure Python or any programming language does that. But that was a big deal. The fact that it was accessible. I could be a scientist. What I really liked is many programming languages really demand a lot of you, and you can get a lot, you do a lot if you learn it. But Python enables you to do a lot without demanding a lot of you. There's nuance to that statement, but it certainly it's more accessible. So more people could actually, as a scientist, as somebody or an engineer who was trying to solve another problem besides point programming, I could still use this language and get things done and be happy about it. Now, I was also comfortable in C at that time.
And MATLAB, you did a little bit.
And MATLAB, I did a lot before that. Exactly. Yeah. So I was comfortable in those three languages were really the tools I used during my studies and schooling. But to your point about language helping you think, one of the big things about MATLAB and APL before it. I don't know if you remember APL.
Nope.
APL is actually the predecessor of array-based programming, which I think is really an underappreciated. If I talk to people who are just steeped in computer programming, computer science, like most of the people that Microsoft has hired in the past, for example, Microsoft as a company generally did not understand array-based programming. Like culturally, they didn't understand it. So they kept missing the boat, kept missing the understanding of what this was. They've gotten better, but there's still a whole culture of folks that doesn't programming. That's that's systems programming or web programming or lists and maps. And what about an n-dimensional array? Oh yeah, that's just an implementation detail. Yeah. Well, you can think that, but then actually, if you have that as a construct, you actually think differently. APL was the first language to understand that, and it was in the 60s, right? The challenge of APL is APL had very dense, not only glyphs, like new characters, new glyphs, but they even had a new keyboard, because to produce those glyphs, this was back in the early days of computing when, the QWERTY keyboard maybe wasn't as established. Like, well, we can have a new keyboard, no big deal. But it was a big deal, and it didn't catch on, and the language APL, very much like Perl, as people would pride themselves on how much could they write the game of life in 30 characters of APL. APL has characters that mean summation, and they have adverbs. They would have adjectives and these things called adverbs, which are like methods, like reduction. Reduction, it would be an adverb on an add operator, right? So, but using these tools, you could construct, and then you start to think at that level. You think in n dimensions, is something I like to say, and you start to think differently about data at that point. Now it really helps.
Yeah, I mean, outside of programming, if you really internalize linear algebra as a course, it philosophically allows you to think of the world differently.
Yes,
it's almost like liberating. You don't have to think about the individual numbers in the n-dimensional array. You can think of it as an object in itself, and all of a sudden this world can open up. And you're saying MATLAB and APL were like the early C. Because I don't know if many languages got that right ever.
No, they didn't. Even still, I would say. I mean, NumPy is a inheritor of the traditions. Like, I would say APL J was another version that was. What it did is not have the glyphs, just have short characters, but still a Latin keyboard could type them. And then numeric inherited from that in terms of let's add arrays plus broadcasting plus methods, reduction, even some of the language like rank is a concept that was in Python and is still in Python for the number of dimensions, right? That's different than say the rank of a matrix, which people think of as well. So it came from that tradition, but NumPy is a very pragmatic, practical tool. NumPy inherited from numeric, and we can get to where NumPy came from, which is the current array, at least current as of 2015, 2017. Now there's a ton of them over the past 2 or 3 years. But we can get into that too.
So if we just sort of linger on the early days of what was your favorite feature of Python? Do you remember like what?
Yeah.
So it's so interesting to linger on like what really makes you connect with a language. I'm not sure it's obvious to introspect that.
No, it isn't. And I've thought about that to some length. I think definitely the fact that I could read it later, that I could use it productively without becoming an expert. And like other languages I had to put more effort into.
Right. That's like an empirical observation. Like you're not analyzing any one aspect of the language. It just seems time after time when you look back, it's somehow readable.
It's somehow readable. And then it was sort of, I could take executable English and translate it to Python more easily. Like I didn't have to go, there was no translation layer. As an engineer or as a scientist, I could think about what I wanted to do, and then the syntax wasn't that far behind it.
Yeah.
Right. Now there's some warts there still. It wasn't perfect. Like there's some areas where I'm like, it'd be better if this were different or if this were different. Some of those things got added to the language too. I was really grateful for some of the early pioneers in the Python ecosystem back, because Python got written in 91 is when the first version came out. But Guido was very open to users. And one of the sets of users were people like Jim Huguenin and David Asher and Paul Dubois and Conrad Hinson. These were people that were on the mailing list, and they were just asking for things like, hey, we really should have complex numbers in this language. So let's, there's a J, there's a 1J, right? And in fact, they went the engineering route of J is interesting. I don't think that's entirely favoring engineers. I think it's because I is so often used as the index of a for loop. So I think that's actually why.
Probably.
Right.
I mean, there's a pragmatic aspect.
But the fact that complex numbers were there, I love that. The fact that I could write ND array constructs and that reduction was there. Very simple to write summations and broadcasting was there. I could do addition of whole arrays. So that was cool. Those are some things I loved about it.
Language?
The KDL is the name of the programming language and the code we give the chemicals. So Chi, as in, it's actually like an XML format, but I've now taken it from script to a fully expressible programming language. So we can do dynamics, and there's for loops in there and conditional statements.
Right, but the structure, it started out as like an XML type of thing.
Yeah. And now the chemist doesn't need to program in KDL. They can just go to the software and type in add A to B, reflux, do what they would normally do, and it just converts it to KDL, and they have a linter to check it and error correct.
So how do you, not with ASCII, but because it's a Greek letter, how do you go with, how do you spell it just using the English alphabet?
We just
XDL?
XDL, or we put in Chi. And it was named by one of my students and one of my postdocs many years ago, and I quite liked it. It's like, it's important, I think, when the team are contributing to such big ideas, because it's their ideas as well. I try not to just rename, I didn't call it Cronin or anything because they keep saying, the chemistry, when they're putting stuff in the computer, one of my students said, we are asking now, is it Cronin complete? And I was like, what does that mean? I said, well, can we make it on the damn machine? And I was like, oh, is that a compliment or a pejorative? And they're like, well, it might be both.
Yeah. So you tweeted, quote, why does chemistry need a universal programming language? ? For all the reasons you can think of: reliability, interoperability, collaboration, remove ambiguity, lower cost, increase safety, open up discovery, molecular customization, and publication of executable chemical code, which is fascinating, by the way. Just publish code. And can you maybe elaborate a little bit more about this KDL? What does a universal language of chemistry look like? A Cronin complete. language.
It's a Turing complete language, really. It's so what it has a series of operators in it, like add, heat, stir. So there's a bunch of just unit operations, and all it is really is just it's with chemical engineers. When I talked about this, that you've just rediscovered chemical engineering, and I said, well, yeah, I know. I said, well, that's trivial. I said, well, not really. Well, yes, it is trivial, and that's why it's good, because we've not only have we rediscovered chemical engineering, we've made it implementable on a universal hardware that doesn't cost very much money. And so the KDL has a series of statements like define the reactor. So it defines the reagents. So they're all labels. So you assign them. And I also implemented at the beginning is, because I give all the hardware IP address, you put it on a graph. And so what it does is the graph is equivalent to the processor firmware, the processor code. So when you take your KDL and you go to run it on your computer, you can run it on any compatible hardware in any configuration. It says, what does your graph look like? As long as I can solve the problem on the graph with these unit operations, and you have the resources available, compiles.
Aha.
We could carry on for years, but it's compilation. And what it now does is it says, okay, the problem we have before is it was possible to do robotics for chemistry, but the robots were really expensive. They were unique. They were vendor locked. And what I want to do is to make sure that every chemist in the world can get access to machinery like this at virtually no cost, because it makes it safer. It makes it more reliable. And then if you go to the literature and you find a molecule that could potentially cure cancer, and let's say the molecule that could potentially cure cancer takes you 3 years to repeat, and maybe a student finishes their PhD in the time and they never get it back. So that it's really hard to kind of get all the way to that molecule, and it limits the ability of humanity to build on it. If they just download the code and can execute it, it turns, I would say, the electronic laboratory notebook in chemistry is a data cemetery, because no one will ever reproduce it. But now the data cemetery is a Jupyter notebook, and you can just execute it.
And people can play with it. The access to it,
reversion
orders of magnitude is increased. We'll talk about so as with all technologies, I think there's way more exciting possibilities, but there are also terrifying possibilities, and we'll talk about all of them. But let me just kind of linger on the machine learning side of this. So you're describing programming, but it's a language. I don't know if you've heard about OpenAI Codex, which is...
I'm playing with it.
You're playing Of course you are. You really are Rick from Rick and Morty. This is great. Okay. Except philosophically deep. I mean, he is, I guess, kind of philosophically deep too. So for people who don't know, GPT-3, it's a language model that can do natural language generation. So you can give it a prompt and it can complete the rest of it. But it turns out that kind of prompt, it's not just completes the rest of it, it's generating like novel sounding text. And then you can apply that to generation of other kinds of stuff. So these kinds of transformer-based language models are really good at forming deep representations of a particular space, like a medium, like language. So you can then apply it to a specific subset of language, like programming. So you can have it learn the representation of the Python programming language and use it to then generate syntactically and semantically correct programs. So you can start to make progress on one of the hardest problems in computer science, which is program synthesis. How do you write programs that accomplish different tasks? So what OpenAI Codex does is it to generate those programs based on a prompt of some kind. Usually you can do a natural language prompt. So basically, as you do when you program, you write some a comment which serves the basic documentation of the inputs and the outputs and the function of the particular set of code, and it's able to generate that. Point being is you can generate programs using machine learning, using neural networks. Those programs operate on the boring old computer. can you generate programs that operate? There's got to be a clever version of programs for this, but can you write programs that operate on a computer?
Yep. There's actually software out there right now. You can go and do it.
Really?
So, yeah. It's a heuristic. It's rule-based. But what we've done, inspired by Codex, actually, is over the summer, I ran a little workshop. Some of my groups got this inspired idea that we should get a load of students and ask them to manually collect data, to label chemical procedures into KDL. And we have a thing called Synth Reader. So there's a bunch of people doing this right now, but they're doing it without abstraction. And because we have an abstraction that's implementable in the hardware, we've developed basically a chemical analog of Codex.
When you say, sorry to interrupt, when you say abstraction in the hardware, what do you mean?
So right now, a lot of people doing machine learning and reading chemistry and saying, oh, you've got all these operations, add, shake, whatever heat.
Right.
But because they don't have a uniform, there's a couple of groups doing it, competitors actually, and they're good, very good, but they can't run that code automatically. They are losing meaning, and the really important thing that you have to do is generate context. And so what we've learnt to do with our abstraction is make sure we can pull the context out of the text. And so can we take a chemical procedure and read it and generate our executable code? Yes.
What's the hardest part about that whole pipeline, from the initial text, interpreting the initial text of a paper, extracting the meaningful context and the meaningful chemical information, to then generating the program, to then running that program in the hardware? What's the hardest part about that pipeline as we look towards a universal Turing computer?
So the hardest
computers.
The hardest thing with the pipeline is that the software. The model gets confused between some meanings, right? So if, chemists are very good at inventing words that aren't broken down. So the classic word that you would use for boiling something is called reflux. So reflux is you'd have a solvent in a round bottom flask. At reflux, it would be boiling, going up the reflux condenser and coming down. But that term reflux could be changed, to people often make up words, new words, and then the software can fall over. But what we've been able to do is a bit like in Python or any programming language, is identify when things aren't matched. So you present the code and you say, this isn't matched. You may want to think about this. And then the user goes and says, oh, I mean reflux, and just ticks a box and collects it. So what the Codex or the Chemex does in this case is it suggests the first go, and then the chemist goes in and corrects it. And I really want the chemist to correct it, because it's not safe, I believe, to allow AI to just read literature and generate code at this stage.
Because now you're having actual, by the way, Chemex, nice. Nice name. So you are unlike, which is fascinating. We live in a fascinating moment in human history. But yes, you're literally connecting AI to some physical, and like it's building something in the physical realm.
Yeah.
Especially in the space of chemistry that operates sort of invisibly.
Yeah. Yeah, I would say that's right. And it's really important to understand those labeling schemes, right? And one of the things I was always worried about at the beginning, that the abstraction was going to fall over. And the way we did it was just by brute force to start with. We just kept reading the literature and saying, is there anything new? Can we add a new rule in? And actually our KDL language exploded. There were so many extra things we had to keep adding. And then I realized the primitives still were maintained and I could break them down again. So it's pretty good. I mean, there are problems. There are problems of, interpreting any big sentence and turning it into an actionable code. And the Codex is not without its problems. You can crash it quite easily, right? You can generate nonsense. But boy, it's interesting. I would love to learn to program now using Codex, right? Just hacking around, right? And I wonder if chemists in the future will learn to do chemistry by just hacking around with the system and writing in different things. Because the key thing that we're doing with the chemistry is that where a lot of mathematical chemistry went wrong is people, and I think Wolfram does this in Mathematica, he assumes that chemistry is a reaction where atom A or molecule A reacts with molecule B to give molecule C. That's not what chemistry is. Mm-hmm. Chemistry is take some molecule, take a liquid and a solid, mix it up and heat it, and then extract it. So the programming language is actually with respect to the process operations. Mm-hmm. And if you flick in process space, not in chemical graph space, you unlock everything. Because there's only a finite number of processes you need to do in chemistry. And that's reassuring. And so we're in the middle of it. It's really exciting. It's not, the be all and the end all. And there is, like I say, errors that can creep in. One day we might be able to do it without human interaction. You simulate it and you'll know enough about the simulation that the lab won't catch fire.
I mean, Python is an integral part of it. Just for the fun of it, let me ask, what's your most and least favorite aspects of Python?
Ooh, most and least. I mean, I love that it's like object-oriented and functional, I guess, that you can kind of like get both of those benefits for how you structure things. So if you would just want to quickly whip something together, the functional aspects are nice.
It's your primary language, like for programmatically generating stuff?
Yeah, it's home for me.
Python
it's home. Yeah.
Sometimes you travel, but it's home. Got it.
It's home. I mean, the biggest disadvantage is that it's slow. So when you're doing computationally intensive things, either you have to like think about it more than you should, how to make it efficient, or it just like takes long.
Do you run into that at all? Like with your work?
Well, so certainly Old Manum is like way slower than it needs to be because of how it renders things on the back end is like kind of absurd. I've rewritten things such that it's all done with like shaders in such a way that it should be just like live and actually like interactive while you're coding it if you want to you have like a 3D scene, you can move around, you can have elements respond to where your mouse is or things. That's not something that user of a video is going to get to experience because there's just a play button and a pause button. But while you're developing, that can be nice. So it's gotten better in speed in that sense, but that's basically because the hard work is being done in a language that's not Python, but GLSL, right? But yeah, there are some times when it's like there's just a lot of data that goes into the object that I want to animate that then it just like Python is slow.
Well, let me quickly ask, what do you think about the walrus operator, if you're familiar with it at all? The reason it's interesting, there's a new operator in Python 3.8. I find it psychologically interesting because the toxicity over it led Guido to resign, to step down from his...
Is that actually true, or was it like there's a bunch of surrounding things that also... Was it actually the walrus operator that...
Well, it was an accumulation of toxicity, but that was the most toxic one. Like the discussion, that's the most number of Python core developers that were opposed to Guido's decision. He didn't particularly, I don't think, cared about it either way. He just thought it was a good idea. This is where you approve it. And like the structure of the idea of a BDFL is like you listen to everybody, hear everybody out, you make a decision, and you move forward. And he didn't like the negativity that burdened him after that.
People like some parts of the benevolent dictator for life mantra, but once the dictator does things different than you want, suddenly dictatorship doesn't seem so great.
Yeah, I mean, they still liked it. He just couldn't, because he truly is the B in the benevolent. He really is a nice guy. I mean, and I think he can't. It's a lot of toxicity. It's difficult. It's a difficult job. That's why Linus Torvald is perhaps the way he is. You have to have a thick skin to fight off the warring masses. It's kind of surprising to me how many people can like threaten to murder each other over whether we should have braces or not, or whether like it's incredible.
Yeah, I mean, that's my knee-jerk reaction to the walrus operator is like, I don't actually care that much either way. I'm not going to get viscerally passionate. My initial reaction was like, yeah, this seems to make things more confusing to read. Yeah. But then again, so does list comprehension until you're used to it. So like if there's a use for it, great. If not, great. But like, let's just all calm down about our spaces versus tabs debates here and like be chill.
Yeah, to me, it just represents the value of great leadership, even in open source communities.
Does it represent that if he stepped down as a leader?
Well, he fought for it. No, he got it passed.
I guess, but like, I guess, sure.
It could represent multiple things too. It can represent like failed dictatorships, or it can represent a lot of things. But to me, great leaders take risks, even if it's a mistake at the end. Like you have to make decisions. The thing is, this world won't go anywhere if whenever there's a divisive thing, you wait until the division is no longer there. Like that's the paralysis we experience with like Congress and political systems. It's good to be slow when there's indecision, when there's people disagree. It's good to take your time, but like at a certain point, it results in paralysis, and you just have to make a decision. The background of the site, whether it's yellow, blue, or red, can cause people to like go to war over each other. I've seen this with design. People are very touchy on color choices. At the end of the day, just make a decision and go with it. I think that's what the Walrus operator represents to me. It
represents the fighter pilot instinct of like quick action is more important than
just like hearing everybody out and really thinking through it, because that's going to lead to paralysis.
Yeah, like if that's the actual case, that it's something where consciously hearing people's disagreement, disagreeing with that disagreement, and saying he wants to move forward anyway. That's an admirable aspect of leadership.